Big data, it's why big data started is because in 2001, 2002 onwards, when internet age came, the volume of data started becoming huge. Earlier, people had Oracle, DB2, MySQL Server, and all this. So SQL Server and MySQL, wherein only selected people who had access to the application were generating the data. But with internet age, websites coming in, the whole world is creating data for, let's say, yahoo.com or google.com or Twitter or LinkedIn. So the volume of data was huge. Velocity of data was very huge. The data was coming at very, very fast pace. The variety of data was also huge. You have the structured data, unstructured data. Structured data is which has all those columns. Semi-structured data is like some sort of JSON type of format. Unstructured data is videos and images. So all this data was started coming in. Veracity of data is, the data was not always clear. So if you are working on an application in your enterprise, let's say ICICI Bank or some application in your company, you enter something on the UI, it gets stored in RDBMS at the backend. That becomes, this data is correct because your application building validation. But sometimes when data is uploaded on the internet, like comments on the websites, on the shopping sites, video, images, and so many other things. So you do not know whether the data can be trusted or cannot be trusted. So it's some vagueness comes there. So all these problems started coming in, and that led to the invention of big data. Yahoo was the first company who released the open source version of big data. Google came up with in 2002, Google came up with a paper called MapReduce and Distributed File System. And Yahoo hired one person who was building on this, and Yahoo came up with open source implementation of MapReduce and implementation of distributed file system, which is HDFS. And we'll cover HDFS in more details. There are people keep adding more and more V's. Initially started with 3 V's, then 4th V got added, then 5th V. Now there are some 7 V's also. But that's besides the point. You can go and read about this on the internet. Why existing ETL solutions were not sufficient? Because RDBMS problem in the RDBMS type of system is that if you have to do some processing on Oracle or data stored in Oracle or SQL Server, MySQL, or any such systems, you have to bring data from the database server to your application layer. Now think about billions and billions of records. If you want to apply some business logic, you have to fire query in the database server, and the data will, billions of records will travel from your database server to your application layer. And there are other inherent problems. The RDBMS was by design not columnar storage, and which causes a problem. A lot of disk IOs used to happen. So by design, they were not suitable for big data problems. So that's why the need for new solutions like MapReduce, Spark, Hive. We'll talk a little bit about Hive also later. So general prerequisite for this course is basically you should know either of these languages, Python, Scala, and Java. If you don't know any of these languages, then at least start learning Python. Please go and mute everyone. I think So, so that's about this. And these are the only 3 slides I have in this. Now we'll directly jump onto the Spark part. If there is any quick question anyone wants to ask, please ask. Otherwise, I will start the Spark training.
Sandeep, I have one question. Hello.
Yeah.
Like we have a many like ETL tools like Informatica Power Center, Ab Initio, and all. So in the presence of that tool, why we need to use Apache Spark?
Yeah, good question. I will quickly answer that. If more discussion needed, we can discuss it offline. See, these tools have their own problems. These tools have been there before even big data came. And if you see all this platform, Ab Initio, Informatica, they were not able to, initially they were falling very, very far behind these open source, big data platforms. They are adapting it now, and still they are not there where big data is. One advantage which goes very much in favor of big data is that it is getting driven from open source community. Ab Initio, Informatica are the proprietary software, which only one company drives. And one company can have as many people, they can't compete with open source. The innovations happening in the Hive, in Spark, and the Presto from framework, these are all open source big data, frameworks, which are getting used in, thousands of companies and solving big complex problems. And the performance wise, the feature wise, the cost wise, these solutions don't stand anywhere near that. Okay. So
Sandeep, one question.
Yeah, go ahead.
As you mentioned, right, regarding this database thing. So now we have a partitioning option over there, and we can store that thing, cloud.
I got your question.
Yeah.
Even with partitioning, the underlying design of the most of the RDBMS save data in B-tree format. B-tree is an data structure. You can read about how it stores. So it's by design is row storage. So when you apply the big data solutions over RDBMS, it just has so many disk IOs that it sucks at the performance. Performance is pretty bad if you run big data frameworks over the RDBMS.
Okay.
These are the things we'll be covering today. What is the HDFS? What are file formats? Then we'll be jumping onto Spark. And when we talk about file formats, some of the questions which got asked about RDBMS will get answered there. We'll discuss Spark session, driver executor, running on Yarn. Someone asked about Yarn question that will get answered here. RDD dataset and data frame, how to read from and save into RDBMS. Although we are in big data, in the RDBMS are not suitable for big data processing, but still there are many places where you need to read from RDBMS, like some master data you need to read from RDBMS. So things like this. What are RDD functions? Then shuffle and partitions. You don't have to take the notes. I will be sharing this PPT with you, and the recording will also be shared with you. Just pay attention to what I am saying, and and practice over the weekdays. What is HDFS? HDFS is Hadoop Distributed File System. That's the full form. What is, when we talk about any big data system, always in your mind, when you try to visualize, always think about, a set of clusters. Any distributed system has, a set of machines which form a cluster. And the processing happens on all those machines together. One processing is distributed over all those machines together. Now, when we are talking about HDFS, we are not talking about processing. We are talking about storage. Now, I will explain with an example. Let's say you have 1 terabyte file, and 1 terabyte is 1000 GB. And let's say you have one cluster, Hadoop cluster, which has 1000 nodes. To keep the discussion simple, when I upload this 1 terabyte file to that Hadoop cluster, the 1 GB of that file gets stored on each node. So because there are 1000 nodes, so 1 GB on each node, with 1000 nodes, it becomes 1 terabyte. So that's how I know the file HDFS works. There are little bit of nitty-gritties of this, which we're going over now. The data in HDFS is stored in form of blocks. What is a block? Block is every file which you give to HDFS. It gets split into block, and you can configure the block size in one configuration. So when you have some cluster, Hadoop cluster, there are some configurations which you can set. For HDFS also you can set configuration, and you can say by default I think the block size is 128 megabyte. You can change it to more or less, but we'll go with the assumption that the block size is 128 megabyte. Now with 128 megabyte, if you have 1 GB file, how many chunks will be there for that 128 megabyte? So 1 GB divided by 128, that will be 4 blocks. So basically blocks is another synonym of chunks. So we are splitting that 1 gigabyte file into 4 chunks, into 4 blocks. And each of these blocks can be stored on any of the machines in the cluster. But I will talk about it, how this works. For time being, you understand that the file gets split or chunkified into blocks. And block size can be configured. And these blocks are stored on the nodes called data nodes. When you think from the storage perspective, at that time, you look at the cluster from the prism of NameNode and DataNode. So any distributed system you work with, whether it's related to data engineering or outside data engineering also, you will always have the master node and worker node concept. Even in data engineering, when you deal with frameworks like HBase, map or anything like HBase, not as frequently used as Hive, but even in HBase also there's a concept of master node and the worker nodes. So when you look at that concept of master node and worker nodes from the prism of storage, which is HDFS, the master node is called name node and the worker nodes are called data nodes. So the blocks are stored in the data node. Now the master node, which is the name node, it keeps track of the location of the blocks in the data node for each file. The example which we took, 1 GB file gets split into 4 blocks. Now these 4 blocks are, let's say you have 50 node cluster. So these 4 blocks can be stored on any of these 50 nodes. So name node knows that this was the file name and these were the total nodes blocks got created, and this is the place where each block got stored. This is a data node address where each block got stored. So that information is kept with the name node. Important thing to note here is, in any ecosystem, where you have distributed programming, including Hadoop, there will always be a scenario where your machines will crash. I was in Nokia, and we had before that, almost all the companies I know of are moving towards cloud. Amazon has its own cloud, which you can use using AWS. Azure has their own cloud. IBM is having their own cloud. There are many cloud providers, and most of the companies are moving towards cloud. Although you may be on the cloud, or you might have your own premise cluster where you have your own data center and you have put Hadoop clusters there. Whatever setup you have, there will always be scenarios where your machines will go down. In Nokia, we had 200 node cluster. Every month, 3 machines were crashing. Either hard disk was getting corrupted, or memory was getting corrupted, or some or other problem was happening there. So every month, 3 nodes were getting replaced. So this is part and parcel of the life of the distributed systems. But if your data is on one machine and that machine goes down and gets corrupted, then you lose your data. To prevent such scenarios, Big Data provides a concept for HDFS. There is a replication you can enable. By default, replication is 3, which means that each block which you have created for for a file, so 1 GB file had 4 blocks. So each of these blocks will be stored on 3 machines. So in total, you will be storing 12 blocks for this file. The idea is that if one machine which has these blocks goes down, then the data will not get lost. There will always be another machine which will have the data. You can change the replication factor. You can change the replication factor to more than 3 or even less than 3 also. Danger of changing it to less than 3 is that there's a high probability of losing your data. The disadvantage of changing to more than 3 is that you will be adding more storage cost and your processing will be a little slower, because when you save that, save your file, now it has to save at 4 places. So there'll be little performance hit you will take there. Now we discussed that the data node is the worker nodes where blocks are stored, and the name node is the master node where your which contains all the metadata. So we're talking about the master node now. It is a single name node, it's a single machine. It regulates the access to file by clients. So your client here can be you manually using HDFS commands, or you writing any code in Java or Scala or Python or whatever language you are comfortable with, to save the file into HDFS or read the file from HDFS. So in that case, your code, your application becomes that client. So that client, always talks to name node. And name node, why does it need to talk to name node? Because the client might need to save the file on HDFS, or it might need to read the file from HDFS. For all these purposes, client will be interacting with name node. Now, how does that interaction happen? What does name node give to the client, and what does client do after that? We'll be covering in the next slides. Name node is a repository of HDFS metadata. Now, what is this HDFS metadata? This metadata is what I explained earlier. You have the file name, how many blocks that file has, where is the location of each of these blocks. So that information is contained in the metadata on the name node, and it is stored in the memory. It deals with client of HDFS to provide them the information about location of data blocks. I hope that was clear to everyone. This is at very high level. This is how the architecture looks like. You have this name node, which is a master node, and then you have this set of data nodes. Here there is some file which is this is the example from the HDFS Apache website only. So this is the file which has three replication factor is 3, and then it has set up some other information like what are the block, how many blocks, and all those things, and where each block is stored. That information is there. So a client always interacts with the name node and tries to for a file, because client will be contacting the name node with some file name, because it's trying to read or write some file. So it contacts with the, when it's trying to read the file, it will contact the name node. Name node will tell, okay, you're trying to read this file, and this file has these many blocks, and these are data nodes with these blocks are stored, and that client will go to those data blocks and read directly. Dhartesh, I will answer your question in a while. Now, by default, replication factor is 3. Now, what happens is we don't need to worry about these 2 points, but in our normal day-to-day development, when we do the development, but in hindsight, we should know how the internally HDFS is getting stored. If you take any data center, in data centers, you by the way, I suggest you Google search on data centers, and if you can watch a YouTube video, it's interesting how machines are stored in data centers. So they have the concept of rack, and machines are racked in one over another in the rack, and the chance of if one rack collapses, all machine will collapse there. So for that purpose in mind, when you have a replication factor is 3, the two same blocks are stored on 2 different machines on the same rack, and third block gets stored on the different machine in the different rack. So rack is the place in the data center where you keep your machines. Like in data center, there are physical machines like AWS. You deal with AWS. AWS has their own data center. In their data center, they might put physical servers which are on a rack. So a rack, like in you have shoe rack, right? Or you have rack to store your clothes. So similar rack is there for the storing the computers also in your data center. This is the file write sequence. So you have a client. This HDFS client is a library. Like if you deal with Java, then it's a jar file. If you deal with Java or Scala, it's jar file. If you deal with Python, then maybe it's some pip module or something. So now this client can be anything. A Java program, or me as a human trying to deal with HDFS or Scala program, Python program, or whatever. Now I'm trying to create a file here. So what happens is I internally talk to the HDFS client, which is a jar HDFS dependency in my code, and that HDFS client will connect me to the name node, and then name node will tell me. So when these things happen, HDFS name node, we go to the name node. This whole process goes to the name node with the information that I have the file with this much size with this name. So give me the data nodes where it should be stored. So what name node does is name node figures out, okay, this is 1 GB file, so maybe there'll be 4, and I have 128 GB block size, so there'll be 4 blocks of this, and the replication factor is 3. Let's keep it simple. If it has to store 4 blocks, then it will give the data nodes of data node address of these blocks, data node address to store these blocks to the HDFS client. Then what HDFS client will know is it will get the data node address. It will go and start writing the first data node. The moment it writes to the first data node, automatically, from that data node, process will be triggered to write into second data node, and similarly for third data node. So this is how the file write happens. The same is the case with file read. I'm trying to read that file. Then I go to the name node and I'll ask that I'm trying to read this file. Give me that file. Name node will give the data node addresses where the blocks of this file are stored. Then HDFS client will take those data node addresses, read the blocks of this, combine that file together and give to the real client. Right? This HDFS client will do the magic of connecting to the data nodes, getting the blocks, and then giving the file to the client. Client will not ever know. Client, your Java program or me as a human will never know. Will need not need to know that which block had which data node had which block. It doesn't need to know. So NameNode, file system metadata. Again, NameNode is master node. It stores the metadata in the memory. What it does is, whenever you are creating a file or doing some operation over a file, you updated it and then uploaded it back. So it puts that thing in the event in the edit log. There's a file called edit log. That edit log file is stored in the local file system of the NameNode. The metadata contains the files in HDFS, and for each block information about which data node has which block stored. Basically, this is what I repeated earlier. And then I'll answer your question towards the end, man. The NameNode will contain the name of the files, how many blocks, and which data nodes have these blocks, and that's stored in the memory. And edit log file will contain all the information, which file got created and which blocks and all those things. Data nodes are slave nodes or worker nodes. These days there's no one wants to call anyone slave. So even in tech industry, slave nodes have been replaced by worker nodes. They store that when we give block to a data node, that block gets saved into the local file system. And the data node will keep reporting their blocks to the NameNode, so that NameNode knows that this data node has this block of this file. Yeah, someone raised a hand. What was the question? Any question anyone has? Okay. Now, the reason this data node reporting their blocks information to the NameNode is, NameNode knows that I have this file, and this file has, for our discussion, let's say the file size is 128 MB, which has only one block. Now there's a replication factor 3, and there are, same block is getting stored on 3 machines. If data nodes give the report to the NameNode that I have this block, stored, the NameNode will know that first of all, this data node is alive, and second, the one block of this file is stored on this data node, and I don't have to, trigger another similar block, copy on some other data node. It is responsible for serving read and write requests from the file system client. So this is the sequence diagram which we saw, that anytime you want to read or write, any client wants to read or write, they always contact the NameNode. So this I already covered. It sends a heartbeat to the NameNode, which is block report for the data node. So the way it sends the block is by sending along with the heartbeat. If it doesn't, data nodes do not send the heartbeat to the NameNode, then NameNode will consider that data node as dead data node, and it will stop. It will remove that data node from its list, and it will not send any more blocks to that data node. So that's what at high level is. So this internally you ask this question: what is happening in step 2, right? So client has the file. The file is with the client, and client is telling that this is my file. You have to create this file in HDFS. This file exists in the client, and then whatever HDFS call is being made, it gets redirected to this, so that it comes to know what is the file size, so that it can ask the NameNode that how much give me the data nodes for this file size. So that's what is happening here. Okay, block replication. So in the NameNode, you have the file name, number of replicas, block IDs, and all those sorts of things. So for example, this is a file name. This slide is also copied from the Apache website of HDFS. Let's say you have this file name, and it has 2 replicas, and it has block 1 and 3. So if you see 2 replicas, see there will be for one there will be 2. One will be stored in 2 data nodes, one here and one here. 3 will be stored in 2 data nodes, one here and one here. This another file, by the way, has replication factor as 3, and it has these blocks, 2, 4, and 5. So 2 will be saved in 3 machines. One machine is this, second machine is this, and third machine is this. Same is the case with 4 and 5. Secondary NameNode, I think Rahul asked this question, and someone replied also. Rahul replied to some question, and that this topic is about that. When you have in any distributed system, like in this case HDFS, you have NameNode. What if NameNode crashes? You remember I told you the machines keep crashing day and night, and NameNode will also, there's a possibility NameNode can also crash. So what happens then? I also told you that it stores everything in the memory. Then you lose all the data from the memory, right? So there's a secondary NameNode. What the secondary NameNode does is it will take the information from the primary NameNode and keep that information itself. You can configure how frequently it takes the information from primary NameNode. By default, it's each hour, and it tries to keep itself up to date with the NameNode. But still there will be some delay because it's not doing it live. It's contacting NameNode after a certain interval and keeping itself up to date. When primary NameNode goes down, then sometime primary NameNode will come up also. Like if there is an out of memory or something happened, then that will get fixed and primary NameNode will get booted up. Once it gets booted up, then it has lost all the metadata information from its memory. What it will do is it will contact the secondary NameNode and get that metadata information back and will work as primary NameNode again. One important thing to remember is secondary NameNode will never replace primary NameNode. It will always act as a some backup of whatever primary NameNode has. There is another concept called standby NameNode. I forgot to put that in this slide. But the standby name, if you have standby NameNode configured and your standby NameNode is constantly in sync with the primary NameNode, and then your primary NameNode goes down, then standby NameNode will replace the primary NameNode. Then secondary NameNode will still keep performing the same function. Whatever is happening on the NameNode, it will try to get that information and keep a backup of that. There's a question: the redundancy is configured at a node level, cluster level, at a file level, or at every level. I'm assuming when you say redundancy, it's a replication factor you're talking about. You configure replication factor at the cluster level, that whatsoever files are coming at that cluster will get replicated this many number of times. This is Hadoop 2. If you have watched this recording of the same sites earlier, you will know there was Hadoop 1 which had a lot of problems. To solve that problem, Hadoop 2 came. Yarn, YARN is the technology in Hadoop 2, but now even that is getting replaced with Kubernetes. So I will explain how this Hadoop 2 works. Even if you do not understand this, that's okay, because in reality, while writing a Spark program, you don't have to deal with this. And also in 3-4 years time frame, my assessment is that it will get replaced by Kubernetes anyway. But let's say this is a cluster, and this cluster consists of these nodes: 1, 2, 3, 4, 5, 6, 7 nodes, correct? And one of the node is declared as a master node. As we already discussed, when you look from the storage perspective, your master node is called as NameNode, and your worker nodes are called data nodes. So you have all the data nodes here, correct? You can see at the bottom. That is from the storage perspective. Now, when you're processing it, when you need to run some processing, which is reading this file and applying some business logic over this file, whose blocks are stored in data node. So when you do that processing, then right now many companies are running that processing over Yarn. Even Spark is getting run over Yarn. So in that case, first thing which I'll do, let's say I have some business logic which I want to run over the records which are in a file, and that file is 10 GB on HDFS. And that file is 10 GB, it is on HDFS. So I have my business logic in a jar, and I have this file uploaded in HDFS. So when I submit this my Spark application to Yarn, what Yarn internally will do is it will my application will contact the resource manager, and it will tell I have some business logic and I have some files to process. First of all, give me a place where can I figure out how many nodes I will need for that processing. So resource manager will say, okay, I'm giving you, this node, and then this client, which is Spark client, will start an application master there. And what that application master will do is, it will look at the file, it will look at the some criteria and figure out that it needs, let's say, 50 GB RAM and 50 CPUs. Now this application master will go to the resource manager again and say, now I figured it out that I have this requirement of 50 GB and 50 CPUs. Now resource manager, what it will do is, it will check out of all the nodes, what all memory and what all CPUs available. These are the worker nodes. That resource manager, resource manager will figure it out, and resource manager will tell this application master, okay, on this node and on this node and this node, I have this capacity available. So you take 25 GB RAM and 25 CPU from this node, and 20 GB RAM and 20 GB from 20 CPU from this node, and 5 GB RAM and 5 node CPU from this node. So then application master itself will contact these nodes and will start their processing. These containers are nothing but the JVM. It's a JVM instances under which your Spark program is running. So that's how it works. I'll repeat it one more time. And if it's still not understandable, then no need to worry. Still no need to worry. Let's say this client is a Spark application. It goes to it has to run some processing over a file which in HDFS, but it doesn't know how much capacity, how much hardware capacity it needs. So first thing, it will contact the resource manager in Yarn and tell resource manager, give me one machine first where I can do my housekeeping work and figure it out how many how much capacity I need to process this 10 GB file. So resource manager will say, okay, I'm giving you this machine, run your application master here. So Spark will start this application master here. Only thing this application master will do is, it will figure out to do this processing of this file, how many CPUs and how much RAM I need. How does it figure out? There are certain parameters you pass in the Spark configuration, or there are some default value. Based upon those, it figures it out. And the file size also. File size also plays a role there. Then based upon all these parameters, figures it out that I need 50 CPU and 50 GB of RAM. And then it goes to then application master itself will goes to the resource manager and it asks that give me the nodes where I can get 50 GB RAM and 50 CPU. A resource manager might give address of these 3 nodes, and it will tell this application master that I have 20 GB and 20 CPU here, 20 GB and 20 CPU here, and 10 GB and 10 CPU here. So you see this color, same color is here. So then this application master will start the Spark processing here, here, and here. That's how distributed processing will start. Again, when you look from the storage perspective, you will always see there is one name node and rest are data nodes. When you look from the processing perspective, from the Yarn, you have a resource manager, which is single place where you ask for the resource, and then it will give the application master. Sorry. Then the application masters, this client has this application master, this client has this application master. So this application master will ask for the resources for this client, and from the resource manager will give these resources. This application master will ask resources for this client from the resource manager, and to this application master, resource manager will give the address of these 2 nodes. So from the processing perspective, we have resource manager, application master, and node manager. Like these are containers which are JVM processes running inside the node. One data node refers to one machine. Maybe one data node refers to one machine. That's correct. Absolutely correct. Is there no upper limit? We don't give. Will the application take entire? No, this is by default. So we'll talk about it, Rashmi. Just hold on to your question. When we talk about the processing, how the partitioning works in Spark, your question will get answered there. Do we need to have client on? Do we need to have client specific application manager? No. The way the application master works is that once you give your, once you run on Yarn, and we'll see in Spark how does that happen. But you can give Spark application to Yarn, you can give your Hive query to Yarn, you can give MapReduce to Yarn, you can give pick to Yarn. all of this process remains same. Yarn can handle all of these things together. Resource manager is a master node. It's mostly run on the name node. You can see the resource manager is running on the name node itself. Application master is not related to the name node at all. Generally, resource manager and name node are generally at one machine. Application master is any other worker node. Resource manager will pick any worker node which is free for this client and give this client as an application master. It is possible that when this client submits the application one more time, after one day, it might get some different machine as application master. The driver memory and all those things in the Spark we'll discuss later, Shivaji. I have slide for that. So we'll go over that and I will simulate that how all that work. Just hold on to that question. I will skip this replication and rack awareness. Saurabh, if you have any question, please feel free to ask.
So Sandeep, like this container, right? So every container will be running, assume that we are using Java. So every container will be running its own JVM, right?
Absolutely, yes. This is the container you are talking about, right? Yes.
Yes, yes.
It will be running a JVM itself, correct.
So all the, like if I have a 5 container over there, like here we have a 2 containers. So all these 2 containers will have their own JVMs, different JVMs, right?
Exactly, yeah. This is one JVM, this is separate JVM, correct.
Okay, thank you.
So Kapil, can you write your question again for Yarn and Kubernetes? So node manager is good question. I didn't want to have this detailed discussion for Yarn, but anyway, I'll tell you what node manager is. So when a client asks resources from resource manager, and resource manager, tells, you go and, work, create your application master here. Then client will do is, it will go to that application master and it will tell resource manager that I have this, it will tell node manager that this resource manager has given me permission to start a process application master on this machine. So node manager will validate that. So it will give to the node manager. Node manager is responsible for starting this application master. It will validate that request to the resource manager first, and node manager will keep pinging the resource manager, heartbeat, so that resource manager knows that this node is alive. There are a lot of questions coming. Can we hold on to these questions for 10 more minutes, and I will have finished this session, then ask all these questions one by one, because otherwise I'll never be able to proceed. Kubernetes replacing Yarn, Kubernetes to Docker, I will answer that in the doubt clearing session. Just hold on to these questions. Is separate data node needs to be allocated for application master? Yes, application master runs on any random data node, which is free at that time. Data node is for storage, application master is for processing. So let's keep that in mind. There is no relation between application master and data node. From the storage perspective, all the worker nodes are data nodes. From the processing perspective, resource manager is the master node, and rest all the workers can either be running application master or be running containers. I want to cover this file format first, and then we'll we'll finish this session. So let's try to cover that fast. Then people can stay for asking any questions. First of all, what is the need for file formats in Hadoop ecosystem? Why can't we just work with text file? So whatever we discussed earlier, right? We said RDBMS can't, RDBMS are not suitable for big data. What does that mean? It basically means that we can't use RDBMS functionalities. RDBMS inbuilt indexing, primary key, which helps in the query optimization. Queries run fast. Now, because we can't use any of this, but still in big data, we need some way of accessing the file in a most efficient way. And if time permits, in some session I'll go over one Parquet details of how Parquet stores internals of Parquet format. But at this moment, for your understanding, we need this format so that the big data processing engines like Spark can not only save the data effectively, but also can query the data also effectively. If you have billions of records and you want to query, let's say, you are Amazon and you're storing all the data in the cluster, and you want to query, give me the records for what are sales happened in Bangalore for July month. I want to get all the records from the files in HDFS. So such queries need to be performed at, need to, need to be performant. They need to execute fast. So so that's why there's a need for such formats coming up in the big data system. And we'll go into a little bit of details of each this. First is text format. It's plain text format. It is not used often. It is used mostly for testing, debugging, when you are doing some POC or something. This is ORC format. It's optimized row columnar, and it is very fast reading because of better indexing. The Parquet format, it came from Google, and you can go to orc.apache.org or parquet.apache.org or avro.apache.org and look into details of each of these. Parquet is for Google. It has its own format. It also has some way of row group and column chunk format, and we'll go a little bit into that. Avro is mostly based on JSON, and we are dealing with only JSON formats. Then preferably you can use Avro. If you do not know what is JSON format, it's a key value pair, and you can go do a Google search about that. So this is the comparison between Avro, Parquet, and ORC. What is schema evolution? Schema evolution is, let's say I'm getting data which has 10 columns, and after 1 month, there's a new column got added at the source. Let's say I'm getting this data from some server, and that server had this data which initially for 1 month 5 columns, and after 1 month it added 6 column also, which means the schema has evolved. So we need to add the 6th column on HDFS also, on the big data system also. So that's called schema evolution. Avro supports schema evolution, the best. ORC is the second, and Parquet is third. Compression. Here we are talking about huge big data. So compression is important, otherwise your storage cost will shoot up like anything. So ORC has the best compression, Parquet in middle, and Avro is minimum. Splittability. What is splittability? Split across multiple disks for scalability and parallel processing. So ORC has best splittability, Parquet and Avro medium. Where these frameworks are used often, Avro is used in Kafka and Druid. Druid is, I will not be talking about Druid, but it's some sort of data warehousing, in real time. Parquet is used in Impala, Arrow, Drill, and Spark. So we'll be working in Spark, so mostly we will do Parquet. And ORC is used in Hive and Presto. Avro is raw format, Parquet and ORC are columnar format. It's very efficient when you have more writes. It's efficient when you have more reads. Column format, I just want to spend 1 minute on column format, and I think then we'll call it a day. And then next session starts with Spark. So what is column format? Let's say you have a table which contains billions of records, and let's say it's customer table. For any customer, you need to know their some ID is there, their first name is there, last name is there, phone number is there, city is there, state is there, date of birth is there, and the zip code is there, and which country they belong to. These are 9-10 attributes which customer entity might have. Now, most of the time when you do big data processing, you fetch one column and you say, select phone number from this customer entity. Now, what is columnar storage is, columnar storage will store all the phone numbers together to keep it simple for time being. It will store all the phone numbers together. When you say select phone number from customer, it will go to that location on the disk and say, okay, phone numbers are stored together. Now it gets all the phone number together, return to the query. In the row format, what happens is your row is stored together, which is the ID, first name, last name, email, phone number, city, state, and all those will be stored together. And second row will again be stored together. Third row will again be stored together. So if you want to get only one column, then it has to go to each row one by one and then get the value of that column. So if there are billions of records, it will be going to billions row one by one, and it makes it slow. If it's columnar storage, all the phone numbers for all the rows are stored in one place. It goes to one place and get all the phone numbers together. What do you mean by read and write? Parquet is more efficient when you have less write and more read. Same is the case with ORC. When you have more write and less read, then Avro is efficient. I think let's stop it here. I will pause the recording now and I'll give you a chance to ask questions. So today we'll be discussing the, starting from Spark, what is Spark and how does that help and what are the different components of Spark. You all might have some basic understanding of Spark. So some of this might be repetition for some of you, but bear with me for the benefit of everyone. So Spark has different modules. It has Spark Core, SQL, Streaming, Machine Learning Library, and Graph. This is the representation. The code, the code which is common across multiple components goes in Spark Core. And if you want to use, there are different libraries for SQL, Streaming, Machine Learning, GraphX. And Spark can work on, and I have slide for this also later. It can work on Spark, and you can run Spark as a standalone, or you can run on Yarn, or you can run on Mesos, or now Kubernetes is also there, so you can run on Kubernetes as well. Yeah, this is what we discussed. So now, why Spark is needed? So, before Spark, there was mostly people were using MapReduce. They were using Pig also, but Pig internally was starting MapReduce only. And the problem with the MapReduce was its design was that it writes data to the disk. And the moment you start writing to the disk, like mapper gets over, then it writes to the disk, and then reducer picks up from there, reads from the disk. So when you're talking about big data and you involve disk IOs, then by design, your job will become slow. So what Spark does is it tries to do everything in the memory. And that's why it is way faster than the MapReduce. MapReduce does not leverage the memory cluster as effectively, so it's slow because its design is writing to the disk, and then next steps like reducer and everything picks from there. Another advantage is you have the interactive shell. So you have Spark shell. You can try your program and practice your program there, or debug something there, and it comes quite handy. And if you have written ever MapReduce program, you would have realized that writing the MapReduce itself is a huge is a huge thing. You have to write a mapper, you have to write a reducer, then you have to write a driver where you set the mapper, reducer, input directory, output directory, formats, and everything. And if you have more, if you want to use combiner and everything, you have to write another class combiner. So minimum 3 classes you will write. I mean, you can all put in one class itself, but the minimum 3 components you will write. And if you want more, then you have to write like combiner, etc. You write more components. So Spark is not that way. Spark is very easy to code. And as you will see in the subsequent sessions, you don't have to worry about writing mapper, reducer, and combiner, driver separately. It's all part of one. They did some analysis. The logistical regression is a machine learning algorithm. So they ran for the same logistical regression for the same data set. They ran that algorithm over Hadoop and Spark. So Hadoop took these many minutes, and Spark got finished in these minutes. So this is the drastic performance difference between Hadoop and Spark. What are the Spark core concepts? So one thing I will recommend you, if you have watched my previous video, which was on the same topic, there also I'm indicating that this you never forget. Keep that in your mind always. At least this rectangle. And I'll tell you why. But before that, let me explain you what this diagram represents. You have a driver program. So you have a driver program, and as far as your construct goes, as far as your coding goes, everything is in one class. But internally, what happens is the code starts from the driver program. You always deal with Spark, but internally, there's a Spark context behind that. And that Spark context deals with the cluster manager to get the resources to get where the job should run, and that your code runs on worker node. So this is what you should keep in mind. Again, I'm iterating. The worker node can have one or more executor. Here in the diagram, we are showing only one executor, but it can very well have one or more than one also. One executor is one instance of JVM, and one executor can have one or more than one task. So this you always keep in mind. Your code runs inside the tasks on the executor, which are residing in the worker node. What is Spark session? It is entry point for Spark SQL. It provides a way. So here we are talking about Spark context, but in your in your Scala program, or in Python, or even Java, or even R also, you always deal with Spark session. And Sparks, all your code will be on, most of the code will be using Spark session, but once in a while you might need to use Spark context also, and we'll cover whenever we need to use Spark context later. So Spark session is entry point for Spark SQL. It provides a way to interact with various Spark functionality with a lesser number of constructs. So now, what do you mean by lesser number of constructs? Before Spark 2.0, if you had to deal with Hive, you had to create a Hive context. If you had to deal with SQL, you had to create SQL context. So likewise, there are a few contexts, you have to create a corresponding context. But in in Spark 2, they created Spark session, which unifies all the context. So with one Spark session, you can run Hive queries or SQL queries and everything. If you just have to, while creating the Spark session, you just have to say enable Hive support. Like you're creating a Spark session here. So, and you say .app name and say .enable Hive support, then it will be available. It can interact with Hive also. And by default, it will you can run the Spark SQL also using the same Spark session. So point is, you don't have to keep creating this different context. With one Spark session, you can do all of this. You can use the Spark session to create RDD, data frame, and datasets. We'll cover what RDD, data frame, and datasets are in a while. If you're using Spark Shell, in your Spark Shell, Spark will automatically give you, Spark session in a variable called Spark. So in your Spark Shell, you can directly say spark.read. Whatever, CSV or whatever. If you are in a program and you want to create a Spark session, this is a construct you use to create a Spark session. You have to use Spark session.builder, .master, app name, and get or create. The master, it tells you where you are running your Spark application. Is it on local, or is it on Yarn or Mesos? And now even Kubernetes also come. For Kubernetes, we'll discuss separately later. And this app name is a name which you give in the, which appears on the, on the UI. We should go to Spark UI, and we'll discuss Spark UI also in some session. So this application name will appear as, with this name on the UI. And get or create. If already exists, it will give it to you. If it does not exist, it will create some Spark session and then return to you. This is one pictorial representation. So you had the Spark context. You have the, for the core API, you have streaming context for streaming API, SQL context. Even in the streaming API, I think I should mention that we discussed this diagram, right? Spark SQL and Spark streaming. Now, in Spark streaming, what is happening is they came up with the structured streaming some years back. And the constructs of structured streamings are very similar to Spark SQL. This has data frame, this also data frame. And this is, Spark session exists in the Spark SQL. Now it exists in the structured streaming also. So once you learn the concept in Spark SQL, at least the construct wise, it remains same in Spark streaming. You just have to only understand how Spark streaming works. That's all. Now what this local and yarn, I think you already know. Local means you are running on the, you are running on the local machine, and yarn, you are running on the yarn machine. Spark session, you could have multiple Spark session in your program, in your application. What does that mean? If you already created a Spark session using get or create, use that Spark and say new session over this. So I just copied this from Spark documentation. I will read it out, then I will explain you what what these lines mean. It starts a new session with isolated SQL configurations. Temporary tables, register functions are isolated, but sharing the underlying Spark context and cache data. So when you create a new session, by the way, someone asked this question, and why do we need to create new session in first place? The reason you want to create new session in first place is, let's say in one session you want to deal with just Hive. In another session you want to deal with something else. And you don't want to deal with Hive in the session. So if that's your business, that depends on your business logic, honestly. But if that's your business logic, then you will create, two different Spark sessions. We'll discuss the temporary tables also later, not today in today's session, but in coming session. We'll discuss UDFs also. And of course, there's a caching, you can store your RDD and everything you can cache it or persist it. That also we'll discuss later. Get or create, this method first checks whether there's a valid thread local Spark session. If yes, it returns that one. If it then checks whether there's a valid global default session. If it does not exist, then it check global default session. If yes, returns that one. If no valid global default Spark session exists, the method creates a new Spark session and assigns the newly created Spark session as a global default. Basically, what it is saying is, in layman term, if you have to understand, if the Spark session already exists, it gives you. If it does not exist, it creates and gives you. So that's what get and create does. This is a pictorial representation which I try to do. So Spark earlier used to have Spark context, SQL context, Hive context, Spark streaming context, Spark conf, all of this separately. Now you have one Spark session which has all of this together. It's the same diagram which I showed you earlier. So like this example, when instead of earlier you had to create a Hive context, now you don't have to create that Hive context. You can say .enable Hive support while creating the Spark session itself. And with the same Spark session, you can deal with Hive as well. You can pass various configurations in this. Some of this we'll discuss in coming sessions. What is driver program? You will be hearing this driver program a lot. Driver program is the class, in a programming terminology, it's a class which has main method. Whether it's a Java-based Scala program or Scala-based, or I'm assuming even Python-based, where from your program starts. So it should have main method. With the class which has main method, your driver class. It launches parallel operations in the cluster. So in your driver class itself, you will be creating RDDs and invoking various operations of RDD. So that's the only class you will have for writing the Spark program. But whatever operations you will be doing, in the code inside the driver program, that operations will be getting launched, in a distributed way on the cluster. It accesses the computing cluster. It's a driver. It creates RDD data frame, etc., data frame datasets, which run in the cluster. Now the driver program itself runs in the master node in one of the cluster node. So let's take example of you are running on Yarn. So in the Yarn, you have a cluster which consists of master and worker nodes. So you can, based upon the configuration, which we'll discuss later in coming slide, you can configure for your driver program to run on the master node of Yarn, or you can configure it to run on one of the worker nodes. And what is that configuration? We'll discuss. The question is, there's a question, what will enable Hive support do internally? So if your data is in Hive and you want to read from Hive, or you want, so if this is one of the examples. So if you want to do that, then you enable Hive support. We might discuss something about Hive architecture and everything. But if you want Spark program to deal with Hive, then you enable the Hive support. The driver program converts program into physical execution called tasks, and we'll spend good amount of time on this later. But idea is that we discuss this diagram, right? Which I told you to print in your mind. Always. I will again go here. This is a diagram which you should never forget when you're dealing with Spark. So there's a worker node, executor. Executor has task. One worker node can have more than one executor. So now the real split of the thing, real task creation inside the executor, happens via driver program. So it's natural because all your code is inside the driver program anyway. So task creation and everything will, get driven from the driver program. This is one example of driver program. It is written in Scala. Krishna asked what are stages. Krishna will discuss stages in lot more details later. Just bear with me. So this is one example of driver program written in Scala. Python program will be very similar to this. Whatever you see in Scala, using PySpark also you can write with some changes. So this is the way I created the Spark session. So you can say Spark session.builder. I'm running this on local. This is the app name. Now this is just an example. This will not be, you will not be creating such driver programs in production, because you might be reading from database or HDFS or Hive or S3 or Azure Blob Storage. So this your data I'm just hard coded some, rows and creating this data. But in production scenario, this will be getting read from one of these storages, which I just told. So just for, just for explaining, you have this row is a SQL, Spark SQL construct. In this row, you have 3 columns. And so I have created 2 rows. So this data will have 2 rows, each having 3 columns. And the schema, I'm giving the schema to, I'm creating a schema. So this is how I create the schema. So I create a struct type and I'm saying add. So internally, when I say add, it's creating struct field for me. I could very well create struct field, and I have example of those also later. But this is, I'm saying that this struct type has 2 columns, 3 columns. First column is called first name. It is of string type. Second column is called last name. That is also string type. Third column is salary. That's integer type, right? So first, second, and the salary. And then I create a data frame from this. So the way I create data frame from this, I say, because I have this data, I parallelize the data and I pass a schema. So that's how I create the data frame. Then I do something. Generally, when you create data frame like this, I will discuss it's lazily evaluated. Unless you do some action, nothing happens. Here, I'm not doing any action. So in reality, nothing will happen. But I can say df.save or df. I apply some operations, right? And we'll discuss a lot of these operations in coming sessions. Some transformation I apply, and then I take some action. Action is collect, save, take, count, some of these. Okay. Now there are some questions. What does indexing local -1 local -1 means? It basically means that I'm taking 1 core from my local. If I give star, it will take as many core as possible. Everything is case sensitive. I don't know, Karthik, and what do you mean by case sensitive, but the syntax is case sensitive. Parallelize is a construct. If you have some list or something, right, then you can parallelize using this method. Spark context parallelize. So mostly you, as I said, you will not be using this parallelize. You will be reading from the S3 or something. So there is a construct Spark provides Spark dot read or something, and we'll discuss that later. Yeah, you don't have to, Arun, you don't have to decide. There is no fixed way. It depends. Question is, how do we decide how many cores we need in local? Depends upon your load. Depends upon your hardware. Various factors go into deciding how many. People, can you please go on mute? Okay, so this is how you decide. The driver program, this we already discussed. App name is the name of the app. It appears on cluster UI. Master cluster URL, yarn, if you give the yarn, it runs in yarn. If you give local, it runs in local. If there's a K8 something, you give, it runs in Kubernetes. Executor, we are double clicking on executor now. What executor is? It processes in worker process. These are processes in worker nodes in charge of running individual tasks of Spark job. It runs for entire life cycle of application. It provides in-memory storage for RDD. So when you're processing your data frame or data set or RDD, you need to, you need to get memory. So that memory is this memory, in the executor JVM. Whatever is memory, that's where the RDD or data set or data frame gets loaded. After the task is over, these send result back to the driver. One executor you have to remember is one JVM instance. Now these different tasks inside the JVM instance are multiple threads running inside the same JVM. It can run many tasks as we discussed, sequentially or concurrently. If it has resources in terms of memory and everything, memory CPU to run task parallelly, it will run parallelly. If the tasks are such that JVM doesn't have those many resources in terms of memory, etc., then this task will run sequentially. So this is about executor. Yeah, I think Rajesh, very valid point. Please ask, don't direct a message to me for questions, put it in the common forum. Others can also answer. Worker node, will cover the data frame the whole later. And how does the driver node divide a DAG into tasks? I have a simulation for that. I will cover that as well later. So if you don't get answered in by next session, then you please ask these questions. But it will get clarified once we cover all of this. Worker, it's a node which runs executor or executors. It can run one executor or more than one executors also. Task, unit of work on a partition of a distributed data set sent to one executor. Now, I will explain with an example what is task. In terms of Spark, let's say you have a file of 1 GB size on HDFS, and your HDFS block size is 256 MB. So there will be 4 blocks of that size in HDFS. 256 multiplied by 4 is 1 GB. So that 1 GB file is split into 4 blocks, and you write a Spark program to process that file. So in reality, it will create 4 tasks for you. In one executor, across 2 executors, that depends upon how much executor memory and other things you will specify. But in reality, across executors, there will be 4 tasks. One task run, processing 1 block of the data. On HDFS, this is how it works. And these task and partitions are, one task is one partition. So one task in Spark, it means one partition in Spark. Spark application master, this is very specific to YAR. The Spark application master is responsible for negotiating resource request made by driver with Yarn and finding a suitable set of hosts in which to run the Spark application. There is one application master per application. I think I explained you last time also, but I'll reiterate here. This is very, very specific when you are running your Spark job on Yarn. So when your Spark job runs on Yarn, what first thing which happens is an application master gets started on one of the node. Now this application master looks at the file and and varies in a couple of other factors and realizes it needs this many number of nodes. It needs this much capacity. I will not say number of nodes. It needs this much capacity in terms of RAM and CPU, etc. Then this application master will go to the resource manager in YAR, and then it negotiate those resource requests with the Yarn resource manager, and resource manager will give the resources which this application master is asking, and then application master will spin up the executors and tasks on those nodes. So there will be one application master per Spark application, and you can go to this link. It's described in much details here. There are different Spark execution modes. You can run Spark in, I think we discussed that, right? When you give the local or Yarn or something. So you run this in local mode. It runs on local machine. It's not a distributed, and mostly used for unit testing or some debugging or something like this. A standalone, I have not seen anyone using standalone, honestly. Maybe on some test machines or something where you don't need power of Yarn or Kubernetes or something. The third execution mode is cluster. You can use Yarn or Mesos, etc. If you use Yarn, in Yarn we discussed that there's a Yarn cluster. You can run the driver on Yarn. You can pass the configuration. I think I have next slide which tells you when you submit a Spark job. Let's talk about this. So when you submit a Spark job, you have, how it works is this. You have the, you want to process some file on HDFS. So write a Scala code or Java code or Python code to process this. So we'll be discussing Scala, but similar concepts apply for Java and Python, etc. also. So you wrote the code, and you created all your logic is inside the code. Now created a jar file using using Maven or using SBT. You created a jar file. Now you have to submit this jar file. Let's say you are submitting this, you have this Yarn cluster where you can submit. So you say Spark submit and say -- class. This is your main class. This com.df.spark, this is the main class, the driver class, which has the main method. And then you give the jar file. This jar file should have this main class. And then you tell whether it's running, the configuration is Yarn client or Yarn cluster. And I have a detailed explanation of this Yarn client and Yarn cluster, but let's go. This Yarn, there's a difference between Yarn client and Yarn cluster and standalone also. So driver runs in application master here, which is mostly master node. If you give Yarn client, it runs in one of the worker nodes. If you give a Spark standalone, then it will use one of the standalone is also Spark itself become the cluster manager. So question is, what's the difference between standalone and local execution mode? Local execution mode will always have non-distributed, one local machine, not executing the Spark code there. There's no distributed processing happening there. In Spark standalone, Spark gives you a default cluster manager. So there's a distributed processing happening on the Spark standalone also, but it's not as matured and as robust as Yarn or Kubernetes are. But you could use Spark standalone and have the distributed processing run. So on that, your driver also runs in one of the worker nodes. In the Yarn cluster and Yarn client, application master will go to the resource manager and ask the resources. And a Spark standalone, of course, because Spark internal cluster manager, so internally a client will figure out how many resources it needs and it will use those many resources. Who starts executed process? So once application master asks the resource manager to, application master goes to the resource manager and asks for certain resources in terms of CPU and memory. So the resource manager will give those resources. Resource manager will tell application matter on this 1, 2, 3 host you can go and start your application. So application master will go to those host 1, host 2, host 3, and that node manager is running on the host 1, host 2, host 3. So application master will tell on to node manager of host 1 to start that application there. Then it parallelly it is talking to host 2 also and host 3 also, and their own respective node manager it is requesting to start the processing. Whatever has it will ask the resources whatever has been given to application master by resource manager. Question is, does it mean that in local mode there's only one node? Yes, and it's make it non-different. That's correct. Persistence services. I think I will skip all of that. Most of that. There are some services in Yarn. Mostly you deal with the resource manager and node managers. Resource manager is the one which gives resources to the application master, and application master take those resources and spin those tell node managers to run those resources there. When I say resources, it just means CPU and RAM mostly. In Spark standalone, this is Spark. There are Spark master services and Spark worker nodes. There is no in Yarn cluster. You cannot use Spark shell. The Yarn client you can use Spark shell. In Spark standalone, Spark shell is you can use. How do you specify local? Using local star. If you give star, it will use as many as possible, or you can give in brackets how many cores you want to use. If you want to use Spark standalone, you have to pass dot master, right? Remember when I created the Spark session, I said Spark builder, and then I passed some configurations, and one of the configuration was dot master, and I passed Yarn there. If you want to use Spark standalone, you pass Spark and your wherever the host name where your Spark standalone is running and the port name. Generally it's Spark, your local wherever your Spark cluster is deployed, that machine name, and the port is mostly 7077. If you're running on cluster, then mostly it is Yarn, and Yarn you either pass Yarn client or Yarn cluster. And I already explained Yarn client and Yarn cluster difference. I will have one slide in a subsequent also to explain the difference in little more detail. Or you can pass Mesos as your master, or as a cluster manager, or you can pass Kubernetes as a cluster manager. In the Yarn, if you pass a client mode, which is this, then what happens? The driver runs in a dedicated server, which is master node inside a dedicated process. Driver has all the resources available at its disposal to execute work. It opens up a dedicated NATI HTTP server and distributed the jar files specified to all the worker nodes. So whatever jar files is specified, if you are given the client mode, then it will automatically take care of distributing the jar file to the worker nodes, because your logic is executing on the worker nodes, and logic also needs to access these jar files. Important thing is, it does not use the worker resources because it runs in the master node. If you have limited worker resources and many jobs running, then preferably you do not want your the driver program to take one of those resources. So you can run if you give client mode, it will run on the master node mostly. If you give the mode as cluster mode, then driver will run on one of the worker node. Like in Yarn, it will tell you which worker node you go and run. Like we know that story, application master, resource manager, and everything. But net result will be the driver will not be running on the master node. It will run on one of the worker nodes. It runs again here also dedicated standalone process inside the worker. It takes up at least one core and dedicated amount of memory from one of the workers. So So which means that the resources on the worker which are getting devoted to the driver program. It can be monitored from master node using the supervised flag, and you can reset in case it dies. I have not seen this getting used often because most of the time you have resources on the master. Most of the time you can run in the master node, but once if you don't have then resources on the master node, then you can use this mode. All applications has to be, now here is the catch here. All applications has to be publicly available to worker nodes. The cluster mode will not take responsibility of copying your jars to other worker nodes. In this mode, in the previous mode, client mode, the driver took up the responsibility of distributing the automatically in the background. It happens. You don't have to do anything. But here, the jar will not be distributed public to the worker nodes. You have to manually put them in the shared place or on some HDFS folder, which all worker nodes have access to. So that's the work you have to do. The default mode is nothing. If you don't give any mode, the code won't even compile. Difference between YARN client and cluster mode, this is what just I explained. The YARN client mode runs on the master node and jars automatically get distributed. On the cluster mode, the driver will run into the one of the worker nodes, not on the master node, but then jar responsibility of distributing jar, you have to take care. In the cluster mode, what is the use of master node? Since the driver itself is stored in one of the cluster. I mean, yeah, in that case, there is no use of master node because however number of Spark jobs you are submitting, each of the Spark job starting its driver on the one of the worker nodes. Only thing is, the initial submission, the application master and everything is, even that is also getting created on cluster mode. So in that case, there is not much use of the master node is not at all getting used there in the cluster node. I will skip these questions. We'll discuss this later. When you use PySpark, yes, then still you have to use jars. We'll discuss RDD, and I try to give a pictorial view of what RDD is. So RDD is resilient distributed data set. Important thing to notice, these are very important things. Sometimes in our design or when we start thinking about RDD, we tend to miss this. First of all, it is fault tolerant, and second is immutable. What do you mean by immutable? First, what is the fault tolerant? I will discuss both of these, fault tolerant and immutability, once I explain you how RDD gets created and what RDD is. Then I'll come back to this. Elements can be operated in parallel. So now think about this. You have, to keep the discussion simple. Let's say this is your Hadoop cluster or Spark cluster, and and HDF is also there. You have data stored. You have the a 1 GB file which is had it, and 256 MB is the block. So you'll have 4 blocks of that file. Let's say one block is here, second block is here, third block is here, and fourth block is here. So now, but in reality, this is just one file. It is just that it's stored in these 4 blocks. So the NameNode will know that file. So you can create an RDD, one RDD, and give the file name. I mean, I will show you how to create RDD by providing the file name in HDFS. But over that file, you can create an RDD. So in the driver program, for you, this is just one RDD. But in reality, if you do any operation over this RDD, let's say you map operation or map partition operation, and we'll discuss each of these operation in detail later. But you can do some operation, some transformation over this RDD. All these transformations are parallelly getting executed. In the driver program, you say, do this transformation on RDD. But internally, RDD is applying same transformation here for the data which is here, and here for the data which is here. So, and same in these 2 nodes also. But for driver, it is just one collection, which is just one RDD. Internally, RDD is executing the transformation parallelly here. Now, what is fault tolerant? Fault tolerant is basically if something goes wrong. I don't know. One example could be the worker node goes down, then there's a replica of this data stored elsewhere, right? So you don't have to worry about this, and RDD will still have the data. Immutable is if you do any operation of this RDD. So once you have data loaded into RDD and do any manage operation, I am in the transformation. So when you do any transformation of the RDD, that RDD will never get changed. Every transformation will result in a new RDD. And over that new RDD, if you do any more transformation, it will return in new RDD. So that's what immutability means. Yarn is fault tolerant. Yes, we discussed about Yarn earlier. I would suggest you to watch that video. There's a standby NameNode. From the HDFS perspective, yes, there's a standby NameNode and there's a secondary NameNode. Resource manager of Yarn is also fault tolerant. We have not discussed Yarn in detail because, in my view, after 2-3 years, Yarn will get replaced by Kubernetes. But to answer your question in short, yes, Yarn is also fault tolerant. There are 2 types of operations you can do on RDD. One is transformation and one is action. Now, what is transformation? Transformation is it construct, there are various transformation functions. You can do map, you can do filter, you can do filter, you can do map partition, and there are a lot of those things. We'll cover most of this later. So it constructs a new RDD from the previous one. Like I said, this RDD called line, and you say line.filter, and this is an example. And that filter will give you a new RDD. It never changes an existing RDD, but these are the one of the example of transformation. And every transformation will construct a new RDD from the previous one. Action, it compute result based on RDD. So a result is either returned to the driver or saved to external storage like HDFS, Cassandra, RDBMS, or whatever else you might have, S3 or a blob storage. You can save any of this. Now, so take this example. Let's say there are 1, 2, 3, 4, 5. There are 5 rectangles I'm trying to show here. One rectangle, first rectangle, represents one RDD which you read from database or some file or something. Then you do some transformation, it turns second RDD. More transformation, it turns third RDD. More transformation, it turns fourth RDD. And then more transformation, it turns fifth RDD. Over this fifth RDD, you are seeing action. Action is RDD.save, collect, take, or whatever, right? So the moment you trigger an action, these RDDs are lazily evaluated. So if you don't have any action, you have only transformations, then nothing will happen. The moment you have action, then only the first action, then the executions of RDD will trigger from beginning till end. So and the here what I have tried to show is that first RDD you transformation, it gives second RDD. You do some transformation, it gives third RDD, and so on. So every transformation creates a new RDD. And at the end, you have some action. And then action can, action could be you are saving the RDD into some file or some storage, or you are collecting the result of RDD as a list or something, and that result can get returned to driver. So either of these things are actions, and we'll see some examples of actions later also. Does during RDD creation process copies data from any district file system or blob storage to Spark cluster machines? It depends. If you are doing HDFS, I think I tried to explain an example here. If you are, where did that go? Here. If you are using HDFS, then in data will stay here, right? And you can just create an RDD over this, data doesn't need to move. But when you're using blob storage or S3, and yes, then there'll be some movement of, well, during RDD creation, nothing will happen because I said RDDs are lazily evaluated. During action, these things will happen. With lazy evaluation, does every transformation create a new RDD or it gets loaded lazy? Good question, Arun. So what happens is you can do, if let's say you do not have any action here, you can do as many transformation as you want. Nothing will happen. Actually, none of this RDD will get created. And your driver program will just start it and finish it without doing anything. You have, these 4 or 5 transformation over RDD. First transformation itself will get triggered when you have some action. The moment you have action, then only first transformation will get triggered. First RDD will be created, then first transformation will be applied over RDD, then second transformation, then third transformation, and fourth transformation. And each of these transformation will result in new RDD, but that gets triggered from the first action itself. If there's no action, there's nothing will happen. This is what I try to explain again. RDDs are lazily computed. This is what I was trying to say. Computed first when action is executed. If you don't have any action, then no RDD will be created. These are computed each time action is run. So this is a very important statement, and I'll try to explain what this means. So let's say you have one action which is saving it to a file, And you have another action over the same RDD, which is saving into a database. For whatever reason, I have these two actions. Now, both actions are working on this final RDD. And this final RDD got created by reading from a file and applying these transformations. When I say first action, it will read from somewhere, whatever it's reading from, apply all this transformation and save into a file, because that's my first action. The second action, which is saving to a database, when I do that, it again does the same thing. Again, it's from the file, apply these transformations, and then save to a database, because that's what my second action was. So question is, after an action is triggered, each transformation will be triggered, and then each transformation will result in a new RDD. That's correct. That's correct. If RDD is used in multiple actions, then you should better cache it. Like there's a RDD cache or RDD persist, because when the example which I explained here, right? If for the same final RDD, I have this, I reading some file, creating an RDD from that, then applying all this transformation, and have this final RDD. When I'm doing two actions on this final RDD, one is saving to a file and second saving to a database, then both of these actions will trigger all of this reading from file and then each transformation. I don't need to do that. I could very well have this final RDD as cached. I can say I can use RDD.cache, and over that cache, no matter whatever number of actions are specifying, those, whole of this graph will not be executed. Only the final RDD will be saved. And we will have a detailed explanation of cache and persist later. This is just giving you a high level overview how this cache might help. I think I will use 5 more minutes, then I will open it for questions. So this is one example of RDD. So generally you will not be creating RDD from this array in the memory. You will be creating RDD by reading some file from HDFS or S3 Azure Blob Storage, and I'll explain you how to do that later. But just for our testing purposes, I want to test some functions of RDD. Then I can create an RDD from this array, and then and you can read RDD. You can read RDD. One of the APIs to read from text file is this Spark context.text file. So that also gives you an RDD. Or if you have some data in the memory, from there you want to create RDD, then this is how you do. These are two examples of creating RDD. Now one thing I will I think we are almost. I will explain data frame and dataset, and we'll go into details later. So like RDD, data frame is immutable distributed collection of data. But unlike RDD, data is organized into named columns like RDBMS. So your column 1, column 2, column 3, each row has these columns, right? You can use Hive, CSV, CSV, JSON, Parquet, what you call ORC, sequential file, RDBMS, XML, Cassandra, RDD, all of this can be converted to data frame. What I want to do next time is, let me cover dataset also. Distributed collection of data. It got added into Spark 1.6. It provides the benefit of RDD, which is strong typing and ability to use Lambda function. And I'll talk about Lambda function later. And it provides the advantage of optimization engine. Over RDD, you don't have, Spark cannot run much optimization. But over a data frame, and dataset, Spark can run much optimization. Data frame is best suited for the optimization. Spark optimizes data frame in best possible way. Datasets also it optimizes it, but RDD cannot optimize. In PySpark you don't have dataset. Dataset is available only in Scala and Java. It can be constructed from JVM. Dataset can be constructed from JVM objects. Let's say you have a class person, and it has two variables, name and age. So you can construct, a data set using this. I have a detailed example of how do you convert data set from various other ways also, but this is one of the way. If your data in the memory, and from that memory you want to convert data sets, you can say you have a sequence, this is Scala sequence, and say two data set, and you are passing, this person class, and which has, name, this name and this age, and you're converting to data set, and you can do this. If you want to, if you have some sequence array, this is an array. One collection contains 3 elements, 1, 2, 3. You can convert integer also like this to data set, and you can do any operation. This is one of the transformation. Map is one of the transformation and collect is one of the action. So you can map here. I'm adding just one to each integer and collecting at the end. Question is, nowadays we are using data. We should always use data frame as much as possible, or data set. RDD we should avoid, but sometimes if RDD, sometimes you might need to use RDD. So maybe you are getting image or video, you are processing image or video. That time you might need to use RDD, but most of the time you are dealing with structured data. So at that time you don't have to use RDD. You just use the data frame or data set. Now I will just what I will do is I will not cover this, but what I wanted in some session was maybe in coming week is I want to read data from the database and create a data frame out of it. So this is one thing which you can use over the coming week. You can go to this website dbforfree.net, sign it up, and there it gives you MySQL free instance. You can create one database, give your username, give your password, and give your email address. So it creates a RDB data, it creates a MySQL database for you. What we will do is we'll populate some data into this and using Spark, and we'll read it back using Spark. So in your spare time, before next Saturday, just try to create one, thing here. And remember, this is transient. After some days, it will get deleted. So make sure by Saturday when you come, you have something created here. I will stop it here. I think I will stop at this data sets. It can be data sets can also be manipulated using functional transformation, map, filter, or flat map, etc. It's available in Java and Scala. It's not available in Python and R. Homework for you to guess the reason why it's not available in Python and R. So do that reading, and I will stop now. I am opening up for questions. Let me stop the recording also. Recording. So, like RDD, data frame is also immutable, distributed collection of data. And unlike RDD, data is organized into named columns like RDBMS. This is how a data frame looks like visually. If you have to see, there are rows and there are columns. Like if you were to visualize the RDBMS table, that will be a good analogy to visualize data frame also. You can read data from various sources. These are some of the examples. You can read Hive data, CSV data, JSON data, RDBMS data, XML data, Parquet data, Cassandra, RDD, ORC. There are many such things from S3, from Azure Blob Storage. So you could read from all of this and be able to create the data frame. And we'll see the examples. How you could even give us schema. If the schema, while creating the data, you will be able to provide the schema also. There are some examples below. So a data set is again similar thing, distributed collection of data. It got added in Spark 1.6, and you can. This link I refer a lot. I want to see what all is available in data set. The difference between data frame and data set is this. You can have a class. Let me cover the data set, then I'll tell you the difference. Data set provides the benefits of RDD for strong typing. This is one important thing which data sets gives. Ability to use powerful Lambda function, SQL optimization engine, and it can be constructed from JVM objects. So now what does this mean for strong typing and from JVM objects? I have an example also, by the way, further for this, but let me try to explain verbally right now. Let's say you are trying to read a schema, and that schema is in a file, and that schema, you're trying to read a file, and that data in the file has certain schema, and that schema is, let's assume for our discussion, it has a column called ID, it has column called first name, last name, salary, date of birth, and city. These are the 5-6 columns you have in the in that schema for the data which is in the file. Now, when you read that, sometimes you want to specify, these columns. You could very well specify this column names as part of schema itself, which you can do in data frame. But beyond schema, let's say you have a class, and that class represents this. Let's say class name is customer or employee, let's say class name is employee, and employee has the same columns. It has same variables, which are the columns in the schema. Employee has the ID, first name, last name, date of birth, salary, and city. So employee class is representing the the schema which is there in the file. And what you want to do is you want to have a collect while you're reading that file. You want to have collection of the records in the in that object, employee object. So there will be many employee objects, each object of employee representing one record in that file. So if you want to have such a representation of your data, that is when you use data set. And here you can see one example. I have I'm trying to create a I have a class called person, which has name and age. And just for example purpose here, I have I have one record ND and 32, and I'm converting that to data set. So you will see the case class, this is a data set. So this is a data set of a type person, and I will show you more examples below. Now you can access the, if you have worked on Java list or Java array list or things like this, there are generics. You have list of type person, or you have list of type of some object. So something similar here, but this data set will automatically, so there are encoders, and we'll talk about those also. How does the data in the file get mapped to the one record in the file get mapped to one object of that class? So these are called encoders, and we'll discuss those encoders in detail. But this is what it means for strong typing. You can strong typing means the row in the file is one object, and then you have data set consisting of all such objects. So of course you can manipulate similar as data frame. You can have map, flat map, filter, etc. It's available in Java and Scala. It's not available in Python and R. Why do you think it's not available in Python and R? If someone can guess the reason and either put it in the chat, I will read it out for that. Otherwise, we'll discuss towards the end. Data frames, as I discussed earlier, the data set organized into named columns, equivalent to RDBMS tables. This also we covered. It can be constructed from various sources. This is the one difference. This is one line which you have to remember. A data frame is data set of type data set row. If you go and look at a Spark code, you will not find any class called data frame. You will find a class data set only. But data set of type row is again, if you do not know, it's again a Spark construct. So data set of type row is called data frame. Data frame is available in all languages, and this is how you present. The moment you see this in any Spark program, you can say that it's data frame. And now we'll take one example, and we'll try to read some CSV file. And what I would recommend is that you go and write this program on your environment, whatever environment you have, so that you get some hands-on for this also. Anand Barn says Python and are not strong typecast. Very good. Java and Sahil says Java being compiled language is static typing. Absolutely, these are the answers. You already give the answers. So I am reading some file, and this file is at this location. So if you are reading from S3, you prefix with S3. If you are reading from whatever HDFS, you suffix HDFS. If you are reading from local file, possibly you suffix with F file : // But idea is that I'm reading this file. It's a CSV file, and here see Spark has this format. You will see this format quite often. Spark.read.format. And you pass CSV here, and I'll show you example when you read the JDBC also, data from the RDBMS as well. It's a similar syntax you will use, so it's easy to remember. Spark.read.format CSV, and here I'm passing some schema. I have not mentioned the schema here, but in subsequent slide I will show you how to create even this schema object also. So I'm passing some schema, and I'm telling there's an option, so you can pass some options. One option is I'm telling header is true, which means that CSV file, first line in the CSV file is a header, so that it does not consider that line also, the header line also, as part of the record. So it will skip that line. And you load, and this is of course the, this here I am not providing the schema. Here I'm providing the schema and telling header is equal to true and loading the file. So if I do not provide the schema here, then Spark will give some arbitrary column names. Let's say there are 3 columns in through that into that file. So it will underscore C0 underscore C1 underscore C2. But if I provide the schema, whatever names I would give in the column names I'll give in the schema, Spark will assign those column names to the record in that file. If I do not know the schema and I want Spark to infer the schema for me, so then I can pass it's the same thing. I am reading the CSV file from this location and everything else is same. Header is equal to 2. That first first line is header, so it will skip that. It will not skip that. It will use the column names, the names of this header as the column names here. Here it will not use, but here given a header, it will use those column names as the in the schema in the data frame schema here. Now, what is the type? Whether some column represents a string, or it represents an integer, or it represents a boolean. What is that type? Or it represents a decimal. It represents a decimal. That I am telling Spark here to infer it itself. Then here, if I give this, then Spark is going to take a while to read this file, because it is going over all the records of this file and trying to figure out the data type of, only way it can figure out the data type is by going through all the records. So it will be a little slower, but here it will use the name of the column which are given in header. Here it will use the name of the column which are given in schema, and here it will give the arbitrary column names. So that's one example of reading the CSV files. Spark can read from data frame. Maybe I will add this in assignment also. I will give you if how do you read from a database? It's a JDBC call Spark will make, and I'll talk about a little bit of that. But if you want to practice, if you want to write a Spark program to read from a database and you do not have database set up on your local or anywhere, you can use this website, dbforfree.net. It gives you MySQL database free for certain time. So once you go there, you are signing up. It will ask you this: what is your MySQL database name, user ID, password, and repeat the password and give your email address. So it will send all the information to this email address. And how do you use this information? You check, you'll get an email, you activate the link. So once you activate the link, it will ask you the admin. You can see on the UI itself. If you don't see, then click this link, copy paste this link in the URL. So it will show you the admin, MySQL admin. And on the UI, there will be a place to, create table. So create some table like, imply with, some ID and the name and age. And with this, type varchar integer. And what we'll do initially is, this table is blank, right? There's nothing in this table because we just created it. So we'll just read it and then save it. So this is how we want to do. So if you have Databricks, you can do on the Databricks. This is how you write. If you have local setup, do it in local. But if you're doing on local, you should be connected to internet, because we'll be connecting to this host. So you can say spark.read.format. Here we are using JDBC. Once you use JDBC, then it will expect certain options for this format. One, the URL where you're trying to connect to. So this is the host name. So this is the JDBC URL, JDBC MySQL, and the host name and the port. And this is a database name, demo Spark, which we had given here. This is the demo Spark dataset name. Then it's going to ask you which table, for which table we are trying to read. And then it will ask you the user ID password. So this is the table we have created here. And this is the user ID. And this is the password we have created here. So, so we are giving that. And it's reading. So right now, because we had just created this table, so it will not be, it will be empty. There will not be anything. So if you show it, you will see blank. It will not return anything. Now what we are going to do is we are going to save something to this table, and that's coming in the next slide. So import this org Apache, Spark SQL types. What are these types? We are using this in the schema, and I'll talk about these types. First, randomly I'm creating, some record 1 ABC 20, 2 DF 30 and 3. So what are these? This is the employee ID. Remember this table we had created here. So it had the ID, name and age. So this is what I'm creating to create 3 rows. First row with this ID, name is this, age is this. Second row with this ID, name and age. Then again ID, name and age. 3 rows I'm creating, and this row is also a row is also part of this package. So I created these 3 records. Now here I'm creating. So I told you that you could create the schema at runtime. So when I showed you this, when you read from the CSV file, like here, when I was going to the CSV file, I was passing the schema here, right? But in this page, I did not specify how to create the schema. This is how you create the schema. If you want to create the schema, you create a struct type, and in the struct type you add whatever, each column, what is a type. ID is string type, name is again string type, and age is integer type. So this is the simpler way to create this. By the way, this is Scala syntax. Similar, very similar is there in Python also. So now I'm creating a data frame. So this is the employee data. So I'm parallelizing it and I'm passing this schema. So I got this data frame, and I'm showing it to make sure that I know this is read properly, this data frame. Then I'm writing this data, writing this same thing, format JDBC. So now it's, earlier it was df.read. Now I'm saying df.write, and I'm passing the format as JDBC and giving this URL, the table name, the user ID, and the password. The mode is save up append. So I think someone in the WhatsApp rightly said there are various save mode. There is a save mode append. There is a save mode overwrite, things like this. So, and you save it, and then you save it. So now you will see that, and if you run this program, once you do this, so you return it, right? If you want to read it back, you can run normal SQL, or you can run this program again, because you are reading it from here, and you will see some records coming from that table. Now, one question is this. We discussed that when you are reading from HDFS, the block size of HDFS becomes one partition in the Spark, or one task in the Spark. Like block size, let's say 1 GB file with 256 block size, so there are 4 blocks. These are 4 partitions or 4 tasks in the Spark. But when you're reading from JDBC, how does Spark decide that it needs to have these many partitions? Because partitions or tasks are the only way Spark can parallelize the data. If all data while reading from JDBC goes into one partition, then it's as good as writing a standalone Java program or Python program which is reading from the table. But whole idea we are using Spark is because we want to parallelize it. So how does Spark do the parallelization of JDBC? So Spark decide number of partition for JDBC using either of below options. First is, we said it, right? When you give JDBC option, we pass the URL, the table name, the column name. This is important. The column name, the lower bound and upper bound, and number of partitions. Whatever column name you are passing, this should be one of the column in the table, in this table which you're trying to read from. So this column should be of type numeric, date or timestamp. This column cannot be string or anything other than these one of these 3 types. The lower bound, you can give the the range endpoints. For example, if it is numeric, let's say I have 1 to 1 lakh records, or 1 to 10 lakh records in the table. So I can give the lower bound as 1 and upper bound as 10 lakhs. And I can decide, then I can tell the number of partitions, how many partitions it should have. I can say 10, or based upon my hardware or whatever, I can say it's a 10 or 20. It just does not depend upon the hardware or which Spark runs. It depends upon the hardware which you have on your database also. Because as a big data developer who might not have good exposure to the RDBMS systems, we assume that whatever queries will fire on the on RDBMS systems, whether it is MySQL or SQL Server or Oracle or anything, that database will be able to take it. But in my experience, it doesn't work that way. Any query which hits the database servers, puts load on the server. So you can't just spin 10,000 queries to Spark and hit database with 10,000 queries. Your database will crash. So you have to work with the database team, the DBA database administrators, and figure out how many queries you will fire and how many, based upon that you decide number of partitions. So that's one way. The other way is that you can pass these parameters. So URL, of course, a JDBC URL, table name, and the predicates. The predicate is here array of where conditions for defining custom partitions. One advantage of using this is you can say where name is equal to name between this and this or whatever, or date date we have already covered here, or some other column value is equal greater than this and less than this or whatever. So you can specify all of that. This can be used for non-numeric columns also, and it can be used for dealing with skew. So skew is basically if you have let's say I'm talking about city names. City is my key, and the table has data for more number of records for Bangalore and Delhi, and very less number of records, let's say for I don't know, let's say Jaipur. So this becomes a skew. So if you're creating data, if you're partitioning or on the city names, then the partition for Jaipur will have very less number of records, whereas the partition for metro cities will have more number of records. So that becomes a skew. So to handle such scenarios, you can use this syntax to connect from JDBC. So this is your homework. Go and do this. There's one thing which you can try. So just go through this slides. You have link for all the, you will have the recording as well as the PPT also you have. Write this. If you don't have MySQL, then use this. One other thing which you can do is, if you are feeling little courageous, when you get data from when you read data, right? When you read data after loading it, read it again, you can apply some filter condition. Let's say, I don't know, I want to get records where age is greater than something. Now, why I'm telling you to apply filter condition is there is one important thing, and we'll cover that in details also later, is this. There is something called predicate pushdown. Let's say your database has 10 million records, and those 10 million records, taking the city example again, those 10 million records belong to all the cities. Now let's say your processing is concerned with records only from Bangalore, Delhi, Chennai, and Kolkata. Only for, because you are doing some analysis for metro cities. You are not concerned about all other records from other cities. So what you can do is you can put that in filter condition, and you can say city equal to or whatever. You can city in or city equal, whatever you want to specify. You can put that as filter condition here. Now, one important thing is this. When you so Dhruv has written correctly. So when you put a filter condition, ideal situation would be that that filter condition gets evaluated at the database server only, because out of let's say 10 million records for all the cities, your metro cities have only the rows which are for metro cities are only 2 million. So you don't want to get all those 10 million records from database server to the Spark layer and then Spark filtering those out, because there's a huge network traffic involved. And of course, database, will also, it will be a hit on the database server also. So you would want database server to evaluate that condition, and out of 10 million, give only 2 million records, because those are for the metro cities. But how do you validate it? How do you know whether database is really doing this or not? Maybe database is sending you all 10 million, and Spark layer is doing the filtering, or database is really filtering at a database layer, which we want. So how do you validate that? So what you should do is, I will cover that in details also, but what you should do is type df.explain after reading it. Sorry, after you or before read, you say, once you create, actually you can do it here only. Once you create all this data frame and then say JDBC df.explain. Once you explain it, there will be a push down. You search for push down in that. If push down is equal to true, that means the database is doing what it is supposed to be doing. It's filtering those at the database server level only. If push down is false, then you have a problem. Then you have to figure out why the database is not filtering that. And I'll explain one example from my experience when it happened and how did we fix it. I will explain that. But having said it, I'll be covering this in much more details with examples in coming sessions. So we had this, if you know, one of the things you should do is you should go and look at the documentation, Spark documentation. I tend to refer that very often. So if you go to Spark documentation, I will open that right here. So if you, so if you go to Spark documentation, you say Spark JDBC, it will show you the first page is documentation itself. So if you go here, so there is another option is Spark policy to write a query. So either you can give all of this DB table and all other things, or you can just give a SQL query like this person has given, select C1, C2 from table T1, correct? So this is another syntax you can give, URL and query. You don't have to give the things which have specified here, the URL, so the table and all those things, because this table is already part of your query itself. Now, once what we were doing was, we did not realize we were using this query option. And when we gave this query, we said select C1, C2 from table T1, and we said where, city equal to Bangalore, for example. Now, when we gave query like this, and we checked, we printed the plan. And again, I'm reiterating, how do you print the plan? You print the plan by putting in a DataFrame.explain. So you say df.explain, it will print the plan for you. So once you print JDBC df.explain, it print the plan. So in that, when we printed that plan, we realized that predicate pushdown is coming as false. And we're wondering why that is coming as false. And then later we realized that instead of giving the, the where condition in this query itself, we could use a filter, dot filter option of the data frame that triggered the, that created the proper plan and enabled the predicate pushdown to happen on the database server itself. So these are some of the experience in the examples which I have come across from experiences, but it's always nice to not only while reading from JDBC, anything you do when you're joining, I will cover the joins also later. When you're doing some heavy operations using data frame, it's always nice, in your dev or QA environment to print the plan and see it, Spark is doing what you think it is doing in terms of optimization. And we'll have, some good number of slides covering that later. Does it give the execution plan for that query? Yes, and we'll cover the planning, Sahil later in detail. I have good number of examples for those. So this is about JDBC. Dataset, just reiterating it, it provides the benefit of RDD with the benefit of Spark SQL engine. It's the same thing. It came in 2016. So data frame is dataset of row and dataset is of type certain object. This is again, if you are just, here I have not given any schema. I have told that whatever is in the CSV file, I have some CSV file called data.txt. Whatever is that CSV file, just put that as one string. Then this is the way you do it. Say spark.read.text file, and it comes as a data set of string, and the column name is just value. So all the columns come under one value. I will show you further. If I want to have the proper schema also for this, I could do that. But if you want, in certain scenarios, I want all the records to come as, all the columns to come as just one, just one column in the data frame. So if you want, then this is the way. Some of the things, you can go and, read from here. Spark, there are two syntax, spark.read.text and spark.read.text file. Spark.read.text will return you data set of row, and it have proper columns and everything. If you do spark.read.text file, it will return you data set of string. All the columns, full record as one column called value. You can go and read about this in detail. So I keep referring to, these APIs quite often. The difference between dataset, data frame, and RDD. So RDD, basically you should, as I said, you should try to avoid. And what we'll do, some of it we'll do today, and some of we'll do the next session is we will go through some RDD functions, and RDD provide rich set of functions. If you have to use those functions, then go with RDD. And when I say you have to, because there is no other alternative, of those function in data set or data frame. So if that's the case, then use RDD, otherwise avoid. So it's all distributed. For processing, it uses MapReduce, it uses dispute collection data into named column. We covered all of this, correct? Data set will cover the encoders. How does data set make sure that one record in the file maps to one object of a class? So that that is done through encoders, and we'll see example of that also later. All are immutable, all are fault tolerant, all are lazily evaluated, and all do the transformation action. Only thing is, you will get more optimizing. Spark optimizer work best on the data frame. There are small examples here. From when RDD is converted, you can convert an RDD to data frame, but then you cannot generate a RDD from the then RDD cannot be regenerated. So once you have the RDD to data frame and then you want to regenerate the RDD, that's not possible. Now it's in the data frame itself. So all have transformation action. We covered that. RDD doesn't have compile time safety. It has excess of unknown columns in data frame. Does not show compile time error. If you want compile time safety, you use dataset. And someone replied, to some extent on this, that why Python doesn't have dataset. This is the reason. Someone replied it already. The access to, so basically what this is, what does this mean? Access to unknown column in data frame does not show compile time error. So when you're using a data frame, right? Data frame is nothing but data set of type row. And you might have some operation on that data frame. And on that operation, you might be referring some column which does not exist. And you will not get this error during compile time. If you do that, you will not get this error during compile time. If you use data set during compile time while writing the code itself, you will see that error. This is type safe. Whatever I just explained is type safe. And when you get an error during the compile time, sort of considers it type safe. If you get error during runtime, considers it untype safe. RDD is available in all these languages. Dataset is available in Scala and Java, and not in Python and R. This cannot take advantage of Spark optimization like Catalyst optimizer and Tungsten optimizer engine. It's RDDs don't interfere the schema. We need to use it. We have to specify this. You have to specify it here also, but here you have some option like if you read CSV file, you can give header equal to true. It will know that at least the column names or something like this. So this is what it is. I explained this. A syntax error you will get in data frame and data set in compile time. Analysis errors. If you use data set, you will get at compile time. If you use data frame, you will get it at runtime. I'll put these questions in the quiz, so you can refer this from the quiz. So I will not ask about I will not ask these questions now. There is one thing I always used to get confused between map and flat map. It's flat map, not flat map, sorry. I always used to get confused between map and flat map operations of Scala. This is very specific to Scala. It is not related to Spark or anything. So I just wanted to, I was thinking maybe there are more people like me who would be getting confused. So I wanted to write something to clearly distinguish what's the difference between map and flat map. So if you have a list, let's say 1, 2, 3, 4, 5, and you are doing, there's some function you have created. If element is greater than 2, then return sum of that element, else none. This is Scala syntax. And I use this map and pass this function in this map, right? I run a map over this. This is not a Spark map. This is just a plain Scala map outside Spark. So when I run this function for each element of the list, like 1, 2, 3, 4, 5 are the elements of this list. For each element of the list, it goes to this function. So then what I get is, I get list of none, because I have greater than 2. 1 and 2 are, it will return none. Then I get sum 3, 4, 5. But if I use flat map, it will just give me, 3, 4, 5. It will remove none and sum and everything. It will give me 3, 4, 5. Now, how do you execute a program? I think someone asked me the ID thing. So Dhruv, thanks for putting that link. Someone asked the ID, how do you create a Spark program? So Scala shell is fine for debugging and everything, for testing, but ultimately you have to put your Spark program in a, you have to develop your Spark program in some IDE. So what I would recommend is, if you are using Scala, then download IntelliJ, Scala or Java, you download IntelliJ, and will maybe possibly in the next session, will set up your IntelliJ to run Spark session. And I will give you, the setup instructions. Maybe I will share that in the assignment, possibly if I can. So use those to set up your IntelliJ to create a Spark project and write some lines of code there and be able to debug. So we'll see that possibly live in the next session. But you have some, let's say you have written a Spark program in Scala or in PySpark also, for that matter. Now you packaged it and it's a jar file for you. So I've created some jar file. Don't go by the name of this Spark Scala or something. This is the jar file of my application. This is just a path, but consider this a jar file of my application. Then how do I submit my Spark job? The way I submit Spark job is I use a Spark submit. By the way, let me go through this, all of this. If you're creating a Spark package if you're writing the Spark code in Scala, then you will be using, most likely you'll be using SBT. And SBT comes, it's a build tool, Scala build tool. Because you're writing in Scala, so you can, once you have written your code, and you can compile in and package that code using this command, SBT clean package. Once you do SB clean package, it will create a jar file for you. Once it creates a jar file for you, this will be your jar file. There's some name, whatever name of your project is, based on that will create a jar file. In your code, what you got compiled and packaged in your code, you will have some main method, right? Because if you have ever worked on Java or Scala, the entry point is always main method, and it's same in many programming language also, like so main method is well known if you are a developer. So you have to give your class, when in Spark submit -FN class, and you have to give your main class method, sorry, main class name, not method, main class name. That will be basically, this is your driver class name, honestly. So so you, once you package it, you say Spark submit, then say, tell Spark that this is my main class, which is nothing but your driver class, and this class and other related application code exists in this jar. And then what I try to do is I have tried to put some data into this directory, and then forget about this line and this line. I was trying to do something and I did not complete that, so forget about these two lines. Focus on this and this. So once you do Spark submit, if your bin Spark bin folder in your class path, if you're doing it on local or on server, if it's in class path, then you can just say Spark submit, or you go to that folder where that Spark base folder and type this command, Spark submit. Give the main class, give the master. I think we discussed the master earlier, whether it is yarn or local or something. So we have discussed that. We have discussed the deploy mode. On yarn you can run in client mode or cluster mode. You could give that. You can pass a Spark configuration. This is very important. Spark provides you a hell lot of configurations, and there is one page from the Spark documentation which has all the configuration defined. We'll cover some of the important configurations in coming session. I can give you some example. One configuration is driver memory, the number of executors, executor memory, executor cores. So things like this you could give in the configuration. And based upon that, Spark will spin up the the executors and tasks and set those executors. And of course, you have to give your application jar, which you are giving this. Additionally, if your main method is accepting some parameters, the command line parameters, so then you could give those also here. So this is the Spark submit job. This is a Spark submit command. I will take 5 more minutes to cover this. Then I will stop and go to the questions. One important thing to realize is that each action is a job. So we discussed about Spark transformation and action. So each action is a job. If you go to the Spark UI, and I have an example of that also later. If you go to the Spark UI, you will see that you submitted one job sorry, you submitted one application through Spark Submit, but you will see two jobs there on the UI. Those two jobs are there because you have two actions in your application. One might be collect, second might be save, or one might be saving to a file, second might be saving to a database. For that matter, whatever action you have, these are just example of actions. So whatever actions you will have, those will appear as one job on the Spark. So this is the in layman terms. If you go to the Spark documentation, what Spark documentation say about job is, a job is a parallel computation consisting of multiple tasks that get spawned in response to a Spark action, save, collect. You will see this term used in driver logs. So basically what it is saying in reality is that if you have any action, then that action is a job, and that job will trigger multiple tasks. Those tasks will run inside the executor and everything. It did not say that, but that's what it will happen. So it will spin up the task which will run inside the executors. We'll go through this example, and then we'll go to the question answer session. Let's say you load a file with people names and addresses into RDD1. So I have given RDD example, but similar thing will for data frame also. Load another file with people names and fonts in RDD2. So it has name and address, it has name and fonts in RDD2. I'm joining RDD1 and RDD2 by name to get RDD3. So these name is common, so I'm joining it to get RDD3. Now I'm mapping the RDD3 to split phone number into area code, phone number for each person as RDD4. So over this joint data set, I'm applying some map operation. Right? Forget this splitting and all this. Assume some map operation is being applied. The RDD4, I'm saving it to a file. Now what I do is, I have this RDD1 still with me. So I apply a map operation over this RDD1 to extract zip code from the addresses to get RDD5. So in RDD5, we'll have the zip codes which are extracted from RDD1. Now I will aggregate on RDD5 to count of how many people live in each zip code. I'll get as RDD6. I will collect on RDD6 and print this stats to std out. So you don't have to understand the logic of this. Only thing you need to worry about is I'm loading a file, joining, mapping, and then saving, and then mapping, and then aggregating and collecting. So all of these steps will be part of, you'll be writing in your driver program. Now step 5 here, because you're saving to a file, it's a job. And in step 8, you're collecting is, so why step 5 is a job? Because it's an action. Step 8 is also a job because it's another action. There are only 2 actions here, 5 and 8. So these are actions and no transformation. What are others? You are loading it, you are joining it, mapping it. These are all transformations. A job is sequence of one or more stages. And what are those stages? We'll talk about that later. What are stages? We'll talk about that later. A task is a particular piece of data that will go through a given stage on a given executor. If you remember the first diagram which I showed you, that an executor can have one or more tasks. So in reality, that's what it is saying. Now, what is a stage? I will cover in detail later, but I will give you one example, a high-level overview of what stage is. When you're loading a file, so here we joined, for example, right? I'm loaded, one file here, second file here. I did a join. When you are joining 2 big data sets, first data set has data stored on n number of nodes. Second data set has data stored on x number of nodes. When you're joining, the movement of data from these nodes will happen so that data from the same join key can come to the same node. Let's say I'm joining based upon people name. Then for RDD1, some person's name in on node 1 and node 2. For RDD2, same person name is on node 5 and node 6. But when joining, for the joint data set, data from node 1 and node 2 for RDD1 and node 5 and node 6 from RDD2 should come to one common node. So that's called shuffle. So data is moving from one node to other set of nodes. So the moment that shuffle happens, that means a new stage is getting created. One shuffle means one extra stage. So that's what stage means. So at the minimum, you will have one stage in your any Spark program if there's no shuffling at all involved. So you will have at least one stage, and the tasks are running inside the state. There are executors running inside the state and tasks are running inside that executor. That's what this line is trying to say. Let me see what else is left. This I explained. We'll cover shuffle in details later. Then we'll cover the RDD and some common functions on RDD and everything. So I'll stop it here and let's move on to the question answer session. Sure. Okay, so today what we are going to discuss is, let me put this in presentation mode. Give me a second. We will be discussing, shuffle, partition, and couple of ways to improve the performance of a Spark job. So I am sure you would have, if you are doing the work either every week or whenever you get time, you're reading about Spark. You might have heard about, you might have read or heard about shuffle, already, and you might have some idea about shuffle also. So, but we'll start from scratch. What is shuffle and why it happens, and what is the consequence of this? So shuffle occurs when data is rearranged between partitions. So I'll keep iterating one point. Partition in Spark means one partition in Spark means one task. In Spark, task and partitions are having one-on-one relationship. And task is part of an executor. Task runs inside an executor. So one executor can have one or more than one task. An executor itself runs inside a worker node. One worker node can have one or more than one executor. So keep that picture in your mental mind, so that when we talk about partitions, that it's inside one executor there is one task, and that task is related to one partition. So when data moves across partitions, then it is called shuffle. It happens when transformation is required from other partitions. For example, you are summing some value using a group by, or I have some other functions which you use, which will for sure trigger some shuffle. So you have 10 partitions, you are grouping by, let's say some city, and you are, and summing up the value. And let's say city has there are only 3 distinct cities. So the data from all these 10 partitions will cross, will move over the network from these partitions to some other set of partition. So that will involve, that is a shuffle. So this is what I just explained. Spark will gather data from each partition and combine into a new partition. It's likely to be in different executor. Shuffle is a performance bottleneck because processing is halted as data is transferred or returned to the disk. So when data is getting moved across the network, Spark knows that data is still getting moved. So Spark can't do the processing because data is still getting moved to wherever the data should go to, and Spark waits for that, and that deteriorates the performance. We should try to reduce the shuffle. We should try, if possible, we should not have any shuffle. But in practical world, in production systems, it's not possible sometimes. So you should try to reduce the number of shuffles if you can, or you can try to reduce the data which is being shuffled. And there are some techniques which we'll discuss over the course of these sessions. This is just one pictorial representation of this shuffle. So what this shuffle does is, let's say you are reading, just give me a second, I want to open the chat in case someone is asking the question. So what this, let's say you are reading that you have read this data from some, text file or database or wherever you read it from Parquet or wherever you read it from. But the point is now data is in Spark partitions. And you write this data, you as part of your business processing, you repartition your data and something, and then you write it. So the data which was in this partition, in these partitions, some portion of this data from all these partitions is in one partition while writing, in different partition while writing. So these are the different storage, different way the data has been written. So the point here is that in each of these block, if you're talking about HDFS, while writing the data from multiple partitions, ended up going into one block of HDFS, just to help us understand. And when you're reading it, so you want to read it back into the similar partitions. So you will again, when you read it, then the data will, when you read it, you will read all of these partition executors into the memory. And now you want similar partition to be there. So you will repartition or apply some function, which will end up, shuffling the data. So data from each of these executors will go into different executors. Then is how the shuffle get cast. So in when you look at the UI, Spark UI, so one of the things you should do is, as an homework, let me write it there, is so that I also don't forget. So homework is look at Spark UI, and we'll have big session of Spark UI also later. So when you look at the Spark UI, and you can look at the Spark UI even if you are running in a Spark shell also. So run the Spark shell. When you run the Spark shell, it will show you while starting up the Spark shell itself that this is the URL. And once you see this URL, it will tell you the Spark UI URL, and it will show you that URL. You can copy paste that URL into the browser, and it will show you the UI, Spark UI. And if you run some processing, if you write some line of code over the Spark shell itself, which triggers shuffle, like we have discussed one in the last session, where we're reading RDDs and joining RDDs and all those things, right? So they were triggering the shuffle. So if you execute that on Spark shell and refresh your UI, you will be seeing something like this. So this is stage 0. So shuffle means a new stage. So if you have 2 stages, that means 2 shuffles have happened, or more than 1 shuffle has happened for sure. Correct? So shuffle causes a new stage, of course. The total number of tasks of your Spark job will be the sum of each stage. How many stages you have? Like you have 3 stages here, and the number of partitions in each stage. As I said, right, one partition is one task. One task is one partition, and so you have 3 stages, and each stage you have let's say 3 partitions. So it becomes total number of tasks will become 9. If you have 4 stages, in first stage you have 2 partition, in second stage you have 3 partition, in third stage you have 3, and in stage 4. So 4 plus 4, 8 plus 6 becomes 14. 14 becomes your total tasks. And we'll go into this, and this, when you see, sometimes if you're lucky and if you're able to design your job where you see only this column, this can have many rectangles here, but you will see this column, that means you have only 1 stage, that means no shuffle has happened at all. But if you see more columns, that means these are all result of shuffles. We'll come to the, I will write these questions in the quiz, so you can take that quiz offline. What we're going to do now is today and in coming session is we're going to spend some time on understanding some RDD functions. We will spend some time understanding the data frame functions. While we do that, keep in mind that we should avoid using RDDs, because the catalyst optimizer doesn't work, doesn't work on RDDs. We should try using data frames only, data frames or data sets. But sometimes you have to use RDD. You can't avoid using RDD. It depends from business cases to business cases. So if you have to use RDD, you should be aware of what are the functions you have in RDD. So because we are going to the Spark course together for the first time, so we'll go, just for the sake of completion, we'll spend some time going over the RDD functions. It might so happen that you will not be using much of it in your when you write your Spark code. But if you know these functions and you might have ended up creating RDD, then you will know what are the tools for RDD. In terms of tools, when I say RDD tools, I mean RDD functions you have at your disposal if you have to deal with RDD. I think we discussed map and filter already. It's just a repetition, and I will just explain this example which I have written here. So we all know what is transformation action, right? Transformations are some business processing you are doing over your data, whether it is map, doing some calculation, filtering, doing some massaging of the data. An action is, let's say you're saving into file, you're displaying some records, you're saving into database and things like this. So that becomes actions. Transformations are lazily evaluated. Unless an action is there, transform won't get executed. Any transformation will not get executed. The moment you have an action, once that action starts, then it will start transformation from the beginning, and at the end, action will get triggered. The transformation, there are many transformations, but I will give you example of map and filter. So map takes a functions, apply this function on RDD because we are discussing about RDD. And by the way, the same thing exists for data frame and dataset also. It applies to each element in RDD. And the result of function becomes a new value of each element in resulting RDD. So let's see how it works. So let's say I have an array and I parallelize, I create an RDD. So this is all on Spark shell. I have written this code. So you create an RDD of this array. Now what I do is I say over this RDD, invoke the map function. And what is going to happen in the map function? What is this n? What Spark will do is this is an each element of this RDD, each element of this RDD. In this case, it happens to be an integer. So each element of this RDD will be passed as a parameter. So first time it will pass 2. And what we are telling, what to do with this 2, I'm saying, we are saying 2 plus 2 multiplied by 2. We're just squaring it up. So it becomes 4. So then Spark will take another element of this RDD, pass to the same function, it becomes 16. Then 36 and 64 and 100. That's how it works. So on each element, it works. So that's how map works. Now, one thing to note is, I think I asked this in the quiz also, and I'm just reiterating here is, we are modifying this RDD. This is an initial RDD. You do any transformation of this RDD, you will never be able to modify this initial RDD. Anything you do over this RDD, it will end up creating a new RDD. Same thing happens with data frame and dataset also, because those are immutable. So once you create it, then you can't modify it. It just anything you do, it will end up creating the new RDD or data frame dataset. Filter, I will explain. I think you know filter already, but I will explain it again. I think I had some file where I had, let's assume this is a file. It has many lines, and it has names of the people in each line. And what I wanted to do was, I wanted to get only the line where my name appears, for example. So I read this file, I applied the filter, and each line is getting passed as a filter function like in map. So in this also, in an RDD filter, you are passing each line of the file as a parameter. And then what I'm doing is this should return a Boolean because it's a filter function. So this should return a Boolean. And then here I'm checking if line contains RDD. If it becomes true, then that becomes part of the new RDD, which is data. Then I'm collecting the data. Collect is another action. So I'm collecting the data, and it prints only the line where my name appears. So in RDD, there is no versioning mechanism. It is just that anything you do over the initial RDD, it will end up creating a new RDD at all. Right? So you will have, if you are doing 3 transformation, let's say you read the RDD, first RDD, which is this. Here I'm doing 1 transformation, it becomes an RDD. If I do another transformation, it becomes 3rd RDD. If I do another transformation, it will become 4 RDD, 4th RDD. So likewise, I'll have all the 4 RDDs. So any RDD you cannot modify at all. It's just immutable. So this is what I explained. Like this is the line I had, and I just wanted to check where my name is there. So this is just a sample data. This is again a reiteration of that. I just copy pasted one example multiple times. Now you read about map. Now what is map partition? So map partition is a function which we use to improve the performance. And I will explain with an example. Let's say you are writing and it is just one example, but you can use map partition for any relevant business logic you might have. So the example goes like this. Let's say I'm getting some input data, and that input data has let's say the currency in dollar, and my Spark processing is I want to convert that dollar into let's say Indian rupees, and one line which has many columns, and one of the column is dollar, and I want to convert that dollar, and I have to process that line, and I have to take all the columns in that line. But only the extra thing I'll be doing is I'll be adding a new column, and that new column will be like current amount in rupees. And what that Spark processing will do is it will take the amount in dollars, apply the conversion of to rupees, and then save that as a new column to that record. And it will keep doing the same thing with every record. Now to do this, I have to find the conversion rates from somewhere. Let's assume for our business use case that because that every day the conversion rate from dollar to rupees changes. So let's say that information is stored in some MySQL table or any RDBMS or any file or any third-party system. Ideally, it is stored somewhere outside. Now Spark needs to connect to RDBMS system, for example, and it has to connect to RDBMS system and run a select query over that table which has this conversion. Now let's take an example. I have this file which contains 1 million records. 1 million is 10 lakhs, by the way. So 1 million 10 lakhs records are there in that file. Now, and let's say I have 100 partitions. So 10 lakhs divided by 100, it becomes 10,000 records in each of these 100 partitions. Just to keep our calculation simple, let's make that assumption that you have 100 partition and 10,000 records in each partition. Now, one way you could do was, you could fetch in your driver code the MySQL. You can select the query. You can connect to MySQL, fetch the record of that record has dollar to Indian rupee conversion rate, and you can broadcast it. That could be one way. But let's say your business problem is such that you cannot use that in broadcast variable, for whatever reason. Let's not discuss that reason because I want to explain the map partition. What you have to do as part of your business processing is that when your Spark job is running and data is partitioned over these 100 partitions, you have to go to the database from each partition and get that value, the reference value, in this case, dollar to rupee conversion from the database. Now you have 1 million record. So ideally, and these 1 million records are spread over 100 partitions. So you will be connecting to the database 1 million times, because for each record you have to get the value, the rate. That's how your business logic is. But then connecting to database 1 million times is not right. What you could do is you could give me a second, I'm getting called. What you could do is you could connect to database once for each partition. You have 100 partitions, so you can connect once for one partitions. So you will be connecting 100 times to database. Instead of connecting 1 million or 10 lakh times, you will connect to database 100 times, one for each partition. If you want to do that, then you have to use map partition. So I'll just read it out loud just so that everyone understands it. So it is similar to map, but runs separately on each partition. It is used for use cases like create connection to DB only once per partition. Without map partition, DB connection for each row might be needed. The example which I gave, right? There are 1 million rows, so you will be connecting 1 million times. But with map partition, 1 DB connection per partition is needed. And so once you get this data, you can save in your map partition function all the rows in that map partition. You can use it. It does not require shuffling, as partition as a whole stored on a node, and we'll discuss about partition in the coming slide today itself. One partition in Spark never crosses a boundary of a node. It is stored on one node only. So whatever operations you are doing over that partition, it gets executed on that node itself. So it does not cause any shuffle. Once you write the map partition function, the input to that will be an iterator. It has certain input parameters, and one of the parameters will be an iterator. That iterator will have all the records which are there in that partitions. So the example which I gave, there are 100 partition, 10,000 record in one partition. So when you apply map partition function, when that map partition function is running on partition 1, for example, it will have the iterator which will contain 10,000 records on partition 1. If the map partition function is running on let's say partition 2, then the iterator of that will have 10,000 records from partition 2 itself, and so on with the rest of the partitions. Now the output also, because you have to process, there are 10,000 partitions, you are processing each record one by one, and you'll be outputting possibly 10,000 itself. More often than not, it's not necessary you get 10,000 input, you return 10,000 output. You can skip some records also, but more often than not, you'll be returning the 10,000 output also. So iterator, the output will also be an iterator, which will contain your output, which is the output of your logic, which you have put in your map partition. So now question is, there's one question which got asked by Dhruv is, if I do not have to connect to a DB, I am fetching data from data lake, then it is fine not to use map partition. Yes, then it is fine to not use map partition. But when you are connecting to a database, you think about the business scenario. If there is one function, there is some functionality which does not change from record to record, it is same for all the records, then maybe you do that once in your map partition. If it changes from record to record, yes, then you have to do record by record. But if it is if you want to get it done once, then use map partition. Another question is, can we use connection pooling, or that doesn't make sense? Of course, anytime you want to connect to database, you have to use connection pooling, but that that is tangential to what I'm trying to explain, right? When you connect to database once in map partition, at that time itself, you will be using connection pooling anyway. Okay. This is one small example of map partition I have written, just to explain how that map partition will work. So I have, I am parallelizing integer 1 to 9, and I have said this 3 means number of partitions I am telling. So integer 1 to 3 will be in one partition, integer 4, 5, 6 will be in second partition, integer 7, 8, 9 will be in third partition. Then what I'm doing is I'm saying this, I'm applying map partition. Now imagine there are 3 partitions. So this function map partition is running parallelly on each of these nodes at the same time. And on the first node, this iterator will contain 1, 2, 3. On the second node, this iterator will contain 4, 5, 6. On third node, this iterator will contain 7, 8, 9. And what I'm doing with that iterator is I'm saying just multiply it. Now remember one thing which I'm doing here. I'm saying iterator.map. I'm not going over all the records, 1, 2, 3. I'm going over the first record itself. No, sorry, I'm going over all the records, my mistake. So I'm going over all the records here, and I'm just printing the output. So, in 1, 2, 3, it becomes 1 for 9. In second node, it will become 16, 25, 36. And so with third node, 49, 64, 81. This is one example. I think I have another example of map partitions, which explains it in a better way. Let's see. I think it's here only. You could try this at home. Let this be a homework. You could try this at home in your week. So what I do is I take only the first element for each partition, and and I just say collect it. So it should print 1, 4, and 7. So try this out, because on each node, 3 partitions are there, which means there are 3 tasks on each. And for simplicity, by the way, I'm saying one task is on one node, just to help us understand. But it is not necessarily that one task, one node will have only one task. One node can have 2 tasks, or 2 partitions are also running. But just for our discussion's sake, I'm saying let's assume that one node has 1 partition and 1 task running. And now we'll going over some RDD functions, and I will be explaining those. What I would request you to do is, whatever an assignment I will create in Azure, you do that, but try your hands on this also. See, when you see something and you just read something, you will forget, and it will not click in your mind for it will not stay in your mind for a long time. And while reading itself, you might miss some things, at least when you are dealing with programmings. So I will encourage you to write this yourself, this distinct function yourself, in addition to the assignment. Just go through these PPTs. You have the PPT in the Google Drive, and write this yourself. So distinct is basically, you all know, if some people have worked on SQL, you all know what distinct is. Basically, it is do duplication at the end of the day. So I have this SK repeated twice, and I think CD repeated twice, and things like this. So I create an RDD out of it, Then over this RDD, I do a distinct. So now see, keep seeing this. This RDD one dot distinct ends up creating a new RDD. So I print in, I get this data from this new RDD, and you'll see this, the unique values are coming here. So that's RDD distinct. The question is, whenever the parallelize function execute, does it mean it's, yeah, this is the parallel function. See, this generally used for, your testing or something. In production, I have not seen people using parallelize much, because data in production, you need data from your Parquet file or ORC file, whether it is on HDFS or S3 or blob storage. But yes, when I parallelize, then it creates an RDD. Now RDD union, it's like SQL union. You have, two relations and you unionize, it becomes one relation. Same thing with RDD. I have this first RDD consisting of these integers 1 to 5, second RDD consisting of 7 to 9. Then I apply union, first RDD union, second RDD, and I get data for all of this RDDs together. That becomes my final RDD. Here also you will see any operation over any RDD ends up creating a new RDD. RDD intersection, it is common finding the common elements in both RDD. It removes a duplicate. But because you're doing intersection, so there might be some shuffling involved. So it has impact on the performance. So first RDD is between 1 to 9. Second RDD is only even numbers, 2, 4, 6, 8, 10. When I try to get a first RDD intersection, second RDD, I am getting only whatever is common, like 2, 4, 6, 8, 10 is not here, so I won't get 10. So this is what I get for intersection. Cartesian, sorry, this is not printed properly, but idea is that I apply Cartesian over this. Cartesian, this I say first RDD, Cartesian second RDD, and it gives me the another RDD, and that will be of type int in this case, because I have one element. If I do Cartesian of first RDD and second RDD, it's like SQL Cartesian. This first element will be joined with all the elements here. This element will be joined with all the elements here. This element will be joined with all the elements here. That's how Cartesian works, and that is what you are seeing here. Now we'll discuss partitions. This is an important topic. If you get mastery over partitions, and next will be data set and data frame, you get mastery on this, and you need not be master, you get a grip on this, partitions and data frame and data set functions. I think you are good in Spark. You can claim yourself to be good in Spark. So when I will go through these partitions, but what I will encourage you all to do is read about this yourself offline also. Write some programs, read more, and understand and get a good grip on this concept of partitions in Spark. Partitions are created by default without programmer's intervention. If you don't give anything, any information related to partitions while reading the data, for example, the Spark will create some partition for you already. Like we discussed in HDFS, 1 GB file with 128 MB, it will create 4 partition out of the box for you already. You don't have to do anything, it will automatically be created. Same is the case when we read about reading from JDBC, right? There are ways to, see how many partitions can be created, but there will be some partitions will be created for you, even though you might not specify anything. This is what I just said. By default for HDFS, a partition is created for each HDFS block read. There is one-to-one correspondence between partition and how data is laid on HDFS. This is what this point meant actually. But although you might not have control, if you don't give anything, Spark will create partition, but you can repartition the data. There are functions which Spark provides, which allows you to repartition data, and it gives you quite, a lot of flexibility there. You can partition without specifying the column name. You can specify, and just give the number of partitions. You can specify the column name over that partitioning can happen. You can specify the column name and the number of partitions over the partitioning will happen. So these are the options there, which I will explain you in the, in the coming slide. So let's say this is a pictorial view of what just explained. So let's say this is the data in HDFS. So 1, 2, 3, 4 blocks are there, right? This is one big HDFS file, but first block of HDFS file contains this, second block of HDFS file contains this, third contains this, and fourth contains this. When you're reading this, see this first block goes into the one task on one worker. This big rectangle represents one worker node. this small rectangle is outside. This rectangle represents executor. So this and this small, even colored rectangles inside this are representing the partitions or the tasks. As I said, partitions and tasks are same. So you first block goes into this task or this partition. Second block goes into this partition. Third block goes into this on different worker node for sure and in different executor. Fourth goes into different worker node and different executor here. So this is how the data is read into the partitions. Now there is a concept called split size. You don't have to spend much time into this, but I will, this is a formula. I took this from the Spark code, by the way. I went to the Spark code and pasted this formula here. But then this example I gave myself. In reality, what this is trying to say is this, that if your file size is less than your block size, let's say block size is 128 MB. If your file size is less than 128 MB, then what will happen? So it will create a, let's say file size is 60 MB, then it will create partition of 60 MB only. The data in that partition will be for 60 MB. But let's go through this anyway. The split size, if any one of you have come from the MapReduce background, you will understand what split size is. So one split size here in the Spark term, you assume one split size is one partition, right? If it helps to understand. So one partition, which is one split size, is equal to minimum of these two. What is the first one? Default max split size is default to 120 MB. And what is the second one? The second one consists max of this and this. What is first one? Open cost in bytes. Open cost is byte depends upon total bytes divided by default parallelism. And what is default parallelism? Sorry, open cost is bytes. My mistake. Open cost in bytes is this, default to 4 MB. And then maximum of open cost in by 4 MB or bytes per core. What is bytes per core? Total bytes divided by default parallelism. What is default parallelism? It is a number of executor cores multiplied by the number of executor instances. So let's take one example. Let's say you are reading 9 GB file, and you can define this property while while starting the Spark job. During the Spark submit itself, you can say Spark executor core equal to 1, and the number of the num executor also you can specify. And I will there's a link on the Spark website, and if you Google search Spark configurations, that link will be first or second, and it has all the configuration which Spark has. So out of that, these are the two configurations which are mentioned here, executor cores and the executor instances. So its multiplication of that becomes default parallelism. So I have 9 GB file, 1 core per executor and 3 executors. So default parallelism is this, executor cores multiplied by executor instances. The cores are 3 and 1 core per executor, so it becomes 3. Default parallelism becomes 3. Bytes per core, total bytes divided by default parallelism. So total bytes are here 9 GB. So I'm keeping it 10 GB or 9 GB here. I forgot to change it here. 9 GB divided by 3, it becomes 3 GB. Then max, I'm applying this max of this open cost in bytes or bytes per core, and a max of 4 GB and 3 GB is 3 GB is maximum. Then minimum of 128 MB and 3 GB becomes 120 MB. That's how one partition is get decided in Spark. And mostly, we don't have to debug this further. Sometimes we see, only thing when we are applying the performance, when we are looking at the Spark job for performance reasons, we look if there's any variable which can be broadcasted so that joins can be avoided. These are some performance techniques. If you're reading data from, let's say, from data source, whether it's Cassandra or MySQL or Oracle, you check whether the predicate pushdown is happening. And I'll tell you what predicate pushdown is when we come to the performance. But at high level, what it means is that when you're firing a query in a table which has 10 million records, and your query is supposed to return only, let's say, 10,000 records, then the execution of that where condition and filtering should happen at the DB server level itself, so that not all million of records travel over the network. So if that happens, you will see in your plan predicate pushdown is equal to true. And I will show you the output of that plan maybe in next session. I have that in my slides. So these are the things you take care. The idea I explain all of you that, more often than not, you might not need to worry about it. Sometimes when you have some job which is, which you have to debug and, figure out everything, at that time you might need to able to look at it. Generally don't. This is what I explained earlier. Partition in Spark don't span multiple machines. Every node contains one or more partitions. So one node can contain one or more partitions, but one partitions cannot cross the boundary of a node. This I already said, one task per partition is assigned. If you want to know how many partitions you have, you can see this RDD.partition.size. It will tell you this RDD spread over how many partitions. Here I have only few integers, so it is telling only 1 over 1 partitions. But in case you are debugging and you want to check how many partitions this data is spread over, these are the functions you can use. There's a question: if we specify the resources, then what will be the role of yarn? So yarn has to give those resources, right? When your Spark job runs, when your driver starts on an application master, the driver will take these configurations which you have passed and give it to yarn, and yarn will tell you that you are asking for, let's say, I think you're referring to this screen, you're asking for 3 executors and 1 core per executor. So Spark driver is going to take this information to yarn and tell, I want 3 executors, and 1 for core. This becomes simple because I have 3 executor, and each executor should have 1 core. So yarn will be able to tell you on host 1, host 2, host 3, you run 1 executor each. So that's what yarn will end up doing. You can repartition your RDD. Repartition will involve shuffle more often than not, and we'll discuss about that later. The repartition method can be used to either increase or decrease the number of partitions in a data frame. The value, this is an example I'm giving. Let's say you're reading 1 to 10, and I'm just converting to DF and then repartition. By the way, this is available in RDD also. We were discussing RDD function and ended up using DF, but in RDD also you can use repartition and you can specify the number of partitions. And then the same thing, you print RDD.partition.size, you will see the partition size is 2. Repartition, this is what I discussed. Once you have read your data, you can repartition your data into multiple ways. One is you can give 1 or more than 1 column and to repartition. So Spark will repartition your data on the list of these columns. You can pass columns in this way or this way. This is the scalar functionality, but similar thing will exist in Python also. You can tell the number of partitions and the columns together, that these many partitions you create, but based on these columns, this can be 1 or more columns. It need not be more than 1. It can be 1 column also. You can pass this information in 2 ways, as a sequence or the list of columns. Or if you don't have any preference of any column, you just want data to be distributed across more partitions or less partition than what you have, then you can just pass the number of partition without passing the column names. This is what I have tried to do. This is some user info. I created some user ID and first name, last name, email. This one sample data. Another data is user transaction, user ID, the date, the transaction amount, and the city. I've used this in different. I uploaded this, and I read one file, read this user info, get the number of partitions by reading from HDFS also. So I uploaded this to HDFS. You can see the HDFS here. I read this, and then I checked the number of partitions. It came out as 1. Now, internally, when you repartition data, right, depending upon the type of data it has, Spark will decide whether to use hash partitioner or whether to use, there are 3 partitions. One is hash partitioner, there's range, second is range partitioner, and third is custom partitioner, which you can build on your own. So, I was looking at the Spark code last week, and I realized that, when you call each of these functions, internally Spark is trying to figure out which partitioner to invoke, whether hash partitioner should be invoked or whether range partitioner should be invoked, and things like this. And if you're interested, you can go to the Spark, Spark code is available on GitHub. It's written in Scala. You can check out on your local, open in your ID and go through the Spark code yourself. It's all open source. So another thing is, the hash partitioner. So I'm just trying to explain what is hash partitioner is. Hash partitioner is, if you want to use hash partitioner, you should have a pair RDDs. So if you have pair IDs, then over the pair RDD, how hash partitioner works is it will create the hash of the key first. And then it will have the, you have given the number of partitions, for example, right? So it will divide that hash code by number of partition, and whatever remainder you get, that becomes your partition number. If you have used the modulo functions a lot, you will understand what this is. I'll explain with an example. Let's say you want only 3 partitions. Now, any number in the world you divide by 3, your remainder will be between 1, 2, and 3 only. You cannot have remainder more than 3. Let's say your remainder is 4, then you divide it by 3 again, it becomes 1. So any number you are dividing by 3, for example, will get a remainder either 0, 1, or 2. Right? So because I have specified number of partition as 3, so whosoever hash keys are remainder by 3 is coming as 0, those go to 1 partition. Whosoever hash keys remainder, when I say remainder, whosoever hash code value divided by 3 has a remainder as 1, those go to partition 1. I have 3 partitions, 0, 1, and 2, and I have values. Hash key can give any value. I have millions of records, and each of those records, it's a pair RDD, it's just key and value. So I create a hash of the key and divide it by 3 for the first record, and let's say remainder came as 2, so it goes to partition 2. I took the second record, create the hash of the key, divide it by 3, remainder came as 0, it goes to the 0 partition, first partition, which is 0, and so on. Correct? So I have tried to explain that here. So I read this user info table, and I split this info, split that. I should be comma here, not blank, it should be comma. So I split this and take the first element. So what happens here is, I have this user info complete record. I make user1 as the key, and the value is again the complete record itself. For the second record, user2 is the key, and the value is complete record itself. So that's what I end up doing here in my hash partitioner. Where did that go? And then this is the key. So this becomes my key, user1 becomes key, and the complete record is the value itself. And then I partition it by, and I say hash partition, and I give the number 9. So it will partition, it will spread this data into 9 partitions. Now there's a catch here. I'll tell you what that catch is, but with an example later. So read this, I create a pair RDD, and over this pair I say partition by, and say use the hash partitioner to partition by, and these are the number of partitions you should use. It will give me the number of partition as 9. Now each of these 9 partition need not have, there will be some partitions which might be remain empty also, because that's the implementation of hash partitioner. It does not guarantee that data will be there in all the partition it has created. So some partition will remain empty, and some partition will have more than one record, more records than the other partition. So I'll show you an example as well. So he's saying, so the hash key details is stored with the driver. It is stored internally with the Spark program. So when we discuss about the Spark memory, how the Spark memory works, you will know where this information is stored. Again, I think I am trying to use the hash partitioner here, or this is what I just covered. I will try to explain in little detail here, right? So I have given the hash partitioner as 9. Now what I want to do is, so it has created 9 partitions for me here, right? So for each of these partitions, for this RDD, which has 9 partitions, for this RDD, I go for each partition. So here I'm saying for each partition. So it has created 9 partitions. So this will be there. This will be executed for each of the partitions. Then within each partition, I am saying there are whatever number of records you have in that partition, print those records, right? This P for each is, this P is for each partition. If there are 9 partitions, then there will be 9 such P's running parallelly on each of the partitions. And within one partition, there are records, and P for each means is going over the records within each partition. So that's what is happening. So on partition 1, I see these records. Partition 2 is blank. Partition 3, I see these records. Partition 4, I see these records. Partition 5, I see these records, and so on. Right? This is how it is working. Generally, you don't have to deal with creating your own hash partition or something, but it's good to know. You should know this is how it's happening. Why are we saying print.t.toString? You can just say, because here T is string, if it would be an object, I would have said toString. You can just actually print T also, it doesn't matter. T.toString and T is same. There is a function called the persist. The reason I'm mentioning persist here is because we are discussing shuffling and then partitioning. I think in the last session also I went over over how persist will work, but we'll revisit it here. So once you use persist, then Spark will not recalculate that RDD. What do you mean by that? I will just try to follow what I'm trying to say. If you don't follow, just put the message in the chat. So let's say I'm reading data from a database. So that's my RDD1. Then applying filter, it becomes RDD2. Then apply aggregate, it becomes RDD3. And after RDD3, I'm saving that RDD3 to a database. After saving RDD3 to database, I'm applying some more operation over RDD3 and some more aggregates over RDD3, it becomes RDD4. Now I'm saving RDD4 also into a file now. So when I save RDD4 into a file, this is an action. It will trigger everything from RDD1, 2, 3, and 4 again. When I created RDD3 and saved the RDD3 into a database or into a file, that had also triggered RDD1, 2, 3 again. So any action I do further, all will trigger, I'll recalculate RDD1, recalculate RDD2, recalculate RDD3, recalculate RDD4. Any action further on will keep recalculating this thing again and again. So again, I will reiterate. I created an RDD1, apply some transformation, created RDD2, then I created RDD3. I'm saving that RDD3 to the database. The moment I save RDD3 to the database, it will calculate RDD1, RDD2, RDD3, then it will save to database. Now over RDD3, I created some more transformation. I ended up creating RDD4. Now I'm saving that RDD4 to a file. The moment I save RDD4 to a file, it will end up creating RDD1, RDD2, RDD3, and RDD4 again. So if you see RDD1, 2, and 3 are getting created multiple times for each action, which doesn't make sense. So one I can do is I can say RDD3.persist. The moment I say RDD3.persist, then I am saving RDD3. Save it to database. Then it will save RDD3. It will not calculate RDD1, 2, 3. It will calculate once because the first action we are executing. It will create RDD1, 2, 3, and then save 3 into the database. Then I'm applying some transformation of RDD3 and creating RDD4. Now and saving RDD4 to the data to some file or database again. Now RDD4 action will take from RDD3 only. It will not trigger RDD1, 2, 3 because RDD3 was persisted. It will take from RDD3, apply the transformation RDD4, and then save directly into the where RDD4 was getting saved. Okay. So that's the advantage of persistent cache. I will have some more explanation of persistent cache, not in this slide, but in coming session you will see there's a persistent, there's a cache. What's the difference between these two? I have explained it in a different slide. Yeah. So Anshul, your question I already answered. So I'll explain this in different slide. Repartition, you can, and we discussed that. This is one example. Just keep this when you are looking into Spark job for performance, and you will end up spending time you will spend a lot of time in fixing the Spark performance. That's where your majority of the time might get spent. So let's say I have one user table which I've read and a repartition on user ID. Now I'm joining the user on address. Now when I say join and show, now it is it has shuffled. First shuffle is happened for this user table for sure. Now I'm joining this user table again with some other data set. Let's say salary is another data set. Salary just an example I have given. It can be any other data set which can be joined with users. I'm joining user with salary. Now Spark is intelligent enough to know that user has already been shuffled and shuffled, and these are the partitions which has user records after shuffling. So it will skip the shuffle for user at least. It will make the shuffle for salary data, and let the salary data set data will go to the partition where user data is, but user will be shuffled only once. But at least first one shuffle of user will be there because you are joining this. That will be there. Now another thing is repartition. If repeatedly shuffling data on certain keys. Now this is one way to let's say I need to keep joining this user and addresses and users and salaries. So I need to keep doing such things. So this is an improvement, and not many people know it, by the way. So if I'm doing repeated shuffling data on certain keys, then save the data is bucketed table only. So bucketed table is a provision which Spark provides, and I will give an example also. What it will do is it will write the data out already in pre-hash partition. So it will create the save the data in the partition, already partitioned only. So when you read the data back, while reading the data in and join them, you can avoid shuffles. Let's say, take an example. Users I have read, and I'm saving the users data set or RDD or data frame in bucket by, and this is the number of buckets I'm giving, and this is the user, this is the columns over which bucketing is happening. And I'm saving this as and I have to use save as table and give the table name. Address also I'm saying that, this many number of buckets, and the bucket, this is a column over which bucket should be created. And I'm saving this as address table. Now I read it back. This is a user table I saved. I'm reading spark.read.table user. This is the same name I'm giving here. Spark.read.address, I'm giving the same name. Now you're joining user.join.address, and you show there is no shuffling. There is no shuffling involved in this, because these data were read in the pre-partitioned way, and you're joining on the same. And there's a condition to avoid this. It should fulfill this condition to remove shuffling. What is that condition? Table should use the same bucketing. What does it mean by that? The same number of buckets and joining on the same bucket columns. So you should use the bucketing column as same in both of these, and the number of buckets should be same. If you do this and I join these two data sets like I'm joining here, then no shuffling will be involved, and that will be a tremendous performance improvement. Let's spend 2-3 more minutes to discuss the partition types. There's a hash partition, range partition, and custom partition. Hash partition, we discussed it already. Let me skip this. We'll discuss it's already 6:30, so let me stop it here only. I think I don't want to waste more time. We'll discuss this next time, because it will become too much for you also otherwise. So I'll stop it here, and let me pause the recording, and I'll open up for any questions you might have. Just give me a second. So today, I think you might have gone through the video also, and maybe you might have attempted the assignments as well. So we discussed the partitioning, right? So I'll just very brief partitioning, like Spark runs on executor. Each executor has one or more tasks, and each task is a partition. Right? That's how that is obtained. People, please go on mute. I know you are typing. So, now what are these different type of partitioning? There are different partitioning strategies. And if you see the Spark code, when you repartition, Spark decides one of these partition strategy internally anyway. But if you want to have more control over partitioning, you can use this. And I have example of this in a coming slide. So there are 3 types of partitioning. One is hash partitioning, range partitioning, and you can give your own custom partitioning logic also. Now I have written a note that anytime you do partition by, better you persist it, because generally partition by involves shuffling. And if you have more than one action and you don't persist partition by output, then every time shuffling will happen. So you want to avoid it. So what is hash partitioning? It is implemented on hash-based. It implements hash-based partitions, and these hashes are based on Java objects hashcode function. And range part, and I have an example of each of these, by the way. So range partitioning is the partitionings are based on the ranges. Yeah, so please, we'll put the Discord server. Arun has asked to put the Discord server link. Arun, I will put it. Give me a few minutes. At the end of this, I put it. If someone else can put it before, good. Otherwise, I'll put it. So range partitioning, the partitioning, it partition the keys based on the range. So all keys falling in the same range will be in the same partition. It tries to divide into approximately equal size partitions. Each partition contains records with keys within a specified range. Ranges are determined by sampling the content of RDDs, and we'll see an example of that. So range partitioner has some constructor which take quite number of parameters. So these are the parameters which range partitioner has: the number of partitions you want, the RDD which you want to be partitioned, the order of the range, whether you want it in ascending or descending, during range partition. Ordering method of the key, how how the key should be ordered. If you have a class called person, and person has ID, name, salary. So if you want to tell how to order this, so you implement that pass this as your comparator, or as parameter 4. And class tag authority. In this example, class tag authority will be person.class. So these are the parameters to the range partitioner. Generally, I've seen you don't need to worry about this. You just repartition and Spark internally will decide. But in case you want control over this, then this is what it is. So I've given is partitioning example. So if you remember, we had these two files, user transactions and user info. So user info had user transaction and user info both had user ID as the first column. So I am reading the user transaction here, and I'm converting into key pair. So key is the first element, which is the user ID, and the value is the complete record. So the key value is a paired RDD, and you can see it's a paired RDD with string as key and string as value, string type as key and string type as value. What is the key? The first column, which is a user ID, and value is complete record, complete row. Then I don't use all the parameters. I just tell it give me 9 partitions, and for this particular RDD. So it partitions into 9, and for each partition I go and print the partition. And I think Sahil, you were asking question, maybe you can use the same thing. Go to each partition, and for each partition print the content and see. I think you're saying some blank lines are there also, but that's how you can print the partition, the data inside each partition, and that's how you use the range partitioning. You can customize the range partition, and you can do a lot more things. I have not used all the parameters, but if you want as a homework, and maybe I will add as a homework, you can add more parameters there. And you can use all the more than 2 parameters which I've used for range partitioning. Now what I'm doing is I want to write my custom partitioners. And what I want to do in that custom partitioner is I want to have data, for the cities which have vowels in one partition, cities which do not have vowels in another partition, something like this. We'll see. So this is my data set. And what I want to do now is I'm creating my own partitioner. This is Scala code, but in a Python and in a Java, you could, or a Python, Java, and R, you can create yourself also. So I create my whole partitioner. I take these parameters, and then it should extend partitioner. And this is a get partition method. It has to override. And there I'm putting, this is my internal logic here, right? So this is Scala code. If you know Scala, you will understand it. But in reality, what I'm saying is, whatever record I'm getting. So here I'm getting this record, right? Let me go back. I'm getting this record. So 0, 1, 2, 3. These are the columns. 1, 2, 3 for columns. The first column index is 0. Second column index is 1. Then 3, and then 2 and 3. So what I'm doing here is I'm getting the last column, which is the third column, which is a city. And I'm saying if city starts with A, E, I, O, U, or capital A, I, O, U, then what I do is I return 1, else I return 0. Right? So this is my, I want only 2 partitions. So 1 and 0 will work for me in this case. So I use this, then I do the same file, and then I again convert into pair RDD. And here I'm saying, partition by new vowel partitioner, and I pass 2 because I have only 2 partitions. That's why I'm returning 0 and 1. There will be 2. If I pass 3 partitioner, then my, the custom partitioner should have, 0, 1, and 2. So that's how I, write my own partitioner. And then once I partition the data, I go to each partition and see the content there. So you can see in one partition, all the cities, which have non-vowels here, I think, which are not vowels. And here you have the city starting with vowel name A, U, I, and things like this. So this is how you can implement your custom partitioner. To see the partitions used, if you want to see which partitioner I have used, whether it is which partitioner has been used, you have the either you did a partition by or repartition or whatever, and Spark internally has decided to use one of these, and you want to make sure which one has been used. So you can write take the RDD and invoke partitioner method over there, it will print what partitioner has been used here. What determines the partition size? How many partition you should have? What are the factors it determines? The number of cores available, and for that matter, I will say even the memory also. The size of external data sources, how big size you have, and for that matter, even your logicals. So these are the few factors which determines how much how many partitions should be there. There are certain transformations which you do, which always return the partitions RDD. I think we discussed there are different type of RDDs. Partition RDD is one of those. So for example, if you use any of this transformation, join and all GroupByKey and all those things, then it will return you a partition RDD, which means that the data, these transformation do transform, do partition the data, and that's why returning you the partitions RDD. There are certain partition functions, and this comes pretty handy. I gave an assignment on map partitions. Whosoever had attempted had done this, so that was pretty good. The map partition you use when you initialize, when you do some infrastructure work, which needs to be done only once per partition. So if you want to do that, then use map partition. For example, connecting to database and fetching data from database is one such example. So there you can use map. You don't, in one partition, you don't have to do for record by record. You do it once in that partition, and every record will use the output of whatever you have done once. So that's where you use map partition. Map partition with index, it's pretty similar to map partition. It additionally provides an index to tag the partition number. This is one example. If you want to know the index, I don't remember where I used it, but there was one use case where I needed to know the index of the partition, like which partition. If the number of partitions are 50, then you will know in which partition, the code which is running inside the partition through the index number, which partition that is. I think I needed to create some random thing or something so that it is not unique across all the partition. So for that, I ended up getting the partition index and added that to the value which I was getting to create some sort of randomization.
Sandeep, I have a question on map partition.
Mm-hmm.
Can we do grouping inside that or no? Is it logical to do or not inside map partition?
If you want to do grouping, you are saying, I think you are asking whether I can use group by function, correct?
Yes.
I don't think you can use because map partition is over a data frame, correct? So when you have a data frame which consists of 1,000 records, and you have 10 partitions, so 100 records are inside that partition, correct? So once you are inside the map partition, then you are dealing with those 100 records only, and you don't have concept of the data frame once you are inside the map partition. So you can't use group by inside map partition.
Okay, so most of the times we will use map partition just to do some mapping or maybe creating some connections which we want to limit, right?
Correct. Maybe some infrastructure work which you want to do. For example, I want to initialize something. One of the initialization is database connection and firing some query to get master data. Second initialization could be, I know, just hypothetically, I'm throwing some examples here, is connecting to Redshift. Maybe I want to push something to Redshift or pull something from Redshift in my partitions. So things like this.
Okay, thank you.
Sure. So repartitions. So you can repartition. I think we discussed repartition earlier also. You can repartition the data frame or data set. With repartition, you can increase or decrease the partitions. With Coalesce, if you see the implementation of Coalesce, it calls repartition only, but repartition in Spark code has a method called shuffle equal to true or something. So with Coalesce, it just passes it as false. Coalesce reduces the number of partitions. It can't increase the number of partitions. Now, if you want to decrease number of partitions from, let's say, 10 to 4, which one will you use? Whether you will use repartition or Coalesce? You should use Coalesce, and I'll tell you why. Let's say your data is in 10 partition, which is, for simplicity's sake, let's say these are 10 different nodes. Partition 2 partition can be on one node also, but for our discussion, we are taking the example where each partition is on different node. And these are 10 nodes with 10 partitions. Now you want to reduce it to 4. If you do Coalesce, What it is going to do is it is going to take data from the 6 partitions and move it to the rest of the 4 partitions which are already existing, and then create the 4th partition. If you use repartition and say from 10 to reduce to 4, it is going to take data from all of these 10 partitions and move it to some another entirely new 4 new partitions and copy it there. So shuffle will be when you're reducing the number of partitions. If you use repartition, shuffle will be more. If you use coalesce, shuffle will be less. This is an interview question which gets asked very often.
I have a question here. So in an interview, I was asked to give a scenario where coalesce would be used to increase the number of partitions.
And did they ask whether you can use the coalesce to increase the number of partitions, or did they ask you to whether?
I mean, they wanted me to describe a scenario where I can use coalesce to increase the number of partitions. I was open to assume.
You can. I'll tell you how it can happen. I'll tell you. See, as I said, right, coalesce calls repartition only. So if you see the coalesce implementation, let me see after this session, I will open the Spark code and will show you the coalesce implementation. It invokes the repartition with flag shuffle as is equal to false. Now let's say you have, and this is a hypothetical scenario, just validate it what I'm saying, but I think this is how it will work. Let's say you have 10 nodes, and these 10 nodes have 4 cores, and you have executor which is running on 10 nodes, which is taking only 2 cores. When I say 4 cores are available to Spark. It might, in reality, it might have more than 4 cores, but 4 cores you can use as Spark. Now your executor is running, which is using only 2 cores, correct? So effectively, it would mean that you can start 2 more cores. You can start 1 more executor, which can use 2 more cores, correct? So if you want to, if that's a scenario, that's what you have. Like you have 10 executors running on 10 nodes, and each of those nodes having 2 cores free, and whatever executors you are running on 10 cores, those are also using 2 cores only. Then you can possibly increase the, use the coalesce to increase the number of partitions, because coalesce, as I said, it doesn't involve shuffle. So in that case, it might, copy the data from each of these nodes. From, let's say, node 1, it has only 1 executor running. So it might create a new task and copy the data into the new task. So the number of partitions will increase on the same node itself. So it will not, it will not shuffle any data. So same thing is happening on node 2, same thing is happening on node 3, same thing is happening on rest of the nodes. So idea is that if you have hardware available on each of the nodes for extra number of tasks, then this might be possible in theory. Does that make sense?
Sure. Thanks. And also follow-up question on coalesce. So you mentioned that in coalesce, if we have 10 cores, and we are doing a coalesce for 4. So what it will do is it will pick up the data from 6 cores and move it to the remaining 4 cores.
Correct.
Right?
Correct.
So how would it pick those 4 cores where it wants to save the data at the last?
So I think it might not be deterministic. So one thing which Spark does internally is an cost-based optimization. So I'm assuming same cost-based optimization, and we'll talk about cost-based and rule-based optimizations later in our sessions. Not today, in coming sessions. I'm assuming some cost-based rule it might be firing, and actually I will go through this repartition code later. So I'm assuming that it might be finding out if some partition has more records. It will not touch it. The partition which has less record, it might touch it and move it there. But we can go through that code. I have Spark code downloaded on my IntelliJ, so we can go through that. But it might be some optimization might be happening on that front.
Okay, thanks.
Now the operations which are benefited by partitioning. If you partition the data, then there are certain operations which you can, which you can perform better, which you can do better. One is group with, second is co-group, and I think most of the things but we'll discuss many of the things here. Co-group, join, left and right auto joins, group by key. See, anything you have by key, anyway, it will get benefit by partitioning, because data for the same key might exist on the same node. And lookup. There is one, I think that covers our, that covers our partitioning, thing. Let me open IntelliJ, because we will go through certain code later, not right now, towards the end of this session. So let me open that in the meantime parallelly. So now there is something which is called Spark implicits. And this Spark implicits is basically for Scala only. And this is very helpful. And how is that helpful is, I'll explain with an example, then we'll cover these points later. Let's say you have this data set. The delimiter is semicolon here, if you notice. And it has, some ID, name, date of birth, salary, designation, manager ID, address. Now what I do is, I create a, sorry, where did that go? I create a case class with the same schema, ID, name, whatever. Correct? Now I read this. Now one thing, if you see, right, when I'm reading this CSV, I'm passing header true, delimiter this, I'm loading this file. This file is spark.txt, and I'm loading it as info. This info is a case class, and you will get a data set of type info. How did that happen? That happened because the names which are appearing here are the same names which are appearing in the class, case class. And most important thing, I have done a import Spark implicits. If I do not do that, if I do not add this record, then what is going to happen is it's going to give a compilation error here. Your code will not even compile. IntelliJ, if you run on Spark shell, it will throw error. So what this Spark implicit does is it automatically takes this columns, ID column, and put it into the each record becomes for each record it creates an instance of info class and populate the value accordingly. Like ID goes into the ID field of that class, name goes into name field, and so on. And that's how you get the the data set of type info. It's only for Scala. It helps implicitly converting Scala objects to data frame. That's what we saw just now. It implicit object is defined inside Spark session. So inside it is doing that. So now what does that mean is, in your code, if you import the implicits before creating the Spark session, then this won't work. You'll still, on your IntelliJ, you'll still keep seeing that error. So as soon as you create the Spark session, immediately after that, you say import, spark.implicit inside your method itself. In Java, you can't have import inside the method, but in Scala, you can have import inside your methods also. So the moment you create a Spark session, you import the Spark implicit, and then this will automatically happen. It will automatically convert your data set into the case class or whatever class you have, and you'll get data set of that class. So that's why Spark implicits are pretty useful in the Scala code. I think this covers our first module. Any question? I want to jump into the second also to cover a few things.
Hi Sanjay, actually, I have a question. Like, we are creating case class for the columns and then passing the data types. But what if we want to make a generic framework around this Spark, so that we can implement many tables with it, so we don't have to create case class individually for each of the tables. So
this is a good question, Ankit. You complete your question, then I will add my comment to this.
I mean, I want to make a generic function in which I can just pass on the parameters, like pass on.
I got it. I will I'll elaborate your question. Your question is that this schema, this is one data set which has this schema. I met another data set which are different schema altogether.
Yes.
Right? But I want to have only one Spark program which creates, which processes this, right?
Yes.
On certain common logic. This is a very good interview question. I ask this question in all my interviews, but I will let someone answer. In case someone knows the answer, I'll let that answer. Otherwise, I will answer it.
So, as per my expectation, if you don't pass the schema, Spark itself will type inference the data, and it will assign that data types and the column names based on the data what you provided. If you don't have any column names in the data, then it will mark it as $0, $1.
No, but I want to give that. So let me elaborate. I'm asking the interview question which I asked in all my interviews. So, so I'm just reiterating as is here. So let's say I have 5 data sets. Everyone has different schema altogether. No correlation between these 5 data sets at all. Now I want to write one Spark program, and what that program will do is it will take 2 inputs, actually 3 inputs. First input it will take is where is the location of this data, which folder this data exists, which directory exists. Second is some schema information that this data has this schema. This also comes as an input. Third, what I want to do this data, some arithmetic expression. Let's say my expression, all I want to do the Spark job is for all these data sets, I want to create a new column, and that new column is arithmetic expression of some existing columns. For example, for first data set, I can say first data set has column C1, C2, C3, or so let's say salary, income tax, and something. That's these are the columns, few of the columns in the data set, first data set. So my formula will be add a new column which is salary minus income tax divided by 50. Okay, that's my formula. And based on this formula, I want to add a new column for each new column having value for each row. So then I go to the second, I want to process second data set. So I pass the location of the second data set, I pass the schema of the second data set, and I pass formula of data set as second data set. Formula of the second data set might look like multiplication of some 3 columns in the second data set divided by 4th column. But that's a formula. That's my Spark job. That's what my Spark job should process. And similar is the case with rest of the columns. So if you were to design such Spark jobs, how will you do it?
So, Sandeep, is the ideal solution basically in Spark, or we can answer that in PySpark as well?
You can, no, it's in Spark. Use PySpark or Scala Spark or Java Spark, doesn't matter, but it's a Spark question.
Okay. So for that, what we can do is so the path and the formula is very, it's straightforward. We can once we have a data set with us, we can just use with column to generate the required features using that formula. When it comes to schema, we can use struct type and struct field to create the schema object and pass it in the spark.read function while we are reading it.
That's absolutely correct. This is the answer. I think Reshma, you also gave the answer, partially correct, but you forgot to add. Who gave this answer? Was it Arun?
This is Arun here.
Okay. So this is a correct answer. You have to create based on the schema which is passed. Dynamically, you have to create a struct type, struct field, and that becomes your data set row. That's your data frame. And now you pass any schema you want. So it can always create the struct field based on that the data frame. Good answer, man.
So struct we will create before calling that method, right?
Inside your method itself. So once your driver program starts, maybe this is one of the homework I will give you. Once your driver program starts, then you based on the schema. Let's say I'm passing a schema with ID, name, and salary. Right? I'm passing the data type also. ID string, name is string, salary is let's say number. I create struct field and struct type, and inside struct type there can be 3 fields. Yeah, someone pasted that. Sahil pasted that. This is how you do it. And you have the struct type, and inside the struct type, you will, based upon that, you will create a data set of type row, ROW. So here I am showing you the data set of type info, info. But the question which Arun was asking is the one job for multiple schema, you create the struct, and then based upon that, you create a data set of type row, ROW. O is the Spark class. So that way you can write one Spark job for any schema.
Okay, got it.
So, but good question. So now let's move on to the another one.
And
Hi, Sandeep,
one more question.
Yeah, hi, Sandeep.
One more question, then we'll move to another one because we have Q&A session also later. Go ahead.
Oh,
Go ahead.
Yeah. So the question, the struct schema that we have created is like we have we know the predefined field, but I guess the question was like I want to create a generic schema. On that generic schema, I can call, let's say I have a table, 5 tables, okay, and I want to create a class wherein I can pass all those 5 table, and I can get accordingly I will get the data frame.
No, you for create a data frame, you need to know the schema. So somehow you have to find the schema, and it is good that way. Even if you figure out the way, what you are asking, Vishal, I will still not recommend it, because then Spark optimizer will have problem optimizing what you are building. If you give the proper schema, and you can create schema dynamically at runtime, so I don't see any problem there. But if you with that capability and having the proper schema, Spark can optimize your job much better.
So can we create dynamic dynamic schema? For an example, the case class that
Sahil pasted that. That's how you create a dynamic schema.
Okay, fine.
Yeah, Anshul, you were asking something.
Yes, I was asking, like, is there any other place where we will use a Spark implicits?
Mostly you use at this only. I have seen, I have used only at this place. I am not seeing any other example. Basically, Spark implicits are, if you don't have Spark implicit, use an encoder, right? What you are all asking is, it's becoming confusing because Spark is doing this job for you by using implicits. Assume that Spark says, no, there is no more implicits. Then you will be creating an encoder. And I have an example of that also. The moment you create an encoder, you have to create the schema, like Sahil had tested. So you create the schema, put that in encoder, and then create data frame out of it.
Okay, because I remember in some of a project where I was working, there was implicits created by someone already. So that method used to get called automatically. I know it half, but I thought like maybe I can understand it, but means custom implicits, I believe.
I think what you are asking is, in addition to what Spark gives,
yes,
what happened? In addition to what Spark gives, can you create your own implicits?
Yes. And in which scenarios we will create it?
See, what implicit is doing is, in this case, it's trying to, you don't need to create encoders yourself, right? You don't have to define the schema for yourself. So it's trying to save that effort. So anything which Spark can do based on the configuration, see, it is in combination Spark and Scala together. So anything which can be done based on some configuration or based on some standard. Here the standard is at a name or of the same type as here in the schema as here in the class, correct? So anything similar which can be done based upon some standard or some convention or some configuration, there you could create the implicits. I'm anticipating many use cases of implicits based on this, but it depends from your use case to use case.
Okay.
Okay, let's go into I think this covers our module 1. So module 1 and 3 are the biggest one. In total, we'll have, I think, 6 modules. 4 and 5 are pretty small. 3 is biggest. If we cover 2 is small, if we cover 3, then almost we are done with the course. So let's go into the RDDs. We'll cover some RDDs here. In practice, you will not be needing to deal with RDDs. People, can you go on mute, please? You will not be needing to deal with RDDs, yourself. In rare scenarios, when you have the need to deal with RDDs, for example, you need some RDD functionalities, and some of this functionality we'll not talk about here. So if you want to go to low level details and have to deal with the RDD functionalities, then only use RDD. But you should know what are the things, what are the types of RDDs are there, so that in case you need to know, you will be aware. There are many RDDs, by the way. I have captured only few which I thought were of importance. One is double RDD, second is pair RDD, order RDD, sequence file, co-group, shuffle, and new. And we'll go into details of each of these. So what is double RDD? Sorry, let me go back. Double RDD has extra functions which are related to double values. For example, you can create histogram, mean, etc., etc. So just one example, I have this records, and I want to create a mean. I can do this here. Sample variance. I can create because it's double RDD. You see, the RDD is double, so I can say double RDD dot sample variance. It gives the sample variance. I think I have a couple of more examples. The system is a little slow somehow. Stats. So you can come up with the stats. So you can say your the RDD dot stats. So it'll give you count, mean, standard deviation, max, min, and things like this. By the way, if you ever worked in Hive, so if you go to Hive table, what they have done is the Spark. So there is a group Hawaii. They have added a cost-based optimizer in Spark. The way the cost-based optimizer works on Hive base, when Spark is dealing with data sets in Hive, is they have created a command called analyze table name compute statistics. So if you run that over Hive table, that also gives you something similar. It will tell you, it gives you a little more than that. It will tell you what is the size of that table. Like if you're saving in Parquet, what is the size of that table in Parquet format, and Parquet is highly compressed format. And then it will give you what is the raw size also for this. If it were not in Parquet, for not in a normal uncompressed format, then what is that? What is the row count and things like this? That also gives you lot of that information over Hive table. But if you're talking to the double thinking about double RDD, then you can use this in a sample this stat to give you all this information. So is this limited to doubles or any RDD dealing numbers? You can do this. These methods, sample variance, sample standard deviation, or stats are on double RDD only. If you have RDD of some other type and you try to invoke, it won't work, it will give error. And you can see the details of double RDD on this link. All the functions are mentioned here. Okay. Pair RDD, when you need to deal with key value pairs. For example, group by key, many by key, you'll see many by key functions, combined by key, produce by key. So there you use pair ID. The way you create pair ID is like key and value. So I have seen in the you saw in the previous example also, I created a pair ID. I had this RDD lines. Over this lines here, and invoke the map function. And in this map function, I create two values. So incidentally here I'm creating the first column as a key and the complete record as a value. So this becomes my pair RDD. Key as the first column and value as a complete record, including first column also. So this is how you create pair RDD.
Sandeep, like if we had to do the similar function in data frame, so we would use like flat map. Is it? Like
depending upon what data you have, what function you want to do in data frame. If you want to apply some map function, you can just apply simple map function, right?
No. Basically, if for each row we want like two values, like we want to apply two functions on each row, then.
No, I'm just thinking because your data frame of type row, it can have two columns, right? This RDD is only RDD has key value pair. In data frame, there's nothing like key value. Just a data frame is just a tabular structure.
Right.
It's not like, so if you want to have two columns, you for sure in your data frame, when you create the row, one row can first column the row can have key, and second column of the row can have full value.
Okay, so
you can achieve if you want.
Okay. So where do we use like flat map transformation that we have?
Flat map, you have not seen the previous recording. So flat map we use. Let's hold on to that. I will answer.
Okay. Yeah.
Just, type your question in the chat. We'll come to that later. Okay. Ordered RDD. Where the key is sortable, correct? Where we can sort the keys. You can define your own ordering for custom types. So for example, sort by key. So this is an example. So I have created, this list, a paired RDD with the city and some number. Then I sort by key. So it give me, some shuffle RDD. Then I collect it. And then because I've sorted it, so then now it becomes, sorted by the key is the Bengal, so it's sorted by the key, BC in alphabetical order, right? I can sort, this sorted RDD, I can, say filter by range. I want to get from A to G. So any, key which has from A to G that comes outside G, like M, P, H, they don't appear. So this is one function of the ordered RDD. Reduce by key. I think this you must be knowing all by now. So reduce by key is basically, it's again transformation function. And like any other function, like any other transformation, it takes another RDD. It takes, first value as accumulator and second value as, as a value. And I'll have an example of that in coming slide. Now, when you're dealing with, things like, where you have reduced by key, and I think there is one aggregate by key or something. you need to know what is associative property. And I have explained it with example also in later, associative and other properties also. But associative properties says that you can add or multiply regardless of how the numbers are grouped. A group we mean by how you use the parenthesis. So if you say 4 plus 5 in one bracket, then plus 6. So it's a 15 versus you say 4 plus, then in bracket 5 and 6, that will also be 15. So that's a associative property. You can group number in any way you want, and that gives you the same result. There's summation or multiplication or everything. It merges the value of the same key. I will explain with an example how does that happen. It takes functions and input which has 2 parameters of the same type and 1 element output of the same type. Okay, it uses a local combiner. Let me explain with an example. So let's say you have this pair RDD. So anything where you use by key, it works on the pair RDD only. So you have key and value. So if you see A is repeated many times, B is repeated many times, etc. So one reduce by can do is there are 2 parameters, accumulator and n. So how does that work is I have so it'll take first accumulator will be 0, of course. Then it will take A and it will be 1, right? So 0 plus so key is A, right? For each key is doing separately. For A, it is summing up. So what are the values of A? 1, 2, 3. So it will sum 1 plus 1 plus 1. So it becomes 3, right? You can see A3 here. So similarly, because B is a separate key, so same operation is happening for B also. Accumulator, it takes the accumulator, which is initially 0, and then it takes the value. Here it will take first 1, so 0 plus 1 becomes 1. Then it goes to the B. Again, B says, okay, 1 more is there. So previous summation was 1, and the new value is 1. So it becomes 1 and 1 here. So 1 plus 1, 2. Now accumulator has 2 value is 2. And the next B has 1. So it becomes 2, 1. Then 2 plus the 1 becomes 3. So that's how it is passing. And then you see the B. And this is the output of for the B key also. This is just a syntax. You can use this function, or you can create this function beforehand. It's a scalar syntax. You can create a function and say accumulator and whatever some parameters and what is happening on those parameters. This is a function you created, and reduce by key, you're passing that function. So result is same. Group by key, it's again transformation functions, but it involves a lot of shuffling. It is similar to we'll see the difference between group by key and reduce by key in coming slides. It's costly because it shuffles all the records, and it always returns in the hash partition RDD. If you see the implementation of group by key in your Spark code, it will be using hash partitioning and partitioning data based on the hash and giving the hash partition RDD. And it is not recommended. It's not recommended, and you will see why it's not recommended. But let's see the example of this group by key. It's same. You have some country and whatever, and you're grouping it by. So got num partition, so group by key 2. So basically it's very similar to you're grouping. You generally with group by you just give some aggregate also. That what you're doing with that group by. And here I'm not doing aggregate. I'm using group by key and just giving number of partitions. It will give me 3 because there are 3 distinct countries here. So here group by key 2. So it will have the 2 keys going to the same partition. Total overall keys will be 2. So you can say number of partitions will be 2 because I told it to use 2 partition. In one partition, it will be having more than 1 key. This is a pictorial view of why group by key is not preferred, why reduce by key is preferred. So if you have, let's say these are 3 partitions, and you have A, 1, B, 1. Now here you see A, 1 is repeated and B, 1 is also repeated. So this also has some repetition. If you use group by key, then what is going to happen is 2 elements from this and 1, 2, 3, 4 elements from this, and 6 elements from this will be shuffled. If you use a reduce by key, of course 2 will be shuffled from here, but from here there's a local combiner which is working. So let's say reduce by key, I'm doing some summation. You saw the summation function above, right? So if I'm doing some summation, so those summation will happen on that node itself first. So A, A, 2 and B, 2 instead of 4, it will transfer only 2 elements from this 2 records from this node. And here instead of 6, it will emit only, it will transfer over, or it will shuffle only 2 records from here. So this is okay for 216, but you think about millions and millions of records. So with this reduced by key, how much network traffic you are saving? So that saving is huge. So that's why reduced by key is always preferred. There's a sequence file RDD. What is sequence file RDD? If you've ever worked on MapReduce, then sometimes you need to in the MapReduce word generally it happens. You need to save the data as key value also, and that's one problem which sequence file saves. Solves. Other is that when you have Hadoop and for that matter even Spark is this, it works best when you have when you don't have small files. If you have very small files, then performance suffers. So in MapReduce world, if you want to solve that problem, you can use sequence file there as well. And if you want to use that, if you want to take the same advantages into the Spark, then you can use then you can use sequence file RDD. I have an example of that. You can go to the sequence file format on this wiki. It is explained very well. It works on pair RDD because sequence file is key and value, and you can generate or read sequence file. And I like an example here. So let's say the same data, ID name. I showed you the data in the previous slide, which has ID name, salary, manager ID, and everything. I'm reading the same data in text file, creating a pair RDD, and then I save this as a sequence file. Right? You can save as a sequence file also using or RDD function. You save a sequence file. Now I want to read the sequence file. I just wanted to see how the sequence file reading works. So using Spark session, I read the sequence file, and pass a sequence file, and then there are certain parameters. What is the value of key? What is the type of key? What is the type of class, and all those things. So I read all of that sequence file, then apply some. It gives me the key and value because sequence file is stored as key and value always. So it gives me key and value. I just print that key and value, and I will just convert that to string and give. That's all I do, and I collect it. So that's the result I get. So idea here is that if you want to, generally in your Spark implementation, you will not be using the sequence file, but for legacy purpose, or you're getting some output from some other ETL system, and you have to read that, and that output is in sequence file. So in that case, you can use a sequence file RDD. Co-group RDD. So co-group, what is co-group? So let's say, let's read this out and I'll explain you in words also. So in Spark, the co-group function is performed on different data sets. Let's say you have two data sets. One has this key and this value. Another has, it both have key and value, correct? So now, when you join these two data, when you co-group these data sets, then they will be joined on the same key. Let's say, in this, let's say key is Bangalore and it has 50 records. The key is again Bangalore, it has 10 records, correct? So you will get Bangalore as a key, and you get iterable over this 50 records here, and iterable over this 10 records here. In the two iterables you will get. So that's what co-group works, because it has key value. Of course, it will work on the pair RDD. So this is an example. So I created a pair RDD with some keys and keys and the number of values. Then another pair RDD have the name of the city, the type of the city. So this city sales RDD is the first city type, and you can see the Bangalore has how many records here. I think it has only one. So it will get it will get co-group with Bangalore as a key, and one record from here and one record from here. So if there are two records of Bangalore here, you will get Bangalore as a key, one record from here and two records from here in this iterable. Okay, so that's how the co-group works. Shuffle RDD, you will not be able to use Shuffle RDD at all, but while debugging, while the production, you might be encountering this. You might need to dig into details of this. So Shuffle RDD happens during aggregates, and of course, because all of this the shuffle. Can you, so Shuffle RDD involves two steps: marking when a shuffle needs to take place, which is planning. So here correct, this shuffle happens during shuffle. Shuffle RDD gets created during shuffle, and these are some of the examples when shuffle happens. There might be many functions which might be invoking shuffles. These are few of those. So shuffle involves two steps. One step is marking when shuffle needs to take place, which is planning, and facilitating the shuffle execution. So when anytime these things happen, then shuffle RDD gets created, and you can go into details of this shuffle RDD using this link. Generally, I have not seen people dig into this shuffle RDD, but in case you want more information, please feel free to dig into this. Now there is this is the last one. So this is called new Hadoop RDD. Now, if you ever, if anyone, if you have worked on the MapReduce world, one advantage of that MapReduce world was, and it's possible in Spark also, but it was pretty nicely designed. If I want to read data, so they have given support for reading all Parquet data, ORC data, the JSON data and everything is there. But if I want to read my own format, let's say I have some XML file, which is some one document which contains many XML documents, one big file, one file which contains many XML documents within it, and each XML document is spanning more than one line. So if I have such scenarios, this is just one example. But the idea which I'm trying to tell is, if you have some custom format which Hadoop does not understand, then Hadoop MapReduce will let you decide your own format, let you create your own input split. So if you have such scenarios in Spark also, then you can use new Hadoop RDD. So here, your input format class. When you say input format class, these are the parameters you pass while creating the new RDD. So first the input format class, second the key, and third is the value. Main magic lies in the input format class. If you implement your input format class, basically you will be able to parse any custom format also. Like if you have data in some binary format which you only can understand. So in that case, you create your input format class and tell Hadoop, this is my input format class. In the implementation of the format class, you will be telling Hadoop how to parse this. That's your implementation. So Hadoop will take that your parsing of your schema of your format in this format class and accordingly parallelize the task. So if you have such scenarios in Spark, then you can use this new Hadoop RDD. Let's spend 10 more minutes in going over this. So what? Let's talk about Spark scheduler. What it does is converts Sparks into jobs, tasks, and stages. An action is a job. Each job is divided into stages. Each stage is divided into tasks, and tasks are the smallest unit of work. Each task is also called a partition as well. Correct. So it has given this example. So you're joining, there are two RDDs, you're joining and then grouping by and filter. So this is the operation. This is what it is doing. And then there are two data sets which has two partitions, right? You're doing RDD1, RDD2, assuming this RDD1, this is RDD2, some two partitions here, and then you're joining and then grouping by and then filtering. So this is the join and grouping by happening here, and then filter by is happening here, right? So this is some sort of DAG it creates based upon what you are given, and then it will talk to the cluster manager, and based on this task set which is created, based on this DAG which is created, create some sort of task set, and then talk to the cluster manager. What is the cluster manager? Yarn is one cluster manager, Kubernetes is another cluster manager. Spark itself has an inbuilt cluster manager which generally doesn't get used much, and talk to cluster manager and spin up the task on the worker nodes. Okay. So that's what that's at very high level how Spark scheduler works. I'll add the question into the Jurico platform. I think we are done with this too. I think we're done with two. Yes, this is the last slide. Let me cover only few topics from this, and then we can go into question hour session. So here we'll be covering an accumulator, broadcast variable, and then some RDD advanced operations, map partition little more, and data frame functions. We'll have we'll spend good amount of time in going to the plan of this, how the plan works, and how you can see, if your Spark job is taking a lot of time and you want to debug, you will be able to see what all is happening. So we'll be spending good amount of time here. So let's go through 3-4 of such slides. So what is broadcast variable? I think by now you all know what, sorry, my mistake. By now you know what broadcast variable is. So basically, if you have one small data set, a small data, reference data or whatever data, which is not huge in size, and which can fit in the memory of worker nodes, and in your logic you need that data, so you can send the data as a broadcast variable. So the way it works is, in your Spark application, which is driver program, you have some data, some map or something is here, and you are broadcasting it. So this, once you broadcast, these are the worker nodes. So it goes into the memory of each of these worker nodes. And then on this worker node, executor is running, which might have more than one task running, and each task needs this data. You are doing multiple, transformation inside the task. So if they need this data, it is always available to them through the memory. So how does that help? It solves, the bigger data sets are here, right? Bigger chunk of bigger data set is here, here, and here. So the bigger data set doesn't need to, move anywhere. So you avoid a lot of shuffle by using the broadcast variable. And we'll explain how broadcast variable works in an example in the next slide. Accumulator. So what is accumulator? Let me read through this, then I will tell you, where I have used accumulator. So it acts as containers for accumulating values across tasks. So these are the values, these are the tasks which are running, So if you want to accumulate some, value across tasks, then use accumulator. These are write only for executors and the task. This executor and task running inside this. So these accumulators, task can only write, right? Accessing the value of accumulator is allowed only by the driver. So these tasks can only write, and this driver can only read the accumulator. Driver cannot write, and task cannot read. These are serializable, of course, because these are many worker nodes and the driver code needs to access it or modify it. So they have to be serializable. Accumulator can have an optional layer which can be specified by creating it. Out of the box, Spark provides supports for double, long, float collections. If you have some data type which does not fall into any of this, you can create your own custom accumulator also. The broadcast. So we discussed broadcast variable. Let's see the example of that. So let's say I have a state, a map which has abbreviation in the full form of some states in US. Then I have country which has abbreviation and full form. Then what I do is I say spark.spark context.broadcast and states. I'm broadcasting states. I'm broadcasting countries also. I'm broadcasting both of these. Now I have this data which I read. Here I'm in this program is hard coded, but generally you will read it from a some file or some database or something. So, and this will be millions of records in this data. Okay. Now, so I have created an RDD. Now I want to do RDD or data frame or whatever. So I'm doing a map operation over this. So what this RDD contains, it has first name, last name, the country and the state. So what I do is, I do map of each of these records, and I get the third record, which is country, and the fourth record, which is state. Then I get from the broadcast. So I got this country, which was USA from this record, like because I'm over this data, I'm doing a map. So for the first record, I got USA, and the broadcast, I say, in the broadcast, I have passed, the states also as a, broadcast variable. So I say broadcast, and the countries also a broadcast variable, which is broadcast countries. So from that broadcast variable, broadcast countries dot value, it will give me a map. From that map, I'm saying dot get and passing the US as a country. So it will give me the USA and USA, object, and then scale object, and know that I'll use get to give me the get the data in string. So same is the case I do here. So then I say F1, whatever I got, first name, last name, and then full country and full state. Then instead of USA, it will be United States of America. Instead of CA, it will be California, and so on for the records also. And then I print it just to check it out. So that's how broadcast variables work. Accumulators, I have given one example of accumulator. So you can, use that. And let me tell you why I was using accumulator, where I was using accumulator. See, you use accumulator when you need some information, something for informational purposes only. It need not be, it need not be affecting your business process or business logic. What does that mean? For example, when I was writing some, this I used in MapReduce also had similar concept. So, so you could use there also, you could use in Spark as well. So I wanted to know how many, so one of the processing which I was having, so I wanted to know how many records are there which have some amount greater than 10,000. It was just for my information, not for my business logic or something. So I use accumulator there, and whenever I would found some record greater than 10,000, I will say, accumulator.add, it will add it there. And in the driver code, anyway, I could print the accumulator value. You can see the accumulator value here on your Spark UI also. We'll have good amount of session on the Spark UI in the coming days, but accumulator values are really visible on Spark UI. You can see. So because it was informational purpose only, and you can see from each executor, how many, which executor attributed to what to come at this value. This 45, you can do whatever you want with this information. You can create your custom accumulator. I have not created it myself, but if you want to do, please write the code and give it to me. I will add to this slide also. I think I'll stop here. Let me stop the recording. So we'll cover RDD advanced function. As I said, generally we don't need to worry much about RDD, but in some scenarios where you need to deal with RDD and the advanced function, you would know how to use those. We discuss associative property and commutative property. So associative property is associate, like the name itself says associate. How do you associate in mathematics? By putting brackets. So if you associate, so can add or multiply regardless of how the numbers are associated or grouped. By grouped mean how we use parentheses. So associative property is true if putting the association or putting the brackets across any pair results in give the same result. For example, 2 plus 5 in the bracket plus 7 is same as 2 and 5 plus 7 in the bracket. So this is associative. Commutative, name itself says commutative means commute. Commute means moving, like you're commuting from one place to another place. That's moving. So moving means changing the order. So if a function is follows a commutative property, if for example in multiplication, if the numbers are getting multiplied, you change the sequence of order of the numbers, you'll get the same result. 5 to 4 is same as 4, 5, 2. So if any function follow this, changing the sequence of the operators across operation, then the result is same. That means that function is satisfying commutative property. So now why we not need to know these two properties for some of the RDD advanced functions. So first function is reduce. So reduce function, it works on single RDD. It takes a function which operates on 2 elements, and this function should be both commutative and associative, and it is a new element of the same type. So we'll see an example. So I'm parallelizing some data, some numbers from 1 to 20, and I reduce it. What I do is I take 2 parameters. These are 2 parameters, and this is the function which I'm giving. This function is both commutative and associative. So this is the function I'm giving. So all it does is it takes 1 and 2 first, sum it up, then becomes 3, then it takes 3 plus 3 first becomes 6, then it takes 6 plus 4, then 10, it takes that 10 plus 5. So that's how it does. It reduces it, and you get the sum as 210. How it works? So what I did is to make sure how I print the step in each iteration. So when I invoke the reduce function and pass 2 parameters of I am invoking reduce function over this RDD only. So this RDD dot reduce and INJ, and I print INJ before the submission happens. So first time it is taking 1 and 2, and then it's printing 2. In second iteration, this I is 1 and 2, it becomes 3, correct? Then it takes 3 and it takes another 3, becomes 6. Then 6 and 4, 10. So it takes 10 and then 5. So like I explained. So that's how it works. A group by key, I think we have seen this. I will be repeating some of the slides, so that
Sorry, but I was not able to understand.
You are not able to understand this reduce function.
Yes, reduce.
So reduce is simple. So you have an RDD which consists of these elements, correct? I'm just summing this up in reduce. So in reduce, I'm saying, reduce always takes, 2 parameters, and these 2 parameters are 2 elements from this list. And whatever is function I have, this should be associative and commutative. In this case, I'm just summing it up. So forget this function. If you have to sum this up, one way to do this will be, you will do 1 plus 2, it becomes 3, right? Then take that 3 and then multiply it with, add 3 to this, it becomes 6. Then take that 6 and add 4 to it. That's all is happening here. So first it takes 1.
So for each 2 values like I and J, we are reducing it into 1 value and then summing up with the next value.
Exactly. That's what it is. So group by key, we should avoid it. But I think we have seen it earlier. It causes shuffle. In this case, all the records are getting shuffled and reduce the local, operations happen. Whatever by key operations we are doing, it happens on the local machine. Then shuffle happens. So group by key is discouraged and not performant. Reduce by key is encouraged, and it gives better performance also. There's a fold. It takes function with the same signature. It also takes the zero value to be used for the initial call on each partition. Now, what is a zero value? Zero value is the identity element of the operation. That is, applying it multiple times over the function should not change the value. That's one. For example, you can have 0 for plus. How many times you apply the initial value, which is 0 for plus, the result is not going to change. As for multiplication, it is 1. Any number you have, you multiply it with 1, it doesn't change anything. Return type must be same as input parameters. So that's the property of fold. I will skip this because I have an example here. So you see this same thing. I have integers from I think 1 to 11. So over that integers, I'm applying fold. So now one thing you see, I'm passing an initial value. See, now passing initial value doesn't seem to it doesn't seem, you are not able to think the reason why we need this. In some business scenario, the initial value might be needed. Those might not be exactly mathematical operations or something, but in some business logic or some business implementation you're doing, this might be needed. So you're passing the zero value, and then it takes, now if you see the difference between the reduce and fold. So you have 1 to 11. So in the reduce, it take 1 and 2 as a first pair, but here it is taking 0 and 1 as a first pair. So it starts from the initial and takes 0 and 1 as a pair, and then it becomes 1. Then it takes that 1 and then another one, 2, that becomes 3, and that's how it adds. Everything is same, only one iteration got added and the initial value got added. So that's a difference between reduce and fold. Another example. So I have this RDD, which is of key value type. So I'm folding it. So how it works on this is just a plain integer. If I want to make it one key value, so I'm passing fold because the key is my string and the value is integer, like there's a pair. So then I'm passing blank string in the fold as initial value for string, and because I'm doing some operation right somewhere, so I pass 0 as the initial value for the for the second value of the pair. Then I and j. So all I'm doing is I'm printing I is this, j is this. For example, I is this, j is sales 0. Like initially I'm passing this initial value blank and 0. So it gets blank and 0. Then it takes sales. So it prints that. Now what I'm doing with this is I sum it. This is the some value across departments. So I want to know the value across all departments. So all I'm doing is return type should also be key value here, because input is key value. In the fold, you have to have the return type also is key value. So this is what type key I'm putting all, and the value is whatever I'm getting from first pair, take the second element. Can you go on with me? And whatever I'm getting from second pair, I take the second value of that also. So this is what is happening. So from the I is my first pair, so the second value of the I, and j is my second pair, second value of I. So keep summing it up. So ultimately I get a result which is sum of all this 10 plus 20 plus 10 plus 30 plus 40 plus 50, and I print all as 160. So that's another example how you can use fold. You have fold by key also. In fold by key, it should be used where values need to be aggregated based upon the keys. So take this example. It's the same example actually. I have just put it here, but only thing I'm doing is I'm summing it by key only. So sales. So I have different departments: sales, day, production, and I want to sum it by key. So fold by key, it will take all the pair of which have the sale as key and pass it together. And for each key, it is happening separately. So same thing, I'm just printing it and doing the same thing. And you can see for each key, I'm not printing the key. Maybe I should have printed the key also. So, but for each key is happening separately, and summation is happening for each key separately. So this is the result you get. Key is type string and value is type integer. So sales is 40, for production it is 60, and for day it is 60. a fold by key operation. Aggregate, now you have used reduce and fold. The difference between reduce and fold is, they're both same, but in the fold you can pass the initial value. But both reduce and fold have the same return type as your input type. So if your input type is integer, return type will be also integer. If your input type is some tuple with the string key and integer value, your return type should also will be with the string key and integer value. But if you want to change the return type, then you cannot use reduce or fold. Then you have to use aggregate. So here also you pass the initial value. I will see an example. So so I have this, I'm parallelizing this sales, dev, same data. Now I'm doing aggregate. So I'm passing the initial value. Now, one thing in aggregate you remember is, because for performance reason, this key, there might be many records, let's say sales belonging to the same key, sales 10 here and sales 10 here. Let's say both are in the same partition on the same node for that matter. For performance reason, aggregate would want to do the aggregation of these. If these two records exist on the same node, because these two records have the same key, it would want to apply your function, associative and commutative function on the same node, so that it's like reduced by key, so that the data transfer is less. And we'll see this with this example. So here I'm passing account and value. This is the input, which is sales and 10. One pair gets passed at a time. Then here let's go through this. What are the different types, right? You remember this? I'm passing this as a parameter, and I'm doing this account plus value, accumulator plus value _2, then accumulator 1, comma accumulator 2, and accumulator 1 plus accumulator 2. What in reality this is doing is, this code is getting executed on one partition, each partition separately. And what that is doing is, it's just summing up the value. Let's on one partition sales value is there, right? So 10 plus 10 plus 30 will get summed up, and in 2 iterations. And then that will happen on one partition. Another partition, possibly day values are getting summed up. 20 plus 40 becomes 60. And on third partition, production values are getting summed up. 10 plus 50 becomes 60. So this summing of for each keys on each partition is happening through this function. Now let's say sales value is on some other node also. Right now we have these two sales value which exist on the same node. So this, what I'm saying, will not be valid for this. But let's assume there's another sales key which has sales comma 100, and that sales key exists on some other partition. So now on one partition you have some sales data for 10 and 30, it becomes 40. But on other partition also, on other node also, there's a sales key value, sales data with sales as 60. So across partitions, so this accumulator 1 is for one partition, for example, and the accumulator 2 will be for the same key, accumulation of of the same key on the other node, and it will sum those up. Okay, so I'll explain with an example. Here, no, I don't have example, but I will explain this thing here, right? So you have this accumulator comma value. So this accumulator comma value is input parameters. So accumulator will be 0 for first iteration. Value, the value each tuple in the RDD will be passed one by one in this variable. Correct? So this is accumulator and value. So it will be, because it's key values will be blank and 0, and value will be sales and 10 here. Correct? So and then next time it will be sales and 10 accumulator, and the value will be sales and 30 here. So that's how it works. Accumulator plus value comma value, this 2. This is the function which I am applying over the input parameters which are getting passed to me. What is this? Combining function within partition. So this function is getting executed within each partition separately. So adding the second element, which is the integer, to the accumulator. So all I'm doing here is I'm ignoring the key here completely. Although in the value key is getting passed, but if I say value dot underscore 1, it gives me the key. So I'm not taking that. I'm saying value dot underscore 2. I'm just taking this value because my intention is to sum these up key wise. For sales, I want sum together. For dev, actually for here, I want all sum together, not just sales wise. I want every sum together. So I'm using aggregate for that. So I'm ignoring the key here. So now within each partition is happening. Then after that, across partitions, accumulator, comma accumulator 2, it's a merge function, which is across partitions. So within one partition, you have summed up data for each key, and that happened on all the partitions. Now across partitions, you merge the data for the same key. Key 1 is there on partition 1, key 1 is there in partition 2. Now you're using this accumulator, from across partitions, you're merging that. Key 1 data from multiple partitions are coming and getting summed up using this function. So that's how you use aggregate. Aggregate by key is also very similar. It does for the same key. So now I have used the same example, but I have used the, I'm summing it up because I have used key here. So it's same thing is working for each key. So sales is total 40, for production is 60, and for David 60. I will cover only map partition and I will stop there. So map partition, you have gone through, you have written the code multiple times, so you know what map partition is. So it's just a revision for you. It is similar to map, but helps doing heavy initialization once per partitions. So if data is, your data is spread over 10 partitions and each partition has 1,000 records, and you want to, each record needs to refer to database for something, and you need to create database connection. So instead of creating 1,000 times on each node, for 1,000 times on one node, 1,000 data connections on one node, you can, if you use map partition, you can create one data connection and use the same for all the 1,000 records on that node or on that partition. So same thing is happening in all the partitions. So this is where this is how map partition helps. Some initialization you want to do once for each partition. Your partition might have millions of records. You have billions of records you are processing, and that billions of records are spread over multiple partition, and each partition has millions of records. For all the millions of records in one partition, you want to do one initialization. So use map partition for that. I think I have explained this example in the previous slide also. This is one example of map partition. So I'll stop it here. I will quickly, I will stop the recording also. And then so we'll continue our session. So we had left here. So I will cover some of the, I think you had done good, you have got good exposure to the RDD functions. Last time we covered most of it. Now we'll jump over to the data frame and dataset operations. So this sample I have taken from the Spark website only, Spark documentation. So we have, below, this is a JSON, and remember the two names are same here, and these two names are same, age different, and this guy doesn't have the last name. Actually, none of this has a last name. This guy doesn't have the age. Right? So when I read the JSON, this is how you can read the JSON. So it will automatically print the, and you can say, you said spark.read.json and give the JSON file and then show it. So it will print all those things. Now, one important thing to notice is, for example, I have shown it, this is small JSON, for example, and all JSON, one record is one JSON. If the JSON is big and you want to split into two lines, one JSON split into two lines, then this won't work. So your JSON has to be in one line only. Each record is one complete JSON in itself. So then you can use spark.read.json and you can show it. So it will print the age for Michael was null, and it will print everything. Now I want to say distinct. Now Justin, there were two Justin records which had the same age. So now you see when I say distinct, it's a data frame, by the way. You see this is a data frame. So when I say distinct, it will not, it will remove these two, one of these records, and it will print the rest of the records. And by the way, you see the schema, age and name and everything. Now I want to drop the duplicates. Now drop duplicates has, you can give one column or combination of columns. So if you saw the example here, so there were two names, two records with the same name. So when I say drop duplicates just with the name, it will drop the records which have the same name and give. See drop duplicates with name and age, two records with us which have same name and age. Here in case Justin had same name and age, so those will be dropped and rest will be given in the data frame, output data frame. So there are certain D operations. I have taken the same record, same data set which I have been giving, and this is a schema ID, name, date of birth, salary, designation, manager ID, address, and of course hobbies. I forgot to put comma hobbies here, but hobbies also. So I think most of you have seen the code. It might be just revision for you. So I created data frame out of it. So this is the code. So I import the necessary imports, create a schema, and then I say spark.read. And then give a schema, then header equal to true, then delimiter is equal to colon. And so this is what Anshul was saying. You could go dot option as many times, or you can give dot options in plural and pass a map inside. So either of these things will work. Now I've read the schema. So I want to invoke certain data frame functions or data set functions. So I have this imply. So I want to get the minimum salary. I can use say imply.aggregate and get the minimum salary. So homework for you is that you create a temp view to find the minimum salary from this data frame, from this data. I want to get the average salary. So I can get imply.aggregate and get the average salary. Now I want to add a new column. For example, people with salary greater than average are well paid, otherwise they are underpaid. So what I do is, so this average salary I have already created. So I say average salary dot collect. It will be only one record. So I can get 0 and I get that as a double. Then I say imply with column. So I'm adding a new column. So with column, it adds a new column to this data frame. I call that as a column as a pay bucket. So this is a powerful thing. You can use when condition also. So when column dot salary is less than 20,000, then it's underpaid. When column, okay, this is just hard coded. You could very well put this AS also. And when dot salary is greater than 20,000, you get well paid. If it is equal, basically, if it's not less than, if not greater than, then it will be equal. So you say dot otherwise and say enough paid. So idea here was to show you that you have these when conditions while creating the with column.
Is it different than if conditions?
So it's different than if. The if has case. So you use case conditions for if. This is when condition. So I think I might have some example of case also somewhere.
And one more question on the temp view. What is that actually?
We'll come to that. Sometimes I give a pointer to the things which I have not covered. So we'll come to temp view also. Okay. If I don't come to in this session, then there's a temp view. There's a global temp view. Go and read this yourself. Next session anyway, it will get covered.
Okay.
So we have in data frame .rdd functions. So it converts a data frame to RDD. And you use this when you have to use some operations which are only available in RDD. You want to save the data into Parquet format and read it. So this is the example. This is the data I have in the data frame. So this data frame .write.parquet, give the location. Then you can say spark.read.parquet and read from the same location, and you can print it. So this is what this is how you save and read from Parquet. This most of you have already covered. I will anyway cover it. So I am adding a new expression with salary, which is with tax, which is 90% in this case. So you have this data frame. So I created this data frame myself, and I given this schema salary and tax. And then so one way to do that would be that on this data frame, say with column, and give the column name, and you can have an expression. So what is my expression? My expression is this salary multiplied by some literal. So this salary has to be part of the schema, and it is because I have given this salary as part of the schema. Then once I do that, then I print it and I say and then I just show it, and that's how it gets shown. Describe is a method in the a data set and data frame. It computes it's a function which computes statistics for the numeric column. So like in this example, I have given describe of salary. If I don't specify a column, I just say describe, then it will compute statistics for all the numeric columns in the data frame. This describe you should use only for exploratory analysis. What it shows is it shows the count, mean, standard deviation, min, max. This is just if you want to explore. But if you really want the exact value of this, then you should use we have seen the aggregate mean, aggregate average, aggregate max, and there are ways to create the standard deviation and mean data frame. Use those. This is just for exploring. You want to get some idea what is the mean and what is the min and what max. So that's why you use describe. There is for Hive tables, there is another function. I think we'll cover that when we go to the optimizer, cost-based optimizer. A Hive has this explain table, no, not explain table, analyze, analyze table, give the table name, and compute statistics. It's one command: analyze table, table name, compute statistics. So that will compute information about Hive tables. So this is about the data frame. We'll spend some amount of time here. As I said, we'll cover explain. So we'll spend good amount of time here because this is important. So there's the explain method, which many of you have shown. It prints the physical plan and of course logical and optimized logical plan for debugging purposes. Few things you can check. What you can check here is predicate pushdown. So we'll see pushed filters. There's a flag, and I'll have an example of that. I will show you pushed filters in the plan. If you're querying from a database and you're specifying a where condition, then preferably you want this pushed filter or in the, which means a predicate pushdown to be true, because you want the where condition to be evaluated at the database server itself, not after fetching all the data in the Spark and then you do the filter. It's unnecessary, will cause a lot of network IO, and also it will be slow. So if you see this as a false, then all the data will travel over the network and filtering, etc., will happen at the Spark level, which will make it slow. How to add shuffle? I think in one of the assignment I had given, someone was asking, Rajesh, I think was asking about the shuffle and all. So I will show you, the plan will show that if shuffle is happening and or not. If you see if shuffle is happening, you figure out a way how to avoid it. So you will see in the plan, if you see some exchange, that means shuffle is happening. Now what you have to, I think I have, do I have the flow? No, I don't. I have in some other way, but what Spark does is when you submit the code, it will create a logical plan for your code. That logical plan will get converted to optimized logical plan. So once logical plan converts into optimized logical plan, that means some optimizer has run over this. Then optimized logical plan gets converted to physical plan, and physical plan is the one which gets executed. The physical plan, so you can see this in the UI also. I have a separate section for UI. We'll walk over that in detail, but I here just giving a hint that you can see the physical plan over the Spark UI. And Spark UI is a very powerful thing. A lot of information you can see from Spark UI. And I'll explain, I know there's a Spark also has documentation of the Spark UI, but I will also explain. And this is the way you go to SQL tab, and there'll be a graph and there'll be the details or something. You should be able to see that there. What we see is explain. If there are many variations of explain, one of the variation of explain is you pass true flag. It means extended is equal to true or false. If you pass true, then it will print the logical plan, optimized logical plan, physical plan, all it will print, and it will automatically print on the console. You use it for debugging purposes. Since Spark 3, there is another explain method which takes string. Here it is taking a boolean. Here you can pass a string. What you can pass in the string, you can pass as one of these: simple, extended, code gen, cost, or formatted. So we'll go into each of these examples. So let's say this is I have copied from internet from somewhere. So let's say this is just to mimic the situations where we can see at least proper plan. So what I do is I create a or whosoever I copied from. So it creates a data set or data frame from 1 to, I think, whatever number of digits are there. There are other data frame from 1 to these digits with 2 partitions. Then data set 1 is getting repartitioned into 7 partitions. This data set 2 is getting repartitioned into 9 partitions. Then data set 3 is doing select action ID multiplied by 5 as ID. So it multiplies this this DS3, which is repartitioned to 7 partitions, and as ID. Then it joins data set 5, which is the latest one, with data set 4, which is this data set based on the ID. Then over this joint data set, it says select expression sum of IDs, and then it explains. So this, once you run this and you say explain, once you code this and say explain, this is what you get, what you print. Now I'll go into many of these one by one. So you see exchange happening here, exchange happening here. Exchange means shuffle, and you see one exchange is round robin partitioning, second exchange is hash partitioning, and then some sort of short happening, then some sort of hash aggregate happening, and all sort of things are happening. So I will go into each of these. This is when you, so this is just normal. When you say sum.explain, when you say explain.true, you will see a lot of past logical plan is this, analyze logical plan is this, optimize logical plan is this, physical plan is this. We are more or less concerned about physical plan. Why would you want to look at the logical plan, analyze logical plan, optimize this plan? First, to check whether your optimized logical plan has been properly optimized or not. And there are some more things you can do. Generally, you know, Spark developers don't do that unless you are too expert. But we'll cover in the, when we talk about the optimizers, we'll see, you know, what are the optimizers run between the logical plan to the optimized logical plan. And some optimizers run and Spark run automatically, but Spark also gives you ability to have your extension where you can have, you know, where you think you can optimize the graph with Spark DAG. If you think Spark lets you, you know, inject your rules also while optimizing your optimize the Spark DAG. So we'll cover that in the optimizer session in detail. So these might be the reason if you want to see where you can optimize, you know, you want to see what Spark has optimized, and over that, if you think you can optimize, then maybe you print and see to analyze. But mostly we you know, look into the physical plan. So this is, you know, when you say explain true, so it prints all types of plans. When you print explain code gen, so it will print your code which got generated, right? So your data, your Spark job, this data frame is generating some code internally, right? We saw the logical plan, optimized logical plan, and then, you know, physical plan, and then after physical plan, it generates the code. So if you want to see that code, you can see this. Then you can see last one is the formatted. So if you want to the formatted output, so you can see format, you can pass, you know, this df.explain and say pass formatted. This is how your output gets printed, and then it has 1, 2, 3, 4, 5. So that's how you, if you want to see same output, physical plan output in the formatted way, this is the way you do it. Now we'll focus ourselves on the physical plan, and we'll go over the mostly used operators, you know, and when we when we go to the Spark UI, some of the operators I might cover there as well, but for timing, let's focus on what we have. So mostly used operators are exchange. You are seeing this exchange. Exchange means shuffle. So you're seeing this exchange a lot. File scan, once you read a file, so once you read Parquet file or, you know, ORC file or whatever CSV file, then you'll see file scan. In the example which I have shown, I'm not reading a file because I'm, you know, in this example which I was showing you here, I'm not reading a file. I'm just creating data set on some range of numbers. So you will not see file scan in this, but if you read a file, you will see file scan. And I will show you in the, you know, in the, when we go to the Spark UI, file scan, I will show you at that time. Then you will have this, you know, hash sort or object hash aggregates. I think you see hash aggregate here, another hash aggregate here. So sometimes you will see sort hash aggregate, and sometimes you'll see object hash aggregate. What are those? You will see sort merge join. So that sort merge join appears here. Broadcast join is not appearing here, I think, but broadcast join you all know, right? When you broadcast a variable and on the basis of you join, that's a broadcast hash join, and that will appear in this plan as broadcast hash join. We'll cover this in the Spark UI session. So each rectangle on the Spark UI for the job retail represents one of these operators. So these are mostly used operators. If you understand these operators, I think you get sense of a grip on how to read a Spark plan, Spark data frame plan. So there's a question. Yeah. So we read the plan from bottom to up. Yes. You start reading the plan from bottom because that's where from it executes, and then you go all the way up. So that was right. So we'll read the, you know, physical plans of file scan. Although the file scan is not here, you know, in the example which I've gone, but if you had file scan, then how it will look like, and we'll see the same examples when we go to the Spark UI. So first of all, it shows you that you are reading a Parquet file, and there are a few things you will see, right? I told you there's a pushed filters. Pushed filters, it's, you know, there's a, you know, this is some plan, and in that data frame got created where the profile ID is not null. So it pushed the not null condition while reading itself. So it will not read the records which have this profile ID is null. So this is good. This is what you want. So this push filter, if the file was saved with sorting on column, column part of filter, then this will be used. So if you are sorted this and then you are using, if you save the data set or save the record based upon you sorted on some column, and then you are reading that data set back and using that column on which sorting is done, then generally this is used. Partition filters. Partition filter is this. See, you can partition your record. So I will tell a little bit. I think we covered a lot of content on partitioning, but let's say what we covered was partitioning in the Spark layer. The data is in the memory. So let's say you're saving the data in the Parquet file or ORC file. It resides on the disk. Now you're reading that, and you have partitioned that record. While saving the record into the disk, you partition it. For example, if you have saved the record in Parquet and in Hive, then you are giving partition by year and month. So they will create a folder called year, and under that folder, if you have if you are partitioning on multiple columns year and month, so under 1 year it will create subfolders for months also. So that's how it saves. Now based upon how you are reading it, so it can do the partition pruning, which means it will not even touch some partitions. For example, I am giving this month is not null and month is equal to 5. So it's May month and it should not be null or something. So it will go to the partitions which has month as 5. It will go to that folder which has month is 5. So it will skip all other partition, which increases your performance. So this is how you can check. You have partitioned the data and you want to make sure your data frame is ready, and you're given that partition column in your where class or in the filter class in your data frame, and you want to see whether where Spark is going only to that folder, only to that partition, and not touching any other partition, because that's what you want. So in that case, you check its partition filters. So it will do partition pruning, which means it will prune all the partitions which are not needed. It will read only the partition which is needed, which you have given. Data filters show the filtering done by Spark after reading the records. So where is the data filter? Yes. So after reading the records, some condition check will happen here. Profile ID is equal to this or whatever. So this is after reading. Selected bucket counts. So I think if I remember in the first session we have read, you can save this data frame in the bucketed format also. So this is save as table or something. So if you're saved in that, then it will read the how many buckets it had read. So it had read only 1 bucket out of 20 here. The partitions, how many it had? So it will come here somewhere partition counts. Do you see partition here? So it has read only 1 partition, which is good because it read only the month of May partitions. If it is not doing the if there are multiple partition which satisfy some filter condition, you have given some filter condition which will end up Spark going to the multiple partitions, then you will see partition count more than 1 here. Okay. So that's about the physical plan. Now we'll cover exchange. I will spend 5 minutes. I think we are way over the time. So I will spend 5 minutes for this exchange, and then see we want to cover more on this or not. So exchange is the shuffle. Exchange means data is getting moved from some set of nodes to other set of nodes, and there are various ways shuffle can happen. There's various reasons shuffle can happen. So one is hash partitioning. So hash partition, you say in the plan here, right? So there was a hash partition somewhere to hash partition, exchange hash partitioning. So if you have this hash partitioning causes a shuffle, and hash partitioning happened because of these functions. Either you group by, or use distinct, or you join, or you do repartition only by key, or you say window.partition by key. I think this is mostly coming from Spark streaming. So then you have this hash partitioner. Another one is single partition, and you can see this when you go to the Spark UI. So here in the plan also you can see this is hash partitioning. On the UI also you should be able to see that exchange is happening because of hash partitioning or any other partitioning. So now another cause of shuffle is single partition. Single partition is when all data goes to one partition. You are not providing any column in the partition by, for example. So you are giving one example is window.partition by. There's no column or nothing. All data goes into one partition. So that's why you see single partitions there. Round robin, when no column is specified in the repartition. So for example, you say repartition without column and say 10. So just round robin exchange will happen, but beside exchange, you will see round robin partitioning. And you could see that here, right? So exchange, round robin partitioning, and 9, I think it ended up creating 9 partitions. The range partitioning, I was supposed to cover range. I think I have to postpone to the next week. So when you use a range partitioner, at that time, range partitioning occurs, or use order by. So in both cases, range partitioning occurs, and you should be able to see on the Spark UI that this is range partitioner on this and this. All these things happened, right? So here user ID is some user ID was selected in ascending order that triggered the range partitioning, or you specifically use range partitioner. Now we'll go into the hash aggregate. So you saw hash aggregate here. So some aggregates had happened. So that was one. This is another. So wherever hash aggregate you see, so it depends data aggregation. So logical plan. So I decided there's a logical plan, and then there's a logical optimize, and then physical plan, and all sorts of things. In the logical plans, you will see some aggregates needs to happen. It will not tell you which aggregate. Physical planning decides which aggregate, whether it's a hash aggregate or sort aggregate or object. So basically what it is doing. So when you aggregate, let's say you're doing, average, or you're doing sum, let's say you're doing sum by key or average by key or something, right? So if you do any of these operations, then based upon that key, it has to, get data for that key into one partition and then do the aggregation of all that. So because it has to get data for the same key into one partition, so shuffle will happen. So exchange will happen. You will see that exchange in the plan, and you see the reason why this causes one of these 3: hash, sort, or object hash. So generally it comes in pair. For example, if you see partial aggregation before shuffle and then after shuffle, what this means is that some combiner or let's say you are aggregate, you are doing the aggregation which is sum by some key, and your key is city. So data for city, let's say for one particular city is in partition 1, partition 2, and partition 3 also initially. So Chennai appears, let's say for Chennai, partition has 3 records, partition 2 has 100 records, partition 3 has 10,000 records, and you're doing sum. So we'll see the Spark is smart enough to sum those for the same city on the same partition first, and then when it has summed those up, then the sum data will be shuffled to make sure that all data for the same city comes to the same partition, and then again sum will be applied over that to give you the correct output. I have given one example. So this I copied paste from the Spark book. It's very famous Spark book on the internet. I think I copied pasted from here, but the syntax here is wrong. So this is the syntax you should use. So spark.range 10 group by column ID divided by 2 as group, and then aggregate some ID as sum, right? This syntax you used, and then you explain it. So q.explain, this is what you will see. So some hash partitioning happening because it's getting hash over that. And same was the example in our case also, the butter plan I showed you. So these are the things which cause the the hash aggregates. And you could see here, right? Here. So there's a hash aggregate. So this is partial which is happening, and then after that shuffle is happening, and after that full sum of this is happening, correct? So I have a diagram also after this. So this is a hash aggregate, right? This is aggregate. And with Spark UI, you can see the hash aggregate. Hash aggregate, you will see most of the time you will see one before exchange and one after exchange. This exchange represents shuffle. And if you see, these are the functions which cause it: group by, distinct, or drop duplicates. These cause this hash aggregates to happen. The logical plan will only tell this is an aggregate. But during the physical planning phase, the physical plan will decide whether it's hash aggregate or sort aggregate or object hash aggregate. So here, this is a partial sum, as you could see, and then exchange happened, and that's the final merge sum. So that's how the aggregate works. We covered only the hash aggregate. Now we'll talk about sort aggregate. Sort aggregate represents joining 2 data frames. Basically, when you're joining 2 data frames. So often exchange and sort before joining. So this is an example. So there are 2 data frames which you want to join. Some shuffle happens, then some sort happens on both of these, and then some joining happens. This is the example taken from the Spark UI. This is Spark UI. I will show you the Spark UI also eventually. So often there is one exception to this. So it often exchange and sort before joining. This is one exception. We'll talk about exception later. So it will always have branches which merge in the sort merge join, which is this. One branch is exchange and sort. Some data sets, such a data set been moved while joining, right? Let's say joining based on the city. So one data frame city data is spread over all the nodes. Other data frame city data is also spread all over the nodes. So exchange happens. Then some sort of sorting happens. And then you join those two cities. Sorting on the basis of city is happening. Then you join those. So that's what sort merge join is. Broadcast join, I think we'll stop it here. Broadcast join is the last one. So data is broadcasted. The broadcast exchange operator you will see in the plan. This data is on the each executor. Broadcast join data is joined with other data sets. So when that happens, you will see broadcast hash join happening. So broadcast data, broadcast exchange is separate job in itself. So we'll come to that. I have not given an example of this, but I think you all understand at least this much. Now, this is where I stop. In the next session, we'll cover, I think, some more DF operations. This is explode operation. We'll cover explode in detail, join operation, sort within partition, persistent cache, encoder. This is what I was telling. There is something encoder, and then temp views. And Anshul, you're asking temp views. This is a temp view we'll cover. There are many temp views. Create temp view, create or replace temp view, create global temp view, create or replace global temp. We'll see examples of those. And then struct type. I think most of the people know struct type. So we'll again touch base on that anyway. You want to convert data frame to data set. Applying expression. I think I have done that already. So I might touch on this again. Windows function, I have not added that yet, but there are some Windows function. We might touch base on those. So this is what we might cover, and of course range partitioning in the next session. So let me pause it here and stop it here and ask for any questions. So last time we were covering these topics. Okay, where are we? We covered all the how to read the plan and everything, correct? So one we left it that the broadcast hash join. So if you're broadcasting your data, and in one of the previous session we discussed how do you broadcast your data, and how do you see whether your data is broadcasted. Even Spark Optimizer will also broadcast some of your data if it finds your data set which you are using is the size of that is pretty small. So if data is broadcasted, you will see dataset broadcast operator, and if you see that broadcast exchange operator, sorry, if broadcast exchange operator you see, that means data has been broadcasted. It will be available on each executor machine, and the broadcasted data is joined. When it is joined with another data set, you will see broadcast hash join in your plan, and we'll see this example. So it will be a separate job in itself, but when be a separate job on the UI, when you go to the Spark UI, you will see the different jobs, and maybe today we'll cover some part of that UI also. So take this, you have this, it just a random, Spark thing. So you are taking some, range of 1 to 100 as A, you're joining with 1 to 100 as B, where A.id is A.b, right? So basically it just says the random 1 to 100 I'm creating, 1 to 100 I'm creating, I'm joining. That's all it is. So when I print the plan of this, the physical plan, you can see this exchange has happened, a broadcast exchange has happened, and then the broadcast join has happened, right? The join is inner type and everything, correct? So that's one way to see. That's to see whether your data has been broadcasted or not. So that's about the plan, physical plan, and about broadcast hash join. These are some references. You can go through this. Now what we are going to cover is we are going to cover some data set and some data set data frame operations, which some we covered already, which are commonly used. This what I'm covering is it's not commonly used. Some people don't know this, so they might do some workaround instead of using this in case they have some problems where you could use this. So one method in dataset class is explode. We use this explode for array, list, and map type of columns. So it explodes array or columns, array or all of this columns to rows. And I'll show you an example. It has many variations. One is explode, just explode. It will ignore null or empty columns, and I will show you. One is explode outer, same as explode, but it will not ignore null or empty columns, but it will turn null. PUS explode, it is same as explode, but create two new columns. One column position to hold the position of the element. Let's say if you're an array, right? Array, integer array, 1, 2, 3, 4, 5. So now explored, and it is, you have a record in your data set. That record has some normal columns, string or integer or something, and then it also has one array column also. So array column is 1, 2, 3, 4, 5. So when you explore, it will explode that row into 5 rows. Every column value will remain same except for this array, which has 1, 2, 3, 4, 5. The column value for these rows will be, as you said, 1, 2, 3, 4, 5. And in the position explored, it will add another column called position, which will hold the position of the element, right? And the second column called call will hold the actual array value. Of course, it will ignore the null and empty value. If you use POS explored outer, it is same as POS explored, but won't ignore null or empty value, rather will return null. And let's see an example of this. So I have this data set, so same data set I keep using, like this is a data set I have, whatever, you have used this earlier, correct? And at the end of, you saw that I had hobby, cricket, comma, Netflix, comma, walking or whatever, correct? So I read the data set in CSV format. And then I say, I do some triaging because I want to convert these hobbies as array. So I use this, I say data.select, whatever all columns I have are good, but split this hobbies column I used comma as a delimiter and convert it to it's an array. And if you print the schema, you will see that last column is an array. So now what I do is I drop the hobbies column because it was, comma separated list. Then I select everything and explode array. So this is where I'm exploding, the hobbies column. And I say it as the hobbies column I put it as an H array. So I explode that H array because it's a array type, and the column name is as hobby, and I drop H array, correct? So now if you see this, a drop H array is nothing but the comma separated list of hobbies as array. So now what this result is that I had in the initial in the data set, I had cricket, comma, Netflix, comma, walking for each of the for this record, for example. This explode kept everything same. If you see everything same for first 3 records, only thing is that hobby got split into multiple rows. So same is the thing with second. It had only 1 record for 2, and with the explode it got split into multiple records because whatever number of hobbies you had, those number of records it got converted. Now if you see the last record in this data set which you are reading didn't have any hobby, so that record doesn't appear here because we are using explode. If you use explode outer, you will see last record also appearing. So maybe this is a homework you can go and do. Instead of use this explode, but use explode outer also, and you will see the last record also appearing, the record which doesn't have hobby. I will cover join. So I think most of you come from the SQL background, so you might already know about join. You can go to this Spark reference. It explains about joins with some examples also, but I will cover what are the type of joins we have. One is inner join. If you don't give anything, so then by default it's inner join. I think you all know what inner join is. You can say select. There are many ways to join. One way to join is whatever from imply inner. Like this is one this is one data set, is another data set. You are joining these two on these columns. There is DataFrame.join is also there. You don't have to use this. You can say df.join or dataset.join, and the join operator will ask you the type of join and on which columns you're joining. The join types are right joins. Inner join I already covered. Another one is right join. It has values from the right, matched from the left, or null if no match. So you have when you join, you have left hand side and right hand side. If you do right join, all the records, all values from the right, everything will come from the right, matched from the left, or if the records are not matching on the left, then it will come as null. The left join, same, all values from the left, matched from the right, or null if no match. Full join, all values from both relations, left and join. If left has corresponding match on the right side, it will appear on the right. If it doesn't have match on the right side, it will on the right hand appear as null. Same is the case on the right hand side. If it has match on the left hand side, it will appear. If it doesn't have match on the left hand side, it will appear as null. Semi-join, values from the left which has match on the right. Anti-join, this not many people know, it values from the left which has no match on the right. So generally join means that you join on the match, but anti-join is with the value on the left which has no match on the right. Of cross join, of course, you all know it's a Cartesian product. There's a sort. So you sort the data frame. It's same as order by. It can be done on one or many columns on ascending or descending order. If you don't give anything, it's by default is ascending. So now see the data set which you're reading, right? This is a data set, and the last record has null. Now what we do is, this is not a good example because generally what you do when you have similar records in the same column with some variation. But let's see, this is good enough to give, this example is good enough to explain how different sorts works. So I'm sorting on the name ascending. So you can see, right, in alphabetical order, it's ascending is happening. Then designation descending, there is not much because one person has only one designation. If there are two people having the same designation, you could see that designation is in descending order. The hobbies, ascending nulls first. So same thing here, in the hobbies, the nulls, when you say ascending nulls first, I said, right, you can have ascending order, descending order. You can have normal ascending or descending, or you can say ascending nulls first. So null will come first. So it will get in ascending order, but null will come first. So that's how it is. This example is not a true representation because for this last thing to work, we should have had two multiple people with the same name possibly, and then you would have seen it. But at least you get the idea. If you can do you can do sorting on the multiple columns, each column in a different order, ascending or descending, and both ascending and descending have null first also, so that nulls in that column appears first. You have sort within partitions. So what sort within partition does is, it sorts within the partitions, as the name itself suggests. It's local ordering, and there's no shuffle involved, right? So that's sort within partitions. There's a union. You want to combine two data sets or data frame, you use union. There's a collected list. It returns a Java list containing all rows in the data set. You have to be careful with this because all these rows will be moved to applications driver JVM. The driver JVM, it will move, and it might catch out of memory error. Generally use this for debugging purposes. When you have small data set, you want to test something and you want to print on the driver. One possible reason of using this is could be this use case, but generally in production you don't use, if the data set is used, you don't use this method. Count, it runs number of rows in the data set as the count of the SQL does. Where it filters, it's same as filter and where are same. Filter rows based on given condition, it alias or filter. So both are same. People filter who has age greater than 15, or filter where age is greater than 15. So filter and where both are same, right? If this condition is passed, then only the output, those will be part of the output data set or data frame. Persistent cache, this is important. It stores the intermediate computation of RDD data frame or data set. You should use this when you have multiple actions. If you have only one action, generally, there's no point in using this. If you see, we talked about the lineage of data sets. Lineage is you read from some data set, read some record from data set using Spark and created a data frame out of it. Then you applied some filter, then you applied some aggregate, then you saved into a database, and then you're saving that again into some other file also. So if you now saving to database, saving to another file are two different actions. If you don't persist or cache, what will happen is your first action, which is saving to database, will trigger the DAG from beginning till end. And the second action, which is saving to a file, will again trigger all the transformations from beginning till end. So if you want to avoid because your first action has triggered all the transformations, and second action should not be triggering all the transformation because first action has already done it. So preferably you save this, you persist or cache this, so that your you get benefit in the performance. So RDD also is a cache method. So their cache is memory only storage. Dataset class also is cache method. It's memory and disk. You can specify by default it's memory and disk. The cache method of dataset data frame internally calls persist, and which caches the result. Persist is fault tolerant. If the node goes down, it gets computed. So we should use either dataframe.persist or dataframe.cache. Unpersist is if you want, when you are done with your program, you don't want to keep that persistence or whatever data set you have persisted, you don't want to have that anymore, you can use dataframe.unpersist. I think there is one thing in these memory only and memory and disk. There's a disk only. These are the storage levels which you can pass during your while you are invoking these methods. So it will save those that information accordingly in those storages. This encoder. I have an encoder example in coming slides also, but it converts a Java object to and from internal Spark SQL implementation. When it's a Java object, consider this a Scala object also, because Scala ultimately gets converted to Java object only. In reality, it's a raw converter. So you have this imports Spark implicit. This you do after creating Spark session. If you do this before creating Spark session, then it won't be effective. So once you created a Spark session in your code, then you import Spark implicits. Then only thing I'm doing is that sequence 1, 2, 3 to DS. It just converts into by default it detects it's a int, and it converts into data set of type integer. You can see more details here. That person has given good examples how this encoder internally works. But I have copied some examples in the coming slides. We'll discuss about temp views. What are temp views? I think I have example of temp views here. So we'll go through the example of this thing. So temp view generally you create when you are reading data from some data sets, and you do something and with the data sets. Now you want to create some temp view with some given name, and you want to do some operations over that view. So as the name suggested, it's a view only. And when when you use create temp view, by the way, most important thing is not tied to any database or any file or anything, because it might so happen you might have read data from some file and you might have broadcasted some data, you might have joined this data, and based on certain column the joined data, you're getting some temp view, and that temp view you want to apply, you want to query something or do some aggregation over the temp view, and once you are done, then you don't want, once your program is over, you don't want to do anything in the temp view, it will automatically get destroyed. So this is important. Its lifetime is tied to the Spark session which created this. This is a create or replace temp view. It is same. If you use create temp view, if the create temp, and you have to pass a name. If temp view already exists, then this method will give error. But if you use create or replace temp view, if method already exists, then it will get replaced. If that view already exists, then this method will replace that view. And this is also tied to the Spark session which created this. There's a create global temp view. It creates a temp view with a given name. Now here's a difference. Its lifetime is tied to the Spark application which created this. Here it was for the Spark session. One application can have multiple Spark session also. So if you create a temp view with Spark session, and you can't access that, let's say you have two sessions, session 1 and session 2 in your Spark application, and you create a temp view with Spark session, temp view 1 with Spark session 1, you can't access this in Spark session 2. You can access only within the Spark session 1. But if you create global temp view, then you can access across sessions. It's same, if create or replace global temp view, it will replace if the temp view exists. If you issue this command and the global temp view exists, it will error out. Now, in which scenarios, question is in which scenarios will need more than one Spark session? Well, Spark sessions, as you said, right, you have your data sets, you have your broadcast variable there, and of course views isolated, you can have those isolated in Spark sessions. Generally, I don't know when you might need multiple Spark sessions. Maybe some scenarios where possibly you are using some library to create some session, and that library is connecting to some data sets which is confidential in nature, which you don't have access to directly, and that library will give you some session for that data sets. And second session you want to create for your own data sets, because you want to have your own data sets and join with some data sets which are confidential in nature. That's why one possible use case is this. There might be many similar use cases. I have not encountered actually many use cases where you create more than one Spark session, but because Spark gives you this ability, so based upon your business cases, you can have multiple Spark sessions. One I already explained, but there might be more also. Yeah, the key thing to remember is that one Spark session isolates things to itself. For example, broadcast, join, and couple, of course, this views and a couple of other things. I think in one of the previous sessions we discussed that. So if you don't want this to be shared across sessions, then you create multiple Spark sessions. We'll take some example. One example is, let's take one, create temp view. So the same data I'm using, which we use in assignment also, and then what I do is I load this Spark data. Okay, what is this? Some printing error. Then and for this data only, I'm creating or replacing a temp view. I call this employee. Now, one advantage of that is, now I have created this as an employee. I can run any SQL over this. I can say select star from EMP, which is the same name here, where salary is greater than this. So it gives me that. Or any other SQL which you can think of, you can run over this EMP, because it's a view and it allows any SQL to be run. So that's temp views. I think what you can do is you can practice on your own how to create global temp view with multiple Spark sessions, and try to access that view created from one session, try to access it from another session and see if it is accessible or not. So that's about temp views. We'll cover some of the schema for data set. I think more or less we know. It might be just a revision, but let's still go through this. And this is a good example of this link explains some good example of that. So I have two rows with the name and age possibly, and this is just a row. And then this, I think here, I don't know why I have this slide. This is a 2-row schema for DS. It doesn't have, it's just a row. What I try to explain is that once you create this row, this just has a row, and row, it's a data frame, like it's RDD of type row. A row doesn't have any schema as such of its own, right? So what I have tried to do is, here is, you have a data frame, similar thing, but I have created hello world and something and something. So I'll say here I'm passing the schema and the column names. I'm saying label and sentence, and these are column names. So when I print the schema, it says label and sentence. Of course, it automatically detects I am not putting this under double quotes, so it becomes integer. This is under double quotes, so it becomes a string. So if I if I say if I want to know the schema of one particular column, I can say df.schema, the column name and the data type. It gives me that it's an integer type. You could, we'll see some examples. You could specify the the column types also. Along with column names, you could specify the column types also. We'll see the in further examples. And how do you do that? Using struct type. I think more or less you all know. So we'll just go through this quickly. For struct type, you import these. You use these two import statements. The struct type a construct of a constructor which takes sequence of struct fields, which is nothing but collection of struct fields. We'll see some example of this now here. So you can create a new struct type, and you can add, you can add like this also. Like, because it's sequence, you can add first sequence, which is the column name and the column type, then another column name and another column type, right? And when you so this is schema type, and when you you create another, this is untyped and this is typed, and I'm saying schema untyped equal to type is true, because both have, whether I use int or integer type, whether I use string or string type, both are same. So when I say schema type equal to whether this is equal to this, it returns true, because one way to create this is this, another way to create this is this. So either way you can use. You can see the schema. You can say print listing. This is not the data frame. Remember, this is struct type. If you want to see the schema of struct type, you can say print string. It will print like this, or you can say print ln and schema type of petty JSON. It will print in JSON format also. Okay. We are not passing any metadata or any nullable. That's why nullable is coming as true and metadata is coming as blank. We are passing just the name and the type. So that's the schema. Struct field. This is about the struct type. Now, but let's go to the struct field. Struct field, a field inside the struct type. It can create struct type with the following information. So a struct field can have name, data type. Name is mandatory. Data type is mandatory. Nullable, it's optional. It's true by default unless you change it to false. Metadata, it will be empty by by default, and you can add some value if you want. So I'm creating this struct field. Name, ID, data type, long type, nullable, false, and some metadata. I think I'm just leaving it blank, metadata blank. And this is one. You can also nullable. You can also pass nullable equal to true. If you pass nullable equal to false, and you assign this struct will be part of some struct type, and you assign the struct type to some data frame or data set. If that data set has this column, because ID is nullable is equal to false. If you assign this to some data set, if data set has ID column as null, then it will throw error. It will just throw exception and it will fail. Here I'm passing nullable is equal to true. How to convert data frame to data set? Simplicity. Okay, so you have a data frame. This data frame you have, and I'm passing this name and age. This is a sequence and converting to data frame, and columns are name and age. I'm creating a class person which has name and age. Name is string, age is int. I import Spark implicits, and that's all I do. I say data frame dot as person. It automatically converts this, because each record here can map to this class without any issue. So I can convert this data frame to data set like this. This we already covered, but I'll just repeat it one more time. So you can apply expression to data set and data frame. Like one expression, I have sum of salary. I create this data frame, name and salary. And then I create an employee class, name and salary, import Spark implicits. Then I do data frame to data set conversion using data frame dot as employee, because implicits are there, it automatically gets converted. And now I say data set dot select expression. You see select expr. Then I pass this expression, and this expression is nothing but sum of salary. So it will give me sum of salary, and I say this s dot show. It will give me sum of salary. This is another way if you want to get some aggregates from some data set or data expression. Windowing function we'll cover next time, because I have to add some examples also. Let me go to the next slide. I thought I had it here. Slide number 4. I will cover the UI. This Spark UI. If you get, I don't think we'll get time today, but I want to cover the Spark memory. So next time we'll start with Spark UI and the Windows function. So let me start with the Spark memory. I think someone had this question. Someone had this request to go through the Spark memory. So Spark memory consists of two memories. One is the driver memory. We know what driver is, right? So driver memory is part of the JVM memory only. Then you have executor memory. You have execute, let's say you have 100 node cluster or 1000 node cluster. Executors are running on all 1000 nodes, for example. So executor memory will be on all 1000 nodes. On executor, you can, because executors are running in the JVM only. So you can access on-heap memory, you can access off-heap memory also. So I don't know how many of you have gone through the LinkedIn article I published for using the off-heap memory. If you have not gone through, just please go through that. There I've explained I have written a complete Spark program, how to use off-heap memory and how to validate you are using off-heap memory through Spark UI. So go through that. But here idea is that executors can access off-heap memory. What is off-heap memory? Memory which is outside the JVM. So JVM memory is on heap, which is outside the JVM, that is, which is an operating system. So that memory also you can access using Spark. Now we'll go through some setting, and this is a this is a configuration of Spark. You can go through this. I have tried to explain you the box. This is a total memory we have. Out of total memory, around there is some reserved memory, and that reserved memory is around is fixed. It's around 300 MB or something. This is used for some housekeeping or for something which operating system will handle for Spark. So we can't access this memory. So it's out there. The total memory available is the heap space minus 300 MB, right? So so this is our total memory. When I say this is a heap memory, I'm not talking about off-heap memory at this moment. So this is the total memory. Now 60% of the total memory, in the total memory, you don't include this. So whatever you have left from here, whatever you have left from here till here, 60% of that is reserved for storage and execution. So storage and execution is by default, there's a setting called, there's a configuration called spark.memory.fraction. It is 0.6. If you don't change it, then this is 60% of the total memory. It is reserved for storage and execution. What do you mean by storage and execution? We discussed that, right? For example, you can persist or cache your data set or data frame. You have broadcast variables. You will have variables inside your Spark program also, right? So this memory gets used for that, 60% of that. I've given an example. Let's say I have 32.3 GB memory. So 60% of 32.3 GB memory is 19.2 GB. So that's your memory which is used for storage and execution. Then within storage and execution, you have some memory for storage fraction, and you have memory, you have some memory available for storage, and you have some memory available for execution. Now, here's a trick. Generally 50% is available, correct? So out of 19.2, 50% is 9.6, which is available for storage. When you say storage, where we use persistent cache, that's storage. Execution, your all the variables, broadcast, broadcast data and everything is part of this memory section. So now amount of storage memory is immune to eviction. So you cannot change whatever storage memory you have. It is immune to eviction. It is expressed as a fraction of the size of region set aside by spark.memory.fraction. So if you see spark.memory.fraction is 50% and spark.memory.storage fraction is also 50%, both should come to 100%. And that is part of this 60% within this 60%. Now, I will explain you in detail what do you mean by immune to eviction in the next slide. But I hope this is clear. So I'll just repeat. Of the total memory available, 300 MB is reserved. That you can't touch. Spark can never touch. Out of whatever else is available from this, except this 300, 60% is reserved for storage and execution. Within 60%, you have memory reserved for storage, which is controlled by this. Memory reserved for execution. If by default, if you don't change anything, it is 5%. So 50% of this will be available for storage. 50% for this will be available for execution. Now storage memory. So it is used for caching, broadcasting data. Actually, storage memory, broadcasting data is used in the storage memory. My mistake. I said it is used for execution, but it goes in storage memory. RDD data frame and dataset are stored here based on storage policies. We discussed it, right? Disk only, disk and memory and everything. Generally 30% as seen from the diagram. So if you consider this 60% and 50% of 60%, right? How much it comes to for the total? It comes to around 30%. So that's what it means. Execution memory, which is your this memory, execution memory. This is used to store temporary data in shuffle, join, sort, aggregations. For these operations to complete, there's an intermediate stage to store data, and that's where execution memory is used. You can see the memory management section in this Spark documentation. Now there is one thing. Storage and execution memory borrowing. What does that mean? Storage can borrow execution memory. So if storage becomes huge and execution has free memory, it can borrow. Execution can also borrow storage memory. If execution needs memory and storage memory is free, it can borrow. But there are certain rules. What are those rules? Storage can borrow execution memory until execution claims its space. Storage has borrowed its execution memory, but now your Spark program is running. And as we said, right, during execution, we are doing shuffle, join, sort executions. Your Spark program has invoked one or more of these operations. Now it needs memory, but storage has claimed that memory which was available for execution. And in the sort, sort is getting executed. Then Spark will reclaim that memory from storage. It will evict storage from there and reclaim that for execution, because your program should not stop. It needs that memory. So it can tell storage to release that memory for its own use. Now, when execution memory reclaims its space, cached storage blocks will evict the memory. It can go to disk, for example. It will evict it, because now we have reserved storage fraction for this for the caching and or persisting, but it has claimed some part of this memory. But now execution needs this memory, so it will tell to release this memory. And if the cache or persist can't fit in the memory which was available to it, it will go out of the memory. It will possibly get returned into the to the disk, unless we have off-heap enabled. So we'll talk about off-heap later. So if execution can borrow free memory from storage, but storage can never claim back. See, when execution takes more data, it has more data, and it has borrowed some memory of the storage, and storage increases, so storage can never claim back. If storage memory is full, then new storage block will be immediately evicted as per the storage policy. The storage policy is disk only or off heap, whatever storage policy you say, it will go into that. So rule of the thumb is execution takes priority. If storage and each one can borrow, if storage borrows execution memory and execution needs it, execution will tell storage to release it, and storage will get evicted. If execution has taken storage memory, then storage cannot take it back. So rule of the thumb is execution memory takes the priority. I have the Spark code, so I've taken some of these things from the Spark code only. So executor memory, there's a unified memory manager .scala that is responsible for this. So I think I have a couple of more slides. I will stop it here. I will not cover the reserved memory, or I'll cover reserved memory and user memory, and I'll stop it here. Off-heap memory will cover next time. So let's go through these 3 slides very quickly. So I will just read it out. This is a documentation from Unified Memory Manager.scala. So this is just repetition of what I just said actually. So a memory manager that enforces a soft boundary between execution and storage. We discussed that such that either side can borrow memory from each other. The region shared between execution and storage is a fraction of total heap space minus 300 MB, because 300 MB is always reserved. It is configurable through Spark memory fraction default 0.6. It's just the box which I showed you. The position of the boundary within this space, within this 0.6 space, is further determined by Spark memory storage fraction, which is by default. This means the size of the storage region is 0.6 multiplied by 0.5, which is 0.3, 30% of the heap space by default. So I'll just reiterate so that you understand. This is the 60% of the memory, and out of the 60%, 50% is available to this, 50% is available to this. This is the storage fraction, right? So this is what it says. This is storage fraction. This is the memory fraction, 0.6. This 60% is the memory fraction. Memory fraction, I think we covered the memory fraction here. This is the memory fraction tells about this 60%, and within this 60%, within the 60%, storage fraction tells what storage can claim and what execution can claim. Storage can borrow as much execution memory as is free until execution reclaims its space. When this happens, cache block will be evicted from memory until sufficient borrowed memory is released to satisfy the execution memory request. Similarly, execution can borrow as much storage memory as is free. However, execution memory is never evicted by storage. The same thing I said, storage memory is the highest priority. due to the complexity involved in implementing this. The implication is that attempts to cache block may fail if execution has already eaten up most of the storage space, in which case new blocks will be evicted immediately according to the respective storage levels. So this is what it is, right? The unified memory manager. Reserved memory is 300 MB. It is used for non-storage, non-execution purpose, for example, memory for system or something, right? So in the unified memory manager only you see reserved memory, they have in reserved memory in bytes, they have given like this 300 MB, then this KB, then this is byte, right? User memory, whatever is left. So 300 MB is used for this, 60% is used for storage and execution. We know the boring rules also. Whatever is less is 40%, approximately minus 300 MB, of course. So it's approximately 40%, which is called user memory. This is a heap space left after reserved storage and execution memory is user memory. Users' own data structures used in transformations are stored here. Spark does not do any accounting for this. So if you're doing some transformation, if you're doing some map operation, within that map operation, you have created some variable or something, or some object or something that resides in this user memory. And Spark has no role to play there because it's up to you. Spark does not know when you will need it, when you will not need it. So when is normally garbage collection kicks in once your map operation is over and that object is no longer needed, it will automatically get garbage collected through the JVM. So Spark doesn't do any accounting for this itself. I'm just thinking how many Off-Heap we have. Should we, let's finish Off-Heap. There are only 3 slides. You read my LinkedIn article because I have explained with the snapshot, with the screenshots also. So Off-Heap is basically the memory which is outside heap. So you see examples here, right? This is all heap memory. But if you want to save your data set or data frame outside this JVM memory, then use Off-Heap. And you can set the Off-Heap size in bytes. So in Spark shell, I have set this configuration spark.memory.offheap.size in this many bytes. And I have to enable Off-Heap to by default, it is false. I have to enable it to true. So these are the 2 Spark configs. I have used this configs in the Spark shell, but you could use this config when you start your Spark program, which is in a jar file or in Python file also. So using Spark submit command also. So you can say Spark submit and you can pass this conf file, this configurations, enable the heap, and then give this heap size, Off-Heap size. If you don't give any, if you don't enable it and give only this, it will fail. So now let's see the example of this. So same data set I'm using. So here I am importing the storage and I'm passing, see here, the data dot persist, and I'm saying storage level dot off heap. And I say data dot show. Now, how would I know it is off heap? So when I go to the Spark UI, and the Spark UI, you will see storage section here. I click on the storage section, you will see this memory off heap. It is outside the heap. And so that's how I know it is using off heap. And how to open this Spark UI will cover in the next session. But when you start your Spark program through Spark shell also, it will give you URL of UI. When the Spark submit, that time also it will give you URL of UI. So that's how I see the Off-Heap memory is used. So I'll stop it here. Now what I want to do is I want to stop the recording. So basically what I'm trying to do is, yes, last time we discussed the memory, that was JVM memory, right? But you can have, your data set access the memory outside the JVM. We call it Off-Heap memory, which is the operating system memory. Now to do that, just go through this article. I think either you need to be my friend or something. I don't know why you're not able to see this, but to do that, you have to enable these settings. Spark.memory.off if enabled, and it must be true. And I will, through Spark shell, this is how you enabled. I'll show you that command. And also what should be the Off-Heap size, how much Off-Heap memory you want to consume, so that you should give in bytes. And you can see the details of this in this Spark documentation. The way you enable these settings in Spark shell, it's the same way you enable using Spark submit also. Or you can invoke in your, or you can set this configuration in your code as well when creating the Spark session. When you say Spark session builder.create.conf, you can use and set these properties. So so I'm using Spark shell. Memory heap size is this, and memory of heap enabled is equal to 2. So this must be done. The sample data which we have been using, I'm using the same one, and you also how I'm reading, how everyone is reading the CSV file with header true and delimiter as semicolon and something. Now to persist it, I'm importing this or Apache Spark storage underscore whatever and data.persist. Now here important thing is I'm using storage as off heap. Now once I use storage as off heap, and of course and then I show the data and do some action or something. Now how do I know whether it is storing off heap? You can open the Spark UI. So once you open the Spark UI, you go to the storage tab. Let me see if you can open this in new tab. And if you see in the UI, you go to storage tab, and whatever you have saved off heap, it will show you storage level is off heap. So you can be sure that it's not using the JVM memory, it's using memory which is outside the JVM heap.
There is also one
one
option, like it says replication 1 only, means can we increase that part also?
Replication 1 is because I'm using the, where is that replication 1 you saw? I'm using
storage level. Yeah.
I'm using one except because I'm using local Spark shell. But when you run on the cluster, you can, your replication will be 3x replicated. But you can, this is any RDD which you save, because it's local on my local laptop. So that's why it's saying 1x replicated. But if you're in a cluster, it will replicate whatever your replication factor is. Okay. Now what I do is, how do you unpersist this data? I use data.unpersist. Here I say data.persist with this storage level. Then I say data.unpersist. Then it goes off in the storage level. Now I want to save this data only in the disk. So then what I do is, I say data.persist and disk only, and then data.show. And again, you go to the storage tab, and let me open this in new tab, and you will see it's disk serialized. Right? So because that's the storage level I have given. So that was assignment number 3 or something. So you can do that. Now just follow this and do that. Pretty simple. Any question? If not, then I want to come back to today's sessions. Let me see, how do I start it from? I will start it from here. Windows functions. I think someone mentioned in the WhatsApp group that these Windows functions are the interview question that person got asked during the interview. So start with the interview in window questions. And okay, I don't want to share. I want to present it. So window functions operate on group of rows and return single value. They are used for moving average, cumulative sum, or accessing the values of the row appearing before current row or after current row also. This is a syntax of window functions. There's a Spark documentation. I think I mentioned the link. This is copied from there. So window functions over some partition distribute by partition column, and the column value whatever order by expression, ascending, descending, first, last, and we'll see the example. So don't worry if you don't understand all of this. Now this is a window function, and these in this window function one of these things can appear. The window function are split into broadly 3 categories, and by the way, these are all SQL functions. These are nothing related to Spark as such. So if you know SQL pretty well, you would know about these functions yourself. And if you want to understand details of these functions, you don't have to read the Spark documentation. You can go and read any SQL documentation. And most of the SQL, most of the RDBMS like SQL Server or Oracle, or MySQL, they support this. And Spark also supports this. So first is ranking function, and we'll see some example of a few ranking functions. So you can say rank, dense rank, and of course percent rank, entile, row number. We'll not be seeing example of all of this, but a couple of these we'll see example. An analytics function, you want to do cumulative distribution, lag, lead. We'll see example of these 3 also. An aggregate function, you all know, min, max, count, sum, average, etc., etc. So now there's a window frame. So if you see somewhere there's a window frame mentioned here, you see this window frame at the end. Basically, idea is whatever function you want to evaluate, this is over which data. Now that data is described by window frame. Window frame, which row to start the window and where to end. Like basically, you have millions of rows, and you want to say I am taking from row number, like row number 1000 to last row or something. So some frame you want to give. So syntax of this is range row, frame start, between, frame start and end. And we'll see example of this. I think if you're not understanding this syntax, that's okay. You will understand with the example, and you can go in and read yourself also later. So what is the frame start and frame end syntax? So you have unbounded preceding, offset preceding. So I will explain it next slide. Unbounded preceding is basically from whatever row you are in, from there till the beginning. And offset preceding, so till certain offset. Current row, whichever row you are in. Offset following from this offset to the offset following is for the row till this offset, and unbounded following is the last row. Right? Offset specify the offset from the position of current row. So if you say whatever offset your current row in, after that you want to go some rows after, then use of offset following, some rows before, you see offset preceding. If you emit the frame end, if you don't emit this, if you emit the frame end, then it omits, then it defaults the current row only. So generally you specify frame end. So we'll see some examples now. So these are some examples. So what I have done is, I wanted to read some data over which you can use this windowing function. So I created MySQL table. So in MySQL, I created this table, and with the name, department, and salary and age, and these are copied from Spark documentation only. If you go to Spark website, this is the example. I added a couple of more over this, and in this I added these values. The name and the department and the salary and the age. Correct. So these are the rows I added. Now because I created this in MySQL, I'm using Spark shell. So I'm using Spark shell. I have to tell Spark to understand MySQL connector. So I use this MySQL connector Java jar. If you are using Spark submit, generally for your production program, you use Spark submit, either through a command line or through some scheduler like Airflow or something. So each Spark submit, command will let you specify the jars. What are the external jars you are using? So Spark jars will be already there in the Spark cluster. But if some jar which is not in the Spark cluster and you want to use that, we call it third-party jars. So you can specify those with -- jars option. I think we covered that during when we discuss Spark submit command. So you specify -- jars option and then give the jar file. Here I'm giving my SQL connector. So I'm using Spark shell, but with Spark submit also it will be the same syntax. Then what I do is I say read spark.read.format JDBC, because now I'm reading from JDBC. Now what is my JDBC URL? This is the URL, because on my local host only I have a database called test. This is the database name. In that database I have a table called employees, because this is a table I created. So table name is employees, and user is root, and password is this is what my password I have given. And then option driver, the com.jdbc driver. This is com.mysql JDBC driver is what will come from this jar, and then just load it. This is normal SQL, normal Spark JDBC loader. There is nothing, no window function here. It's just a setting up an environment and reading the data from the MySQL into a data frame. Now what we'll do is we'll say an example. Now we are creating a temp view and we are using a rank function. Now what that rank function does is, now see carefully. Here, okay, let's go through this, then I'll tell you the difference. So what we are doing is we are selecting the name, department, and rank over partition by department, order by salary. Now what does that mean? So now go back here and you see these are the departments, correct? So now when you say partition by department, order by salary, so this partitioning is happening, this ordering is happening within each department. So sales is one department, engineering is another. So all row, these and this row for sales, for engineering, this and this row for engineering, and then for marketing, these two rows. So there are three buckets which are getting created. One bucket for sales, one bucket for engineering, one bucket for marketing. Within sales, the ordering is happening over salary. Again, within engineering also same thing is happening. Within marketing also same thing is happening, but it is within each bucket. And that bucket is created by department, because we have set partition by department. And we are saying, so we did this rank. This rank is over the that each of these 3 buckets. And then I just, print this. So I'm selecting the name, department, and rank, which is, order by, which is a rank over department, order by salary. Now you see the difference. Within sales, there are 3 ranks, 1, 2, 3, right? And if you see the record, Lisa, Alex, and Ivan's are sales. So Lisa, Ivan, and wherever the Alex is, these are the sales. So based upon the salary, the rank is given. Lisa's salary is, 1,000, then Ivan's salary is 3,200, and Alex salary is it's 10,000, 32,000, and 30,000, right? So this is how the salary is ordered, because this is what we have told. Same is the case with the engineering. So 1, 2, now there's a difference. Now you see Chloe and Tom. So if you go to engineering and check for Chloe, and it has, she has 23,000, and Tom also 23,000, right? Both belong to the same department and both have the same salary. So in this case, both are given the same rank. Now Paul is the last one, right? It has the, where is Paul? It has a maximum salary, I think, this one, right? Now, with the rank, you will see with the rank function, you will see it has skipped 3. It has directly jumped to 4. So 1, 2, 2, 4, because there were 2 people with the same salary. Implicitly, it assumed that because it was supposed to give 3 to this, but it has given 2. So it consumed 3 already. So it will not consider 3. It will jump to 4 already. So this is what rank does. Now there's another function called dense rank. Now same thing, everything's same. Only thing I'm doing is I should be using dense rank. I did not copy I think I kept this thing rank, but I assume this is dense rank, dense underscore rank. That's the function. This is what it is. Right? Select name, department, dense underscore rank over partition by this. Ignore this, this statement. This is the SQL statement.
You have added it at second part in the same query.
Oh, right. Sorry, my mistake. You are absolutely right. I have added rank and dense rank both because I wanted to see the difference, show the difference. You are absolutely right. So rank is this and dense rank is this, correct? And so see this, rank is over whatever the previous statement was. This is the rank, and dense rank is same thing, but I have used the dense rank over partition by order, partition by department, order by salary, and this is what I have given as dense rank from employee. Correct. Now in the rank, everything is same. Only difference you will see is in the Fred, Chloe, and Tom, the rank had 1, 2, 2, and 4. Here you will have 1, 2, 2, and 3. So if you want to not skip the rank, not skip any digit because the salary is same or whatever column you are ranking over, if that value is same, then you don't want to skip this, then you use dense rank. Otherwise you just use rank. It all depends upon your business logic, the business problem you are trying to solve. But these are the 2 functionality which Spark is providing with rank and dense rank.
And in that method, if we don't give this rows between unbounded preceding and current row, what does that brings the difference? Means what difference does that line bring?
So let's try that. I did not try it, so we'll try that right away. Let me see. I will open the Spark shell. Let me open the Spark shell right away. Okay, and first we'll read this data. Oh, I have that this thing. I have to read this JDBS. JDBS PF. I have to use only this. Hopefully, Tigonas is the. Okay, my mistake. I should have done this. Control R. Controller hyperpin jars, and this is what I want to use. Okay, so now what I'm going to do is I'm going to paste what I had. Detected this. Now let me print this. So this is the records you would have. Now, what were you saying? Let's do that. Window function. Get to only this. Now we are saying, sorry. What is this? So it's arena. Oh, because I did not create the select dance for name, department, and strength partition by. I think I need to create that EMP, right? That I did not create. This one. This one. Now I'll run this. Then show. One, two, three, 1, 2, 2, 3. And you are saying now if I don't give this, this is same because there is no difference. When you say unbounded proceeding, it starts from the beginning. When you say current row, right now we are not processing anything, so it's from beginning till end. So it's doing the same thing. But if you are in between the processing, and then you issue this statement, then you might get that different result, because that result will be from your current row till the beginning. Now here, because it's from beginning till end, whether you give this or you don't give this, it's coming at the same, it's giving the same result. But if you are somewhere on your current row, and then you go beginning from that row till the beginning, then you might see the different result. So that's a difference.
Do we need, means there can be some kind of scenarios where we will need this kind of thing, like to read something above this or below this?
No, above this and below this is the different. That's lag and lead. Here you are just creating the rank. Rank, you might need this sometimes. I have not seen scenario where you generally, when you read rank in big data processing, because in big data you are talking about billions of rows. You will not, mostly you will not be needing to use the preceding and current row or something like this. So because maintaining this cursor or the pointers within billions of rows is a problem. So generally in Spark, you will not be using this rows between and all of this, but of course you will be using rank and dense rank quite often, because you would want to know, like this is one example. You would want to know what's the maximum salary, second maximum salary, third maximum salary. This is one way of doing this. And depending upon the business logic, you might need to do. So I have used this in some use cases. This I have not used. This I have not used ever. So but you might need to use rank and dense rank.
Okay.
Does this answer your question?
Yeah.
Okay. Now let's move on to the next one. This one was a cumulative distribution. I think we covered the dense rank. So this was a cumulative distribution. So in the cumulative distribution, it's pretty simple actually. So you will see, right? So let's go through this. So the select name, department, age. Now cumulative distribution over partition by department, order by age, range between. So you can skip this for this also, by the way. So you can say partition by department, order by age. So what it will do? And you are using a cumulative distribution function, and you're doing over the department. So how many departments we have? How many how many rows we have in each department? So 1, 2, 3 for sales. So it will be, and you are saying order by age. So first age will be, it's sort of cumulative distribution of the first row is 33%, correct? Because there are only 3 rows. Second is 66%, and third is 100%. So cumulative, the records distributed over these ages are in this range. That's what it means. Same is the case with engineering. So you have 4 rows, correct? So first row cumulative distribution is 0.5, then 0.5, 0.25, 0.5, 0.75, and 1. It's a distribution. So that if over 4 rows, the distribution will be 25%, 25%, and so on. So that's what it is. For marketing, there are only 2 rows, so 50% and 100%. That's how it is. The next one is, now I try to explain the lag and lead. This is a program which is not a Spark program. This is not a Spark thing. This is normal SQL. I've tried to tell you what is lag and lead and how does it work. Right. So take this example. I have these three IDs 3, 1, 2, and I have this in names and I have these values. Now I run the following lag query. Let's see the result. Select seller name, which is this, sale value, which is this, and the lag, this is the third column lag. And what this lag will do is order by sale value, order by this as previous sale value. So now we are ordering by this, and you will see, it or by default, it's ordering in the ascending order, 77,000, 12,000, or 25,000. So now what is the previous value of the previous sale value? The value of the sale value for the previous row, what that is for this row. There is no previous row, right? Because it's the first row, there is no previous row, it comes as null. What is the previous row for this? The previous row for second row, it's the first row. The previous row for second row is first, and what is the sale value of first row, which is the previous row for second row, is 7,000. So 7,000 will come here. What is the previous row for third row? Is the second row. So what the sale value of second row is 12,000. So that will come as previous sale value here. So that's what this function does, lag. This is a normal SQL function. There's no Spark here. So I have tried to do this in Spark and see how it gets done. So lag order by salary, value of the above row salary, right? That's what we discussed in lag column. Null for first in the, because we are doing the partition of a department, order by salary. Lead, value of the below salary. So it's very similar to this, but now in the lead, value will be the of the row, which is after the current row, correct? And we'll see example of this. So I try to calculate both lag and lead in the same SQL. So you say select name and salary. So name and salary will appear as is. Then you're saying lag over partition by department, order by salary. So for within each department, I am calculating this lag. That's what partition by department means. Within each partition, lag and lead will be calculated. How lag and lead will be calculated? Order by salary. Now, if you see, you're calculating the lag for there is lag means the previous row. For first row, there is no previous row, it's coming as null. For second row, and it's it's a salary, by the way, because order partition by department and order by salary. For the second row, what is the previous row? This one. And what is the salary here? 10,000. So that's appearing here. Same is the case with third row. Now what's the lead? So I'm saying lead salary 1,0 over partition by department, order by salary as lead from employee. Now lead is again salary. So you will see the next, what is the next row for the first row is the second row. What is the salary of this? Is 30,000. For this second row, the next row is third row. What's the salary of this? 32,000. And here it is appearing 0. So what I'm saying is, for first, just make it 0. This is what it means. So when you don't find the next lead, then just make it 0. This is what it means. So that's why it's appearing as 0. For Fred, same thing for our, because it's partitioned by or department. For each department, it is doing this, right? So that's about lag and lead. Sometimes it comes very handy in your business logic, right? If you do, honestly, I did not know these functions 3-4 years before, and I did a lot of workaround to get these values. And when we came to know about these functions, it became pretty easy. So knowing this comes very handy when you are stuck with some problems which need this. So one is entile, which I am not doing. I think you can do that yourself. Unbounded proceeding, when you mention unbounded proceeding, it's the first row in the partition. When you say unbounded following, then it's the last row in the partition. So that's what it means. And you can see these are some references. This is pretty good. This guy, Jacek Kowalski, is very good. He's given a lot of YouTube video talks. You should see his YouTube video, and he's written a Git book on on the Spark as well as the Spark streaming as well. So you should go and look into this. It's pretty good. So he explained the concepts with examples, and then explained it very nicely. And so you should go and look at these URLs also. I think that's about it. Any questions? Any comment you have?
What will entile do actually?
I forgot that. I think we can read that in the Spark documentation. And tile. It's normal SQL function. You can search for any SQL and tile. And this is what it is. You see this documentation everywhere. So whatever it's in all places, distributes row in ordered fashion into specified number of groups. The groups are numbered starting at once for it. So you go through it. This is normal SQL. I think this you can see better example in Geek for Weeks. This explained Geek for Week explained better. So it's just distributing of some row into certain groups based upon certain conditions, hopefully. So the window function to distribute rows of an ordered partition into predefined number of equal groups. This is grouping, just sort of creating bucket. Right? Just go through this. No, it's some sort of bucket is creating using these groups. I never use the central function, but it will be good if you go through this yourself. Any other question? Okay, now we'll cover the Spark UI. So what we'll do for Spark UI is I will write some query on the Spark SQL, and then we'll see the Spark UI, which is the values in the Spark UI, which is resulting as part of that query. So let me run this query in the Spark SQL. And by the way, when you start the Spark SQL, you can see your URL, or even Spark Submit also. You can see the URL is this. So I'll open this URL after running these queries. Sorry, why did I copy that? I copy this. Okay, good. I copy this. Okay. Good. It's just something I'm running. Just getting some converting this sequence into the DF, and then department, and then I might be doing a join somewhere later. Did I not copy that? Yes. Let me copy all three now. Okay. This is first. And now, is that all? Yes. And by the way, you can see the Spark UI, on this. It's pretty well explained on this link. So you can go and look at this. What I'm going to do now is going to the Spark UI here. Copy this. And paste this. So this is what I see, right? Now you see jobs, you see stages, storage, and we'll go through it one by one. We'll just follow the. How can I open this in another thing? Let me open Firefox. Put it there. Correct. So now we'll go through this one by one. We'll close all of this. Okay. Now on the Spark UI. So let me start from here. You will see Spark jobs, stages, storage, execution, storage environment, executor, streaming, and all those things, right? So it starts appearing here. So we'll go through each of these one by one. And I might not follow all these slides, but what this jobs is. Jobs show you any action you have performed. So every action will come here. And because I have performed show, so I because this is what I've been doing on my Spark console, and this is what is appearing here. So this is what is appearing here. I can click on this. Once I click on this, it goes to details of this. You can see the event timeline, right? The executed driver added and everything, and you can see the DAG visualization. This is basically how many stages and all that you have, and then some exchange might happen. And this is the window operation which I ran. Sorry, this is for the previous window operations I ran. So that did some exchange or something. So you can see that. You can see the details of this. Generally because Spark SQL, it doesn't show your code, but if you have written your own code, your code, and you're seeing this UI which is generating from the action of your code, then you will see your code lines appearing here. Your name of your class file will start appearing here with the line number and everything. So you can see that. from this, go to jobs, click on the job, and this will start showing the details of that job. And generally for your code, you will start seeing, because in your code, you will be reading some file, you will be doing some operations, and you will be having more than one executor. Here it is showing only driver, but it will show executor 1 added, executor 2 added, executor 3 added. It will show all of that in this graph. This graph is not that of important generally. This is what generally you look at for this job, what shuffle happened and why it happened, and what's the code, sometimes. But it has come very handy for me when I see shuffle has happened and I realized I am doing some, count which I was not needing to do, and that was triggering in, some performance issue or something. So it comes handy that way. So you can see that. Then stages, of course, this is what I showed you. It's the same thing you can see here also. Thus in the stages, how many stages you have, you can see the DAG visualization here for this. Some shuffle already I created while showing it, console. Something happened, window operation got run, and some map partition happened here. And I don't want to see additional metrics. You can see generally I don't read much, but this is what becomes very helpful when you're running your code in production. What you want to know is how much data is getting shuffled, because more data shuffle means it's a more problem. So you want to see that how many shuffling is happening here. The tasks, you can see the task for the executor. So this is the additional metrics of executor. Executor is nothing but my driver only is executor because I have a Spark shell on my laptop. So it started 100 tasks for the window function which I generated. It completed all 100 tasks. And of course, it had some this shuffle size, shuffle rewrite size. And you can see each of these tasks. In my case, it's showing driver, but if you have more executor, it will show the executor ID here. And yeah, so this is about the tasks. You will see these things, task wise also, these things value getting populated. And if you see error, and I think you can click on that error and see what the error is for each task. So that's about the jobs and stages. Let me see what else is in stages. Yeah, for each action, whatever the stages are there, it will show all of that. Then you see storage. This I think I showed you. Once you do caching or persistence, it will start appearing the storage, the LinkedIn profile which I showed you. You can follow that and see the values appearing here. Environment, whatever environment you are using, sometimes it comes handy. Few of the things which I want to see, I think there is some system properties which are getting applied here. Not this. There is one Hadoop properties which are getting applied. Whatever you have set, your HDFS or something, what you have set, you can check that here. What setting Hadoop is taking. I don't use it much, but once in a while I end up referring to this. System properties is whatever your system property you set using -d option, those start appearing here. And the class path entry, this I refer very frequently because sometimes I set the class path and on 2 occasions I see problems happening. One occasion is that some jar with different version is in different folders. I try to figure out and that causes problem during runtime. So then I try to figure out where each jar is coming from. So I tend to look at this class path entries and figure out which 2 jars that particular component has and which folder they are coming from. So I look into this path and everything. So this becomes very useful in those scenarios. Another scenario is that I included some jar and the jar the code is throwing that class not found exception because that jar is not getting detected. So I looked into this and figure out whether that path where I have stored the jar is appearing here or not. So these are some system properties. Executors you can look at. So any job you submit, it will have an executors and right now because I'm using Spark shell, so it will have only one executor, but you will see a lot of list of executors here. And you will see each executor is doing how much shuffle, how much shuffle read, shuffle write, how many tasks it has. And of course, if you want to see the thread dump of each executor, you can go and see the thread dump also. Sometimes it helps if you want to see how many, how the system is behaving under the hood. So you might want to look at the thread dump as well. But yeah, this comes handy when one important thing you want to look at this is this. Let's say your machine has, I'm talking about cluster, not about your local. Like I'm showing it on my local, but in your cluster, you have, let's say your cluster, to keep it simple, consists of 10 nodes. And you will have 10 executors. Generally, the relation between executor and node is not 1-to-1. One executor, if it is one node, it has good capacity, it can have 2 executor also, or 3 executor also, based, and that you can specify by submitting your Spark application how much memory each executor can have. Based on that setting, one node can run more than one executor also. But to keep our discussion simple, let's say there is one executor per node. Now, and that executor, but each executor is having, let's say, 32 cores. Generally in production, you will be having 32 cores or 64 cores or something like this. Now, what you should use is, if you see, come here and see the executor, your executor on that particular, one executor is using only, let's say, 10 cores. Basically, your 22 cores are wasted. Like 2 cores you can keep system operation or something. So out of 32 cores, you want your Spark program to use 30 cores at least. If it's not using 30 cores, that means you have not configured your Spark program to run optimally. So this is very important thing you should check, because you over provision your cluster and you don't use the cores. So that means you're paying for that hardware but not using it. It's a waste, and your Spark program could have become faster if you could have used all the cores. So there's a setting in the Spark configuration. I think I'll open the Spark configuration page, and you can specify executor, core per executor or something, and you increase that. So executors should start using on one node. If it is running one executor is running, it should start using as many cores as possible. If more than one executors are running, then let's say 2 executors are running on one node, then both executors together should start using, and you can see that on one node, if 2 executors are running, the address will be same for both executors here. So those together should use almost all the cores except 2-3 cores you want to leave. You should use all the cores of that particular node. Then your task will be much faster. So these are the and then of course SQL. I think we saw SQL example last time. So when you're reading the file or something, you can see here, right? I tend to see. I think I discussed last time also. If I'm reading a file, you can see the plan also here. By the way, the physical plan only it will show you. And when I'm reading a CSV file, it will show me the details that which file it read and which folder it read from, and how many files in that folder it read. Right? Folder might have 100 files, but I'm reading it based on certain condition. It might have read only 2 files or 5 files or 10 files. So it shows all of that information to me here, right? So you can click on this. In this case, it doesn't matter because it's all local and everything. But this comes handy, during debugging such information. This is about Spark UI. Any question on the UI part? Okay, so use this UI quite extensively. Use your plan. I think we discussed the planning earlier. Use your plans quite extensively. If you do your plan, if you look at your plan, you will come to know a lot of problems yourself. And once you have optimized your plan, and then further things, you can look at your UI and see where the problem is and whether your Spark job is using all the resources or not. So that's about the UI. Now what we want to cover next is, so this UI is done. Window functions are also done. Now I want to cover the range partitioner. I think someone asked for range partitioner last time, and we'll cover the range partitioning, how it works under the hood. And what I have done is I have gone through the Spark code, how Spark code, how range partitioning is written in the Spark code, and I have copy pasted that part of the code and try to explain here. So range partitioners, I will go next. Let me share. So while it's loading, so data, if you go to the dataset API, in the dataset you have the repartition by range option. So you could use that option to repartition your dataset. And I looked at the test cases. I am saying share. Sorry, mistake. Should say present. Hope it loads fast. Yeah. So data set is repetition by range. So I looked at the code. So DataFrames suite, it's a Spark code. So there they have their testing repartition by range. So we'll see how they are testing. So they have some 0 to 9 and whatever. The here what we wanted to check was they're repartitioning by range. They're passing some size and some value, in some order, and based upon that they are, repartitioning. And I'll explain it below. How is that working? So if you go to repartition by range, this is the partitioner.scalar. And if you go look at the repartition by range and look at the documentation, let's read out the documentation. It's coming from the source only, right? From the dog's mouth, from the horse mouth actually. So it returns a new data set partitioned by given partitioning expression into number of partitions. So here you are passing number of partitions, and partition expression is the column over which you want to partition basically. The resulting data set is range partition. At least one partition by expression must be specified. When no explicit sort order is specified, ascending nulls first is assumed. And we discussed that ascending null first, ascending and all those things. Note, the rows are not sorted in each partition of the resulting data set. Note that due to performance reason, this method uses sampling to estimate the ranges. Hence, the output may not be consistent, since sampling can return different values. The sample size can be controlled by Spark. This is the configuration. Config by spark.sql.execution range exchange dot sample size per partitions. So based on this sample size, it will try to sort of find out the ranges of this. And I think I have example of this further. Let me see if I have example. Somewhere I have example. This is the example. So let's come to this later. So this is what the this is what the where were we? Yeah, this was the range part repartition by range in the Spark code. Then it's a details. A logical plan is another method in the data structure which provides the same. So repartition by this, they copy pasted this repartition by range, and it tries to repartition. It tries to get the sort order. If nothing is given, it just try to get whatever is the default value, and then in that implementation, it just repartition by expression, sort order, and logical plan. Now, this logical plan, the idea to show here is that the repartition by range will internally use a logical plan, and this logical plan would have already calculated it. When you submitted your Spark job, the first thing it does is to calculate the plan, and it would have used that plan and the sampling and the sort order which you given to come up with the to repartition your data set by range. Now, this is too much code. Let me skip that. I think you get the idea. We'll see the example. Now, there's another class called partitioning.scalar. So partitioning.scalar has range partitioner for RDD. What we saw above is the datasets of scalar, which used for dataset and data frame. That's how it works. But if you're using the RDD, then how range partitioning works, right? So we'll just read this out. This is for RDD only. Represent a partitioning where rows are split across partition based on some total ordering of the expressions specified in the ordering. When data is partitioned in this manner, it guarantees given any two adjacent partition, all row of the second partition must be larger than any row in the first partition. Right? Because when you're specifying range, let's say you're specifying a range of salary. So if the salary is, let's say, 10,000 to 20,000 might be in the first partition, and 20,000 to 30,000 might be the second partition. So that's what it's trying to say here, right? You should do the ordering. This is a strictly stronger guarantee than what order distribution, or forget this, we are not using. So this is the implementation of range partitioning in using in the RDD class. The RDD uses this range partitioning class. So I will not go into details of this, but I just wanted to show you this heading. So let's see the range. I copied this from this URL. So range partitioning by range. Let's see the example of this. So these are the lines. These are the records, whatever 1, 2, 3, 4, whatever, right? And what it does is this is a records called orders to partition, and it is repartitioning by range, and it's giving 3 partitions and based on the ID, right? So this, I'm assuming these are the ID columns, correct? And then you see the output. So output would be, of course, this is a test case is checking the size should be 3. You can check the data set dot partition size or something, it will show 3. Now here is what it's doing the partition. So with ID 10, 11, 12, 13, 14, these are coming in one partition, 15, 16, 17, 18, second partition, rest are in third partition. So that's how the repartitioning by range ended up being. So again, these are the number of partition, and this is the column of which partitioning has to be done. Correct? You can read this again. This is the copy. This is the same URL where from I copy paste the code. RDD range partition has little different implementation. So I will skip that. I'll skip that. Because RDD range partition, RDD we should not use. Generally, we should avoid. So I will just stick to the dataset range partitioning, and I hope you understand how the dataset range partitioning works. Any question? Good. I think it's pretty simple. You see the example shows it's pretty simple how it internally does. You can see that code here in the data set. You can go through this implementation of this in the partition.scalar. Go through the implementation of this if you want to see how it is being. Now you will know an implementation also. Okay, so these are the 3 topics which I had. Any question on these topics? If not, then I want to show you what will the next week will be your last session, and what we'll cover in the not this 4. I wanted to open 6th. This one. So next we'll focus only on the optimizer, how optimizer works, internal details of optimizer. I'll just give you a quick walkthrough of that so that you can read if you want, and and then we can go into details in the next session. Even if you don't read, we'll just go into the as much details as we can. Now, question from Amrita is, why do we use off-heap memory for storage? Is there a particular use cases for this? I mean, everything depends upon your everything depends upon your business logic. Generally, the way we might use this, I will give you some scenario. This is one scenario, but combination of other scenarios might be possible in your use case. The scenario is that you have some clusters which are being used where there's a lot of memory, but not all memory can be given to Spark, because there might be some other reporting systems or in reporting tools are running, or something else is running. So, but if they are not running, Spark can use the memory outside. So that could be one use case, because even if those systems are not systems run slow because Spark is consuming most of the memory, it should be, that is fine. So in that case, you say, okay, we are dedicating out of 64 GB memory, we are dedicating only 30 GB memory to Spark. Rest of the 34 GB is outside Spark. So if that's your topology, then use off-heap. That's one scenario. Other scenario is, for whatever reason, you are having huge data sets, and if you store this in the Spark JVM on the executor, on the worker nodes in the executors, then it's going to consume. Then Spark is going to have very limited memory for other things. If you want to avoid that, then maybe you can use off-heap memory outside the Spark. So these are first few of the examples, right? There is no hard and fast rule that whether you should do that or not do that. It all depends upon your business application and the business problem you're trying to solve. So I will quickly give you a very high level layout of how this optimizer works, and we'll go into details of this. There is a very good YouTube video on this. I think I might have a link of that also towards the end or somewhere. If not, then go to YouTube and search for Spark optimizer. So the way, this is very important. This you should remember always. When you run you have SQL query or use a data frame, and you submit that to Spark. What Spark does it's first of all creates an unresolved logical plan for you, and we'll discuss what that unresolved logical plan is. Then it refers the catalog, like whatever table names you are given in SQL query, whatever columns name you are referring in data frame, everything. It refers the catalog to validate all those are good. Then it becomes a logical plan. Then it runs some sort of optimizers. Like there are some optimizer, catalyst optimizers, and a couple of optimizers. It runs those and it converts a logical plan into optimized logical plan, and we'll see one example of that also. And then from the optimized logical plan, it converts the physical plan. So what is involved in converting the optimized logical plan to physical plan is it just converts into RDD. At the end of the day, everything which executes in the Spark executes in RDD. even though you are using data frame and SQL query, but this physical plan will be converting into RDD. Then is a cost model which gets over this, and we'll discuss about this cost model. This is cost-based optimization. So I'll give you a gist of this. What is this optimization and what is this cost-based optimization? I'll give you some hint, and then we'll cover in details next time. Then it applies cost-based model, and it considers a selected physical plan, which, oh, sorry, my mistake. This is a physical plan, which I'll show you the difference between logical plan and physical plan. It is not converted into RDD yet, but it sort of know. For example, in logical plan, you can say sort. In the physical plan, you tell which type of sort you will do, right? It's a merge sort or any other sort. So that's the difference between optimized logical plan and physical plan. Then you come with the cost model. I will tell you the cost model here and the optimization here. What's the difference? After cost model comes with the selected physical plan, and then code generation happens into RDD, and that's how it runs. So we'll go into these details. That there's a rule-based optimization, the cost-based optimization. The rule-based optimization is what this is. Cost-based optimization is what this is. And I'll very quickly cover what that is. And this is the, I think this is the link, this is the video. Most of this material come from this video only. So you should go through that. I will not go into details now. I'll keep it for the next time when we go into details. How this plan gets converted. This is a logical plan. You see aggregate project. So this query, this query the person is running. Select some from t1.id. There's two tables, T1 and T2, table 1 and table 2. He's joining this table and selecting the ID, and then 1 plus 2 plus T1.value as v. Right, T1.id and T1.value, where condition is T1 and T2 IDs are same and T2 ID is greater than 50,000, something like this, right? So this is your non-optimized plan or something. So aggregate project filter and all. And once you go to the next, it becomes your logical plan, because you see there is aggregate project filters, and this is the join. And logical plan describe the computation without data set. So in this case, it's more or less similar, but we'll see the difference here between optimized logical plan and the physical plan. Here you see the aggregate, and here you see the hash aggregate. Here you saw join in the logical plan. In the physical plan, you'll see sort merge join. So that's a difference. Then the one of the optimizer, right? We saw this. We are on slide number 14. Let me go back to this diagram. Now, how this optimized logical plan works, like how this optimization happens. So some example of that is here, where you see this example. We are adding literal 1 and 2. Right? Spark will check your DAG. This is DAG, direct acyclic graph. So here you are adding literal 1 and 2, and instead of having this tree structure, it will calculate this and keep the literal 3 for you. So that every time this calculation can be divided, instead of 3 node, it will have 1 node. So this is one more, and there are many such things, and we'll go into details of this. Right? Another thing could be that you are doing filter here. First you are doing join, and then you're doing filter. So why can't you do filter here only? So it might reduce a lot of your, you're joining, you're reading this table, and you're joining. And then over this table, you are saying, get me the records where ID is greater than 50,000. Well, why don't you get the records? Spark will check and figure out, okay, this condition could be applied here only. So that instead of getting millions of records, possibly you'll get only hundreds of thousands of records. So it will push the filter down here, right? So that's what it will do. That's another optimization it will do. So it'll combine all of this. And another thing it will do is column pruning. If you're selecting only few columns, and this table has hundreds of columns, this table has hundreds of columns, but you need only few columns. So it will do column pruning and select only the columns which you need. That's another thing. So it sort of creates into tree. And then I'll skip all of that, and I'll just tell you I think at the end is a good slide to tell you the cost-based optimization. So let's see cost-based optimization. Have I added it here or not? I guess yes. Cost-based optimization, right? This cost-based optimization is basically, it's the same thing. What it's going to do is, when you're joining these two tables, there's a build side table and a port side table. Smaller table is chosen as build side table to have a hash table. So you have two tables. Table 1 is 500 GB in size. Table 2 is 20 GB in size. So, but there's a filter on 500 GB table, correct? So, so this is 500 GB is 5 million records. When you apply filter, it becomes 1 million record, right? And only 100 MB. So now if you don't use cost-based optimization, this table, this is how the join will happen. So you will have the smaller table is build side. In this case, this smaller table it considers as this table, which is a build side table, right? It needs that for optimization. Like you might have heard of map side join, or you might even try to broadcast this table, right? To optimize. Knowing which table is smaller helps Spark in optimizing many things, right? So one of the things is doing the map side join, using the smaller table as a map side join table, trying to broadcast the smaller table. So if this information Spark gets wrong, then it will cause problem. So what cost-based optimization will do is it will figure out what is the cost for each of these node, and it will figure out after filtering it's coming as 100 MB only. So what it will do is it will consider this as a smaller table, and which will come as a build side table, and it might even do this predicate pushdown, which means it will do the filtering at the source, and it might consider this 100 MB as a broadcast variable and put as a broadcast into all the executors. So this is how cost-based optimization is done. We will cover all of this into a lot of details into the next session, but this just wanted to give you a high-level overview of how it works. Any question, any concern? Okay, let me stop the recording. Just give me a second. Stop. Correct. So the optimizer goes through this process. Any SQL or data frame first gets converted to unresolved logical plan. Then via cataloging, it gets converted to logical plan, and we'll now go into details how does this happen. From there, optimized logical plan via logical optimization, then physical plan via physical planning. There are many physical plans which get created. Out of this, one physical plan gets selected based on certain cost model, and we'll go into details of that. For that physical plan, RDD is generated. The tree is the main data type. The optimizer, all of these things are happening via optimizers, and optimizer runs rules in each of these steps, and we'll go into the type of rules for each of these separately. Now for rules to run, it takes everything, it takes a tree as an input. Some rules are running here, some rules are running here, some rules are running here. So at every place, a tree is an input and another tree is an output. So what happens during that time? So consider this tree, a tree has node has type or 0 or more children. Now this tree you can represent as this. So you have a literal, which has constant value. You have attribute, a node called attribute, which has which is type string, and then you add node, which is which has left and which is right. So it's basically sum of two expressions. If you have to represent this tree, x plus 1 plus 2, you will using these expressions, you will express add an attribute on the left hand side is x, and on the right hand side, this is another one which you again which you again have an add node, and then you're adding literal 1 and literal 2. Now the rule, the only purpose of rule is to manipulate the trees, to optimize the tree. So it takes one tree as an input, applies the rules, and outputs another tree. Now how does it apply the rule? It applies the rule based on the pattern matching rules. So we'll take one example. So in this case, this is a scalar syntax. So when you say case, basically immediately after the case is a pattern. So, and this is a transform. This is a transform method, and we'll go into some code. If you have to write your own transform method, does Spark allow you to do that? If it does allow, then how you can write it? So here it finds this pattern, and this pattern is basically there's a add node which is summing up two constants, two literals. So instead of having a 3-node tree, you can have only 1-node tree and say replace everything with 1 node which is literal, which is a combination, which is sum of these two constants. So case keyword is matches the pattern. This is what we said, and here it will match add node which has two literals as subnodes, and outputs a new node which is sum of subnodes. So now if you see x plus 1 plus 2, right here, whatever example we discussed, it will result in x plus 3. So these two nodes will go away from here and gets converted into one constant, which is 3. Okay. So now pattern matching functions. So you see this an example which we saw. These are transform functions. So in the transform method only you are calling this, right? These functions. This implementation is inside the transform method. And these are partial functions. So what are the partial functions? They don't get applied over the whole tree. They get applied only on the part of the tree which is matching that pattern. So that's why we call those partial functions. Catalyst called transfer method to apply these rules. And I will show in graphical way later how does that work. And one important thing is here we discussed one transform which has only one rule, but you can have as many rules as you want. Just example of some other rules. So this rule we already discussed. If you have two literals, getting added, then why you want Spark to go to navigate this tree, the two literals, just sum this up and put it here, right? So that way you are reducing the tree size also. Another way is if you have some literal, if you have some add node on the left hand side is some value, on the right hand side is literal 0, then just convert that into left hand only. You can ignore this, right? This node. Same is the case vice versa. On the left hand side you have literal on the add node, and left hand side of add node is literal, right hand side is right. Just replace everything with right only, right? Because adding anything to 0 doesn't change anything. So idea is to show you that a transform functions can have many rules. Now what happens is a catalyst groups those rules. So again, I'm just reiterating. Let me go back to the previous. Here it is. So catalyst group, there are rules here, there are rules here, there are rules here. Whatever rules are getting applied here, for example, those are grouped into batches, right? So these are grouped in batches, and at each place here, it runs those rules in batch one after another, correct? Runs each batch on the tree until, and how does it know? Like there are, let's say there are many batches, there are many rules, convert into number of batches. So start with the one batch and start applying the rules, and it keeps applying those rules again and again and again till the tree stops transforming. And I have an example of that when we go into details. Why does it need to apply again till tree stops transforming? What is the need for that? I will discuss that later. But here idea is that you understand that you have the rules into the batches, and it applies those batches one after another, and within one batch it keeps applying those rules until tree stops changing. Why does it do that? So one transformation in the tree might result in a subtree which can be transformed again based upon the rule. So that's the reason. Let's say if you have added, let's say there is a little here also, so if you have little here, you have little here, you have add and end. So first transformation you do is this, and you convert into one rule. The batch has one rule, so one iteration will convert into this and put one literal here. Then it applies the same rule here and say there's a literal here, there's a literal here. Then I don't need these two nodes. I'll just put the literal here. So second iteration happens. Then it tries to apply the same thing again. It finds there's no match, so it keeps the tree same, and then it just move on to the next batch. So, so Spark executor flow, so I just repetition of what I just said. Catalyst tree transformation happens in 4 phases. Analyzing this, focus on this, analyzing a logical plan to resolve references. So unresolved to logical by analysis. A logical plan optimization, physical planning, code generation to compile parts of the query into Java bytecode. So that's what it does. Now go into each of these. Analysis. A relation either from SQL or a data frame is given to Spark, right? It may contain unresolved attributes. So this is what I said earlier also, that you have select column from table 1. So here Spark does not know whether column 1 is valid column or not, whether this column exists in this table or not. Spark does not know. So it applies the rules, and this rule will tell if will validate this column exists in the table, and it will put into the logical plan. And how does it do that? It has a catalog. So from this catalog, it references, like if you deal with Hive, then Spark has integration in Hive. The data from on this catalog will come from Hive. Otherwise, Spark, whatever your data source is, it just refers to that. and tries to validate this via catalog and convert into logical plan. Second one, the logical optimization. So this optimization is rule based and cost based. Now, what is rule based? Rule based, you have certain fixed rules. One is predicate pushdown, projection pruning. I don't know whether all of you know predicate pushdown or not. I have an graphical example of that, but idea of predicate pushdown is simple. Let's say to help you explain better, let's say you are creating a data frame by querying a MySQL table, and that SQL table has millions of records or billions of records. But your query is that select from that table where the either in your data frame filter condition or where clause in your SQL, wherever you put, and you say where column 1 value is greater than 10,000. So now the table might have 100 million records, but when you apply this condition where column value is greater than 10,000, it returns, let's say 1 lakh record out of 100 million. So what Spark logical optimization will try to do is it will try to push down this predicate. Predicate is nothing but a where condition. So we're trying to push that where condition on the database server itself, on the MySQL itself. What it will try to do is it will try to evaluate out of 100 million records, come up with 1 lakh records on the MySQL server and return and pass that 1 lakh records over the network to the Spark layer. If it does not do that, then your all 100 millions will be passed from MySQL to the Spark layer. Then on the Spark layer, you will be out of 100 millions, you will be applying filter and figuring and getting only 1 lakh out of that. So that is not performant. So performant is push it down on the DB server, push down the where condition on the DB server or whatever your data source is, and get it evaluated there, and then get only the needed. So that helps in the improvement a lot. Now, how do you check that? I think we discussed that during our session on the explain on the plan session, is that you put explain. In the explain, you can see predicate pushdown will be there. If it is blank, that means predicate pushdown is not happening. So if you are querying a RDBMS or any table where you want predicate pushdown to happen and your plan is not showing it, then there is something wrong. Then you have to do something in your code, maybe put the proper filter condition or some syntax might be wrong in your code, fix that and print the plan again. You will see predicate pushdown is equal to true, and then it will tell you on what basis it's doing the predicate pushdown. Projection pruning. Projection pruning is, let's say you have 100 columns in a table or in an entity in a data source, and you need only 10 columns. So your select query is select table 1, select column 1, column 2 from this table where condition is this. Condition where condition is predicate pushdown, select column 1, column 2 is projection pruning. So your table might have 100 columns, but you're selecting only 2 columns. So it will prune or rest of the 98 columns and give you only 2 columns. So there are many rule-based examples. I'm just giving 2, but you can read the Spark documentation of Spark code and figure out there can be many more such examples, and you can build your own rule-based optimizer rule. And I'll talk about it towards the end. The second type of optimization is cost-based optimization. Cost-based optimization, this is what it is, right? It creates many physical plan and compared for the cost. At this moment, the cost is only the number of rows. So once it finds, and what it does is, at this moment it used only for joins. If it finds that there is, by applying this predicate pushdown, there are 2 tables you are joining in your data frame, for example, right? Data frame is result of 2 tables, joining table 1, table 2, or in your SQL query, you are joining table 1, table 2. So what it will try to do is, it will try to optimize this. It will try to put all the predicate pushdown, projection pruning, and all of this, and try to figure out now out of these 2 tables, which one is smaller table, and is that table that small that it can be put into the, it can be broadcasted and broadcast join can happen. So that's what physical planning it will do. So physical planning is focused only for joins at the moment, and that too only for making sure whether broadcast join can happen or not. And I have an example for that also later. Now there's another thing which is happening. If you're dealing with Hive, there is a command in Hive where the command looks like something: analyze table and gives a table name and compute statistics. So if you give analyze table and in that give the table name and mention compute statistics, it will give you some idea what that total number of rows in the table are, what is the min value of integer column, what is the max value of integer column, some metadata it will give you. Another implementation of this physical planning optimization is that it will refer that if you're dealing with Hive, it will refer that and try to come up with the cost model based on the number of rows and the filter and everything, and try to arrive the entity which might be smaller. So it uses that also here. So these are the two things, rule-based and cost-based. A physical planning, which is this. We discussed this cost-based optimization, discussed in last slide too. So many physical plans are created, right? It will try to create many physical plans, and based upon the cost, which is only joined at this moment, it will try to see out of this physical plan which physical plans suit better. Like, to give an example, one physical plan could be I don't know, maybe predicate pushdown is not happening, created that and figure out cost is high, versus another physical plan which has predicate pushdown happening and cost is less because number of rows are less, and it found out that is better because with that physical plan it can push one data into the broadcast and do the broadcast join. So that's how it happens. Physical planning also performs rule-based optimization, which I already discussed, right? One unique example is pushing filter. Let's say you have in your data frame, you are saying data frame dot map then dot filter. So it will figure out that you have dot map and then have dot filter after that. So why not apply that filter inside the map function itself? Because whatever you are filtering on, that column is available in the map also. So it will apply, you have 1 million record and you are applying a map function over those 1 million records. So map function will go over 1 million records. After that, you are applying a filter and saying where column 1 value is greater than 1000. So what this will do is it will, put, because it's generating the bytecode for you anyway. So it will put that, condition where column value is greater than 1000 inside your map function itself. So that your map function also gets reduced and you avoid one extra step also. Of course, it also does the predicate pushdown to DB, which we already discussed, that if you are reading from MySQL or RDBMS or some DB which is allowing the where condition to be evaluated on the DB server, it makes sure it gets pushed there, and then you get the right data and you get the data in an optimized way. So that's how physical planning works. The code generation. So code generation is basically, it just generates a code. And generates a code, it has an optimization built in. That code gets generated in a way that it just speeds up the execution. And this code is in nothing but an RDD. You are dealing with data frame, data set, or whatever, all of this. It does a hell lot of optimization in all of these steps. Ultimately, it generates an RDD and it executes. These are some of the links. I have referred those links to create this material, so you can, and these are very exhaustive links. I mean, I think this is half an hour video. This is one blog. This is another video. Go through this. You might get more insight into how optimizer works. Now we'll go into one example. So I think we covered half of it already. So we'll go into one example. Let's say you have this query. Select sum from select T1. There are two tables we are dealing with. Table 1 and table 2, and these are getting joined. So what we are doing is we're selecting table1.id 1 plus 2 plus table1.value as v, and then we're getting sum of v, and we are applying this where condition. Don't try to interpret this. Only thing you understand from this is that there are two tables, and these two tables, we are joining these two tables, and we are selecting few columns from these tables based on certain where condition. Correct? And so there's a tree which will be created. So there's an expression, there are attributes, correct? So what is an expression? What's an expression? Expression is basically represents a new value, compute based on input value, compute based on the input value. So this is an expression, for example, 1 plus 2 plus T1 value. So an attribute is a column of a data set like T1.id, T1.value, and things like this. This is an attribute. So these are expressions and attributes. Now the optimized query plan, like we discussed, the logical plan, then optimized logical plan, and all sorts of things. So So this is a plan. So what it does, it will try to create a tree structure out of it, right? So select, you have sum, right? So it becomes an aggregate, which represents sum of V. Then you are projecting that you are getting only T1.id and 1 plus 2 plus whatever this will be. So this is a projection. Then you are applying filter, right? This where condition T1.id is equal to T2.id. These are the filters. Then you're doing a join, right? The table 1 and table 2. So this is how it will construct the tree structure in the beginning. Then what is going to do is in the logical plan, it's going to create, of course, we discussed, right? It will refer the catalog, make sure the attributes are valid, the in the query whatever given is all valid. Then ultimately it come with a logical plan. So a logical plan describes the computation on the data set without defining how to do the computation. Take this example. You are just taking aggregate. You're not, and we'll see in the other plan, what is this, how this aggregate is created. So logical plan does not tell, it just tell what you want to do without defining how you want to do. Join, what type, how the join should happen. I think we have defined here in the physical plan, but logical plan will just mention about the join. And so this is the logical plan, correct? And then physical plan will do how to do those things. If you have a aggregate, then what type of aggregate? This is a hash aggregate. If you join, what type of aggregate? Is a sort mod join. Here I am reading the files. So what type of file reading is happening? Is Parquet join is happening. So if you would have seen in our example where we went to the Spark UI, you would see in the UI you can see the Parquet scan is happening in the graphical user interface, and you can see how many files it read, and you can see all of that on the last tab. I think the SQL tab on your UI. So this will appear there as well. And physical plan is the one which is executable. Transformations. So we'll go into details. I think more or less for our understanding, if you have understood till this much, this is more than enough. Now I'll be double clicking on this and going into details of this. So transformation without change. There are two types of transformations. So one type of transformations are with do not change the tree type. So you have expression and expression, logical plan as a logical plan, physical plan as a physical plan. Other transformation is transforming one tree type to another tree type. For example, logical plan to physical plan you convert, right? By applying the physical planning we discussed, a few slides back. Now, this is a repetition, as I said. So take this example, a function associated with every tree used to implement a single rule. So we discussed the rules, right? One rule, and then there are batches which will have set of rules. So let's take this example. You have this tree 1 plus 2 plus t1 dot value, right? So this is 1 plus 2 is a literal here. It's going to add node, and then this add and this t1 dot value gets added here. So what it will do, one rule will do is 1 plus 2, it becomes 3. So all these 3 nodes get converted into 1. So this 1, 2, 3, 4, 5 node tree gets converted into 3 node tree, right? This is one rule, which is example of simulation of one rule which gets executed. And now a transform is defined as a partial function. So we discussed that, correct? And partial function and function that is defined for a subset of its possible arguments. Like in this case, a tree, we are applying a pattern on that tree, and whatever pattern is matching, where this transformation is happening over that. So that's why it's called a partial function, correct? So this is we discussed that this case statement. The case statement determines if the partial function is defined for the given input. Like you have a tree given to it, it just validates if this is matching on that or not. This highlighted in the green is match. A tree has that pattern or not, right? So that's what it is saying. Now you can combine multiple rules. Also, we discuss in one transform you can have multiple rules as well. So one is predicate pushdown. You see there's a filter, right? Instead of applying filter on t1 dot, let's say t2 dot id is greater than 50,000, it pushes that filter here. And so now, because from the database itself, you're getting less records and your join will be better, correct? Instead of getting all the joins and then doing the filter, it's less performant, whereas you are filtering less records and doing the join, correct? And then you will see here, you are projecting also. The column pruning. So column pruning we did not discuss. And by the way, another thing which I forgot to tell you is the predicate pushdown is happening, right? So filter is getting pushed down, predicate pushdown is happening, and this is projection. You're doing column pruning. We discussed that already, right? These tables might have many columns, but in your query, you saw that the select some query, you need only few columns. So T1.id, T1.value here, and T2.id, only 2 columns here and 1 column here. So why to get all the columns in your, get the data for all the columns here? So it will do, column pruning. So it will do projection. How it does column pruning is by using projection. And projection tells that, you select only these columns and select only this column from this relation. Now we'll discuss about transforming into, this is just a simulation if you're transforming into the same type of tree, right? And we discussed the rules are applied in form of batches. So so batch, a rule execute transform a tree to another same type by applying many rules defined in batches. So it in another slide here. So in one batch, you will keep applying these rules, and these rules will keep right. You see this rule 1, then rule 2, then another rules, then go back to rule 1, then rule 2, then rule 10 goes back. Where it stops is that when you reach a fixed point. What is that fixed point? A fixed point is where the tree stops transforming. When tree does not transform anymore, that's where you stop the stop these rules, then move on to another batch and do the same thing with that batch. And each of these is getting executed in your analysis phase, in your optimization phase, in your physical planning phase. So each of these steps, each of these the batches which are the batches of rules which are getting executed in analysis phase, there are different batches of rules which are getting executed in your optimization phase, and same with physical planning phase, right? So once rule executions, a rule execute transform a tree to another tree by, okay, this is the same thing. Every rule is implemented based on the transform, right? So what you can do is you can have the when you implement the rule in your transform method, you can tell that you apply rule only once and you don't have to repeat. That is also possible. So instead of going through this loop again and again and again, you can always say the fixed point is here, till the fixed point is used, it just keeps applying. And here you can say, for particular batch, you can say you apply it only once, don't go into these batches. So that's also possible. And we'll see the Spark API, which you can use if you have your own rules, if you want to create your own rules and be able to specify these configurations. How does it convert from logical plan to physical plan? So logical to physical plan conversion happens by applying set of strategies. So in below example, logical projection is being converted to physical projections using some strategy, right? So this is extraction strategy. And then logical filter is being converted into physical filter. When more than one strategy needed for conversion, plan later is used. You see, this is an object, this is a scalar code, right? And you're having one strategy, and this strategy you are doing something, right? You are projecting, you are filtering, and after that you want to apply more strategy, then you can say plan later. So in the tree, whatever in your strategy set of strategies, whatever is the next strategy, it will execute that. Putting it all together, so you have this data frame, SQL, and data sets. Now data set, I was not there in the first slide, but here data set is also there. It goes to query plan, unresolved, logical, optimized, physical. It it does all of that. Ultimately, RDD comes out. So this is all put together. We'll go into before I go further. Any questions so far? Okay. So now this you don't need to know the details, but this is what we already discussed, and I'm just copy pasting from the Databricks documentation, and here just trying to explain the same thing by repeating. So the steps in analysis, it transforms an unresolved logical plan to a resolved logical plan, and it uses a catalog to find where data set and columns are coming from and the types of columns. The logical optimization transforms a resolved logical plan to an optimized logical plan, and that we discuss so many optimizations happening, the rule based and the cost based and all those things. The physical planning, strategies plus rule executor, it does both of these things. It transforms an optimized logical plan to physical plan, and rule executor is used to adjust the physical plan to make it ready for the execution. Yeah, I think code generation, I'll leave it for time being. We know how, it uses some, it uses some Scala library for code generation. So it just read it into RDD. So I'll skip this also. This is what we'll discuss, extension points. If you have to write your own rule, how you can do that? And these are the videos. These are PPTs and the video. You can go through this if you want to know how to write your own rule. You want to add your custom code to the Spark Catalyst pipeline. So how to do that? So same diagram in a different view, in a different coloring and in a different way. Your parser, unresolved logical plan, analyzer. And so here, whatever was analyzer was here, I put it as here, and whatever was here, I put it here. So unresolved logical plan goes to analyzer. Some rules get applied. It converts into the analyzed logical plan. Then it goes to optimizer. Some rules are applied. It converts into optimized logical plan. Then it goes to Spark planner. Spark strategies and the rules are applied. Then it gets converted into the physical plan. Right? Now, supported customization. So same thing here. You just take the same thing. In each of these, in your parser, analyzer. Now, what you have to know is these are the verbs. These are actions. Like these are the things which are doing some actions. So parser is doing parsing, analyzer is doing analysis, optimizer is doing optimization, Spark planner is doing Spark planning. So you can have your own extension points. You can have your custom parser, you can have custom and rules for analyzer, custom rules for optimizer, custom Spark strategies. How to do this? So they have come up with an extension API at very high level. There's a new Spark session extension class. So this class is used. It has methods to parse the customizations. Basically, it holds a customization. And when you are creating a Spark session in the Spark session builder, Spark session.builder, we have been using this for quite some time. In Spark session builder, there's a method called with extensions. So in this with extension, you would have implemented your new class which has this Spark session with extension. It should extend the Spark session with extension, and whatever your implementation is, you can pass that class in with extension method while doing the Spark session.builder, while using Spark session.builder. Some examples how it happens. So in your parser, when there are inject methods, these are extension hooks. So injection function used to inject a function available in the next Spark release. Right now you have these implementation. You have inject parser, you have inject rule. So I think they're coming with some inject function. So that will be happening in the next Spark release. But in your parser, you can use inject parser to have your own parser work on the plan to pass pass the inputs data frame or SQL. You can have for analyzer. You can inject resolution rules. You can inject check rules. You can inject post hoc resolution rules. I don't know what HOC means. Post hoc resolution rules. You can inject your optimization rules and all of these things. Inject function is in this Jira ticket. You can go and check this. Here you can inject your planner strategies. So once you have this, once you use this class, you'll get availability to all of this. You can override and do whatever you want. And now, so that's about it. I think for your customization, you can use this class and override any of these methods and build your own logic based on your business requirement. You can come up with what type of data you're getting, what type of business processing you do. If you are thinking some business processing is constant, which you do no matter what, maybe put that it doesn't change based on the input of data or something. Maybe put that in your optimizer. Possibly from 2 node you can convert into 1 node, something like this you can always do. So this is about your custom customization of your optimizer, analyzer, or planner, or everything. Now what we'll do is we'll take one example, how cost-based optimization works. We talked about cost-based optimization 2 times in this session. So we'll take an example. Now this is used while joining 2 tables. So now when you're joining tables, you have build cell table and probe side table. Smaller table is chosen as build cell table, right? Build side to have hash table. We'll take 2 examples. Let's say you have table 1 and table 2. This is table 1 and this is table 2. Table 1 is 500 GB in size. Table 2 is 20 GB in size, correct? And table 1 has 5 billion records. This is 100 billion records, something like this. And now if you don't do any planning, and you have filter on the, one important thing is you have filter on the 500 GB side. Now after filter, this 5 billion records get converted into 1 million records, and this 500 GB gets converted into 100 MB. If you don't do any optimization, by default, Spark will think that this is the smaller table because this is 5 billion and this is 100 million. It will try to make this as your build set table and try to see if this can fit into the this can be used as a broadcast variable, and broadcast join can happen over this. But and you can sorry, and then I think that's it. But if you apply the cost-based optimization, then Spark Spark will filter this out, and then consider this table, whatever is the output of this table is, it will apply the predicate pushdown on the source. And once you apply predicate push on the source, out of 5 billion, you're getting only 1 million. And comparing between 1 million and 100 million, the cost-based optimizer will figure out this is a smaller table, and this smaller table can go into be sent as a broadcast variable, and broadcast join can happen over this. So this is the advantage of cost-based optimizer, because it just calculates the cost. What is cost in Spark terminology, Spark automation terminology? Cost is not dollar or rupee or something. It's just the number of records. And, so that's what cost is for Spark optimization. I think that's about it.
Sandeep, one question. Let me pause the recording.